my fiber.
You guys can talk, do whatever it is you need to do. Don't even worry about it.
To the Zoom link for the observations about half an hour ago, and it was Percy, the TO.
You guys can talk, do whatever it is you need to do. Don't even worry about it.
The TO and no one else. So I don't know what that was about. But
I just logged in as well.
Percy is not our
pieces there.
essay for tonight, so I assume he was running the last program. So he skedaddled quickly. We must be getting close to our start time, right?
Yes, just letting you know we are live, and I'm about to let the Zoom audience in.
Okay.
I'll see you guys in 15 or so minutes.
Right.
Can I go into 2 different Zoom calls at the same time? What happens if I open another Zoom call?
You don't have one session running at the same time. I looked at it.
Oh, hold on.
You can.
You just have to do it from another email.
Yeah.
I missed all of that.
You can start another Zoom. You can join the Zoom via another email account. Something like that.
Okay.
Or give it a go. It's not a big deal. It should be fine. Yeah.
Yeah.
I know what happens.
So am I right in thinking the Keck observation doesn't start for another hour? 10:20 UTC.
When does it start? What time does it start?
10:20 UT.
So that would be 11:20, right? Yeah. That sounds right. Oh boy. Well, we can fill for time, right?
Well, probably go straight to Jupiter then, right? Because 10:20 occultations at 12:38. That's right.
Yeah, so there's a bit of time to set up on the star and get Cal's first.
Yeah.
Okay. And then Jupiter pretty quickly.
So yeah, 11:38 UT. The occultation happens an hour and a bit after we start.
Right.
11:38.
That's UT though.
Okay, but we
Yes.
start. Okay, UT.
Oh, yeah. So we'll have a bit of time. I'm going to see what happens if I try and open the Zoom.
Might get logged off.
It'd be good to know, wouldn't it? Yeah, I have to leave and join. Okay, well, I won't do that now. It's annoying though. Well, we can use Discord to talk to Luke for sure, right? If we need to.
I can join on my iPad.
Well, that's true. We've got all of the login information, so I can do the same.
But the summit is actually looking quite clear right now. A few clouds, but
2 clouds.
2 clouds.
Does look clear actually.
I pull this to the side. I should be able to, because I have the live stream. Oh, it does. There's a glow on the horizon. I don't know if that's the moon or.
I think that's Hilo. Huh?
Oh yeah, there must be because of the low cloud. I've got it on my TV over in the corner, but it's very dark. Not to see anything.
That could be something we could share as well.
Yeah, do you want to share it?
YouTube. Mini player? No? Is there a way of filling just the browser screen?
You can share just the browser screen. Mhm.
So there we have the view. And there's definitely stuff on there. The other thing to bring up is the Manichaea weather center.
Yeah.
Current conditions.
It's all very small.
Yeah, well, it will be, right? I mean, to fit it all on. Whether it's possible to share. I mean, I can definitely pick out the 4 panels easily enough. I don't feel like we should legitimately share someone else's YouTube live stream there. It's just the most informative of what's going on right then, right?
That's good.
I'm also going to have organization going to send it down in the building.
Yeah, it's looking clear-ish.
It
It's
is.
improved in the last
These-
hour. That's amazing.
Seems to be improving, but touch wood.
Yeah.
What was that website that James had that had this stream, but with what is in the view, field of view?
Well, the annotating one.
Yeah.
Oh, if you click on descriptions, the start chart. Get the tune as well.
Oh, nice. So it is Jupiter rising up. I thought it might be.
I was enjoying that.
The song, the tune.
Yeah, we've not had that before. Some nice background music.
Elevator music.
But Uranus is just there. We could just go look at Uranus. Can't see any familiar stars. And that's what Jupiter looks like right now.
Okay, great.
Hmm.
So right now, you wouldn't be able to see much of the northern aurora.
It's fading away.
Yeah.
South is coming up, but because we're at +3
Mm.
sub-Earth latitude, it's only a very slightly better view of the north and the south, but because the south is so close to the pole, it does have quite a strong effect on what you can do. So
Yeah, so just for everyone watching, like in that diagram of Jupiter in the bottom right, then the blue lines there, are they blue? At the top and the bottom, that's where Jupiter's northern and southern lights should be at this time.
yeah, exactly that. And it's a tiny little picture, of course, but we can zoom in later to sort of talk about what we're doing more. But the James Webb observations are slow enough in being completed that by the time we're going to start over on the top left-hand side of the planet and start moving around clockwise around the limb of the planet. And by the time we get up to the pole, the aurora will have rotated all the way around again, I think. So while we're only on Jupiter for a few hours because the Earth is spinning and it's hard to do longer, James Webb will just sit there and continue to take data for, I think it's 24 hours or something, right, in total.
Yeah, it'll finish. I can tell you exactly when it finishes. So James Webb is going to start taking data in exactly 1 hour. It'll finish tomorrow at 2 o'clock in the afternoon.
Wow, that's very exciting.
Isn't it?
Yeah.
It's pretty insane. I haven't heard much from Hubble since we first talked about collaborative observation, so I don't actually know what Hubble will be doing tonight. But I think something. They've got UV observation, so that's looking deeper in the atmosphere than we are. But there's some really interesting comparisons between what you see in the UV deeper down and what we see in the aurora. So there's some potentially exciting comparisons there. But I also wonder whether there will be something we can do with the UV emission on the limb, depending on whether that gets taken.
So then we'll look at the satellite images.
What's that for? The weather?
The satellites. Water wave vapor. Isn't it?
Right. I think we're set up. Just waiting to get on the telescope. Same is true for IRTF. The same is true for James Webb.
Yeah.
So we now engage in the most common pastime of a professional astronomer, which is waiting and wishful thinking and hoping for the best.
I'm really glad the telescope's actually open because the forecast was terrible.
Yeah, really bad forecast that seemed purposefully designed to frustrate us, but the clouds have dropped below us somewhat. Hopefully they will stay there. Very clear tonight.
It does. Is there a bit of haze there? But it looks really good.
Certainly on the horizon, you can see the glow.
Yeah.
You can see the outline of several telescopes and almost see our second telescope. Keck is the black outline on the front, the top left corner. And we will be observing from the left-hand one later. And then there's a little dome almost peeking its way out of the right-hand dome, which you can't really see unless you know it's there. And then on the right-hand side, the glow on the right-hand side is 3 telescopes up on the summit ridge, and those are illuminated by the glow of the city of Hilo behind it, basically. So there's hazy cloud around. There's some cirrus, which is going to make the sky quite variable and more difficult to use, but that, you know, we will cope with that later.
All right, maybe now we could, since you guys are set up, and get started on a full introduction. What do you think?
Sounds good.
Yeah.
Maybe then. So I'm going to go ahead and share my screen. I'll stop you from sharing your screen momentarily. And I'm going to turn on my camera and say hello to our wonderful audience. So hopefully, hello everyone. Thank you so much for joining us today. My name is Lucinda Offer. I'm the Royal Astronomical Society Education Outreach Officer. And again, I'm so excited to be welcoming and working with Professor Tom Stallard and Dr. Henrik Mellon, who are sharing with us again their time on a couple of telescopes here, some very exciting ones. We have been on the IRTF, the infrared telescope facility on Mauna Kea before. And if you go to our YouTube page, you could see the previous 4 observations. 3 we did of Uranus, And the first one that kicked us all off was Jupiter that we did over COVID. And I'm so happy to be working with them again today to do eyeing the ionosphere. Have a little bit of a tongue twister, which I'm the one who created that title. Not sure why I do this to myself, but eyeing the ionosphere, Juno, JWST, and Jupiter. And they've also added a second day, because today we are looking at the ionosphere of Jupiter and the limb of Jupiter from two different telescopes. We're looking at the IRTF on top of Mauna Kea in Hawaii, and also doing a 22-hour scan, I believe it is, via JWST. And from what I can tell, Professor Stallard is in charge of IRTF, and Dr. Mellon is connecting us to JWST, or starting the observation, which I think he said starts in another hour. So let's just take a quick look at our program today. Let's see if I can get that on here, just so you can know what to expect. So we're just getting started. We're at about 10:20 right now. They've been doing the telescope setup. 10:30 approximately, well, really now, I believe Professor Stallard said they're ready to go. We're getting an observation, hopefully. The sky looks really good. The weather's a bit iffy, but we're gonna push through. We've got lots of exciting speakers today. 11 a.m., Professor Stallard will talk to us about today's mission, exactly, much better than my description. But you can go to our Eventbrite page. Also on the Eventbrite page, you can sign up for day 2, which will be next week. When we'll see some of the imagery that they got from JWST today, fingers crossed, and that we could take a look at them more closely on Monday. At 11:30, we'll hear from Dr. Mellon on JWST, and 12 o'clock, Dr. Johnson, who is also joining us this morning, will give us a quick presentation on ionospheres. Why are we studying ionospheres? What's their importance for the work that we're doing this morning? We'll get a couple of observation updates throughout the day. We're also having Professor Nichols from Leicester University join us, talking about Jupiter's far UV auroras. And then we're going to hear from our own RAS librarian, looking at what we have in the collections on Jupiter for our librarian at the Royal Astronomical Society. PI, Principal Investigator Katie Knowles, which is a student of Professor Stallard's at Northumbria University, who is in Japan, working with Dr. James O'Donoghue, and they will join us from Japan around 2:30. But they're going to join us on the observations earlier than that, but they've got some work to do before they can give us an update on the work that they're doing. And then finally, at the end of today's observation, it's a 6-hour observation from 10 a.m. now to 4 p.m. And we may go long. Lots of these, we plan 6 or 8 hour observations, and they always go long. And believe me, they go by really fast because they're so much fun to watch. But Dr. Dunn's going to talk to us about orbits, which is original research by young Twinkle students. And it's a program out of UCL where they give data to students at secondary schools, and they bring in PhD students to facilitate these courses to help them do discoveries looking at data, observational data. And they make all kinds of amazing discoveries on exoplanets, looking at atmospheres of other planets, really exciting stuff. So he's going to share with us all about that. And he's going to bring in some students to talk to us and do a Q&A with Professor Stallard and Dr. Mellon, and anyone else from the H3 Plus team who's going to hang out there with us. And he's also going to have a student present to us some of their research that they've done, a study on, I believe, Jupiter on X-rays, I believe it is. So a lot of exciting stuff today. And I, again, am Lucinda Offer from the RAS, and I'm going to have a co-host, Dr. Sheila Kanani, which is my colleague from RAS, also an education outreach officer. And just fun stuff, excited to go. And I'm going to get back to Professor Stallard. And we also have Dr. Rosie Johnson with us this morning. Thank you for joining us, Dr. Johnson. So, and Dr. Henrik Mellon. So thank you. Thank you all, and go back to you.
Thank you very much.
Great, thank you. Yeah, it's a busy day today.
It's the busiest day, I think, that we've ever had. And we'll talk more about why that is and what has happened over the day. But I think as exciting as it always is to observe on any telescope, when we get to look at Jupiter or one of the other giant planets. Some of us have been doing this for a while. It's a rare day today. Sleepless nights in preparation for what promises to be probably some of the best observations we've ever taken of Jupiter. So we will wait and see whether that comes out. As an observer, as an astronomer, you decouple yourself from reality a little bit when you're actually doing the experiment and running the measurements themselves. Because if you tied in your hopes and dreams of what data would be like, it would crush you. You'd never be able to do it again. So it is an interesting state of being doing these observations. You sort of become your own lab rat. You assign the observations you have to do, and then on the day, you just run through and do the observations as best you can, no matter what the conditions, and hope that what you can get is the best you could get without actually worrying about whether it actually answers the science question that you want to answer. Because, as I said, otherwise, all of the many hours you put into preparation of writing proposals and planning macros for your observations and all the hours you've poured in just drain away as clouds roll in.
Yeah. And what's unique about today is we're looking at Jupiter with James Webb, of course, but we'll have not only one telescope, but two telescopes looking at Jupiter at the same time. And that's extremely rare. And it's really hard to schedule this kind of thing. And I think we're extremely lucky it's actually worked out. And it looks like, touch wood, the weather in Hawaii is largely cooperating. So
can you guys just share with us where you guys are joining us from today?
So I'm Professor Tom Stallard, hello. And I work at the university, at the Northumbria University up in Newcastle. I'm currently in Whitley Bay, just outside of Newcastle on the coast, observing from home, just because pragmatically it's easier to do that right now. And that's the joy of modern astronomy, is that you effectively potentially can do it from anywhere. But I have an enormous monitor I've borrowed from work in order to do this, because while it is possible to do this from anywhere in the world, you need some interesting technology to be able to do it effectively. So that's where I am. Henrik?
Right. Well, I'm Dr. Henrik Mellin. I've got you all on a big screen in front of me. That's what I'm looking at, which is very pleasing. So I work at the University of Leicester. I'm a James Webb Research Fellow, so I spend most of my time looking at James Webb data of the giant planets, Jupiter, Saturn, Uranus, and Neptune, which is very, very fun. I love it. So we're in the meeting room here. It's very intellectual with lots of books that no one reads, I imagine.
Rosie.
Hello, I'm Dr. Rosie Johnson. I'm a lecturer at Aberystwyth University, and I'm also part of Team H3+, so looking at Jupiter, surprisingly, in the infrared, focusing on the aurora, and how the H3+ ions move around in the auroral regions, which is very exciting. Yeah, so that's all of us. So
yeah,
we're spaced out across the country. The rest of our team will join us from across the globe.
We can talk a little bit about some of our colleagues. So we're quite tight-knit community. A lot of people involved in this are either people who were taught by my supervisor or taught by me at some point. So Henrik had the same supervisor as I did long ago in the annals of time. Rosie is a former student of mine. We have Dr. James O'Donoghue out in Japan. He is currently a JAXA fellow there, but he is moving back to the UK to work at the University of Reading in about a month or two, having been out in Japan for about 3 years, who is a former student of mine. And then we have Katie Johnson, who is the PI on the IRTF observations we'll be talking about later in the day. That's a program of observations that we've been working on for about a month now, and we've got some amazing data from that. She's my current student. We have Luke Moore, Dr. Luke Moore, out in Boston University, who is not a student of mine and in no way affiliated with us directly, but is a fantastic chap and one of our most esteemed colleagues. He is leading the observations on the Keck telescope today, and is deeply embedded both in our group and in the use of Keck as an instrument to look at the giant planets. He has students that we probably won't see today, but there's Kate and Khalid, who have been learning about doing observations with us over the last month. We have a series of other students that some of you have seen before if you've watched previous streams. So Emma Thomas is not with us today because she's busy, but is working her way towards some really interesting Uranus observations at the end of the month. Ryan Wang is possibly around, I don't know. He's working his way through a second paper now and getting ready to go to his Viva fairly shortly, so he might be a bit busy. And then we have your student. Henrik, do you want to talk about your student?
Yeah.
We may see her pop in later.
Yeah, Paola Taranto. She's in here in the room, but she's hiding on the edge. That's
good.
Yeah. She's working on Juno data, looking at Jupiter, so using the spacecraft data rather than data taken by telescopes on the ground. So yeah, it's a big team, but also very niche, I imagine.
So what we're going to be looking at today, what we're talking about in our observations, is the top of the atmosphere of Jupiter. So it's this layer, the boundary layer between the dense atmosphere underneath and the vacuum of space surrounding it. And it's very similar in many ways to that layer Earth. So at Earth, we know about the aurora borealis and australis, the northern lights, and those are produced as a result of magnetic field interactions surrounding the planet. So the Earth has a magnetic field, the sun has a solar wind that carries magnetic field with it, and when they hit, they interact and cause all of these interesting dynamics that produce the aurora Earth. And it's in that kind of top most atmospheric layer. And that's what we're all interested in, understanding that layer. There's a couple of reasons why that layer is really interesting and important. From a pragmatic sense, it's really important to understand that layer because we all use technology that includes things like satellite and radio communications. All of those technologies are based around either the ionosphere or what happens above the ionosphere in the space surrounding the Earth. If there is a particularly large solar storm, for instance, that can cause all sorts of disruption to satellites. And so understanding how interactions happen around the Earth is really important in order to protect radio communications, satellite communications, GPS, and all those kinds of things. And although we're looking at a different planet, and so you might say, well, that doesn't have an awful lot to do with something like a satellite orbiting the Earth, understanding the underlying physics of what is happening is really important. And what we actually have found is that Jupiter is significantly different to the Earth in what is dominant. So the things that are Earth are governing the main system are different from Jupiter, but they share all of these different inputs and outputs. And in fact, sometimes in the extreme cases, Earth starts shifting in that balance. So when you have a major storm, different aspects of the interaction can become more important. And so by looking at a planet like Jupiter, you have a way of monitoring and understanding effects that you just normally don't see at Earth. So it's a really good way of understanding and relating what happens at Earth more generally and getting an understanding for that. So that's the sort of pragmatic reason why this is interesting and important, because it gives us more information about the Earth interaction. But the more sort of blue skies interesting reason why what we do is really important is that an atmosphere on a planet is mostly contained in the lower layers, but how you lose atmosphere from a planet is through escape off of the top. So even though the layer that we're looking at is very low density, over time, if a planet is to lose its atmosphere, it will be through the layer that we're looking at. That's the only way you can get stuff to stream out into space, is by having it move through the layer that we are looking at, because that's the very top of the atmosphere. And so if we want to understand the evolution of planetary atmospheres over time, not only in our solar system, but on all the exoplanets that we observe, it's really essential to understand this layer. And that's really the fundamental argument that won us time on James Webb. The ability to use observations and understand what is happening in the top of the atmosphere allows you to understand how molecules are escaping from the top of the atmosphere, and then ultimately pull in details of what's going on. So the question I've had is, are there any images to describe this layer? Well, it's difficult, and profoundly boring images are freely available. Lots of ways to show the layer that we're talking about in a really sort of dull way. But let's see if we can find that James Webb image. Pull this image up.
I have a slide of it if you want to show it.
Well, I will just share my screen, and hopefully we can see really the image that kind of governed our thinking on what we wanted to do. So what you can see here is this utterly mind-numbingly good picture of Jupiter taken by James Webb in the very early stages of observing. And the reason James Webb was interested in looking at Jupiter not only is because it's pretty, you know, we're all susceptible to wanting to look at pretty things, but also because it's incredibly bright and it's surrounded by really dark, faint objects. So some of the moons of Jupiter are incredibly faint or impossible to observe from the Earth's surface even. And one of the things that were legitimate concerns at James Webb early on was how well it could cope with scattered light. And so Jupiter itself is incredibly bright, and then it's got incredibly weak objects really nearby. So it's the perfect target to test whether your telescope can deal with scattered light. And it turns out James Webb can do that incredibly well. There is a matching image for this that also shows the rings off the edge. So you're able to image the rings of Jupiter, which, well, I think generally is almost impossible from the ground, at the same time as taking this kind of amazing data on the planet itself. And you can see the great red spot, the famous great red spot here, is white because this is an infrared image. And so the brightnesses that you're seeing here are imposed colors just to try and highlight different features. And the great red spot is a giant weather system that bulges out from the surrounding atmosphere. And so you see reflective material at its core, because it's so much higher than everything else. That material reflects much better. And you see a band across the equator of the planet, this white band that similarly is higher up. So you've got all these fantastic belts and rivulets and storms and wave activity and everything like that. All of this is happening very deep in the atmosphere compared to what we're looking at. But what you can see in this image is at the top and the bottom, there's a faint red glow. And what is harder to see in this particular image, but if you look very carefully, you can see a glow around the edge of the planet. And in some of the other images, this was more clear, especially when you use the specific filter that we're interested in. And so there was a lot of discussion within the community about what we were seeing in this faint glow around the edge of the planet. Some people thought it might be hazes in the sort of stratosphere. which would be equivalent to maybe the ozone layer on Earth, where you've got fairly high up in the atmosphere haze-like materials that are sort of reflecting the sunlight. But Henrik and I immediately knew what this was because it was so familiar. It was clear that this was the aurora because I could actually tell what rotational phase the planet was in as soon as I saw this image, because we've looked at so many of these images in the infrared. So the aurora is very clearly at the top of the bottom. It's actually at a similar CML to what we have right now. If we were to be able to get onto Jupiter right now, it would probably look an awful lot like this. And then this glow, this halo around the edge is a combination of a few different things, but it's all the upper atmosphere. So you have a combination of the glow of the ionosphere and the glow of just hot gas from the neutral atmosphere. And this really excited the broader atmosphere community. They were really thrilled and interested in what this was showing. And for me, it really highlighted that actually there's some really interesting stuff that we could do. So this is the imager, and the imager has this incredibly wide field of view. But in order to do really powerful science, what you want to do is, instead of having a filter that looks at a wide range of wavelengths, you want to split the light up into all its component parts. And that will let you look at different individual chemical species all at the same time. And in order to do that, you have to use a spectrograph, either a long slit, which we'll see today as we get onto Jupiter, where we look at Jupiter and put a single narrow slit. But the instrument on James Webb that we'll be using is a sort of nested set of those slits. So it becomes a box, but that box is relatively small. It's slightly smaller than the Great Red Spot. So when we look with James Webb today, we'll be looking at a box that's smaller than the Great Red Spot. So we can't see the whole planet at once, but what we will do is we will move around the planet. And that will let us look at what we're doing. And it's this thin layer above the planet that we're really interested in. And why are we interested in that? Generally, I think I've covered, but why are we interested in that today? Why is today important? Well, there's a spacecraft at Jupiter that a lot of you will have heard of, which is the Juno spacecraft, which is orbiting in a polar orbit around the planet. And it's actually really changed our understanding of Jupiter so profoundly, it's difficult to kind of detail all of the ways that we've changed what we understand. But most of that is sort of measurements of the fields above the planet as they go in, and images of the auroral region. But what we really want to know is what the ionosphere looks like in detail through this layer. And the only really powerful way you can do that with a spacecraft is to basically do what is called an occultation. You look at the Earth and you look at a signal between the Earth and the spacecraft in the radio. So you have a radio connection between a really large dish on Earth and the satellite, and you have a radio communication between the two. And then you can imagine that out in space, you would see a perfect source. You'd just be able to communicate quite easily. And then, of course, if you're fully behind the planet, you won't see Earth at all, and you'll see no signal. And then you can move between the two. Lucinda is telling me that there's an animation, which I should probably show. Do you have that at hand, Lucinda? That would be useful.
Okay, I'll bring it up in a moment.
And so the magic moment is the step between being out in space and being behind the planet, because you start moving through the atmosphere and your signal starts getting weaker and weaker as a result of being occulted by the planet's atmosphere. Okay, so this is the observation that we're going to take. I think he had an observation where a measurement where he looks at the, is that right? I don't know if I've got that one.
Those are the two I have. Did you?
Let's see. Well, I'll look for that later. But the important thing is that as Juno moves between that space and behind the planet, the radio signal will move through the ionosphere of Jupiter. And we know from Earth that the ionosphere bounces radio signals. That's actually how we communicate with radio waves. Radio works over long distances because the signal hits the atmosphere, the ionosphere, and bounces back down to us, and can bounce multiple times in the Earth's atmosphere, trapped basically by the ionosphere. And so as Juno moves through that region, it will cut out in a really interesting way. And we've done these kinds of measurements before with Cassini and with Galileo, past observations where we see that cutout. And it allows us to measure in detail what the electron density, how ionized that bit of the atmosphere is in a sort of a vertical profile. And when you do that for Earth, or you do that for Mars or Venus, you produce exactly what you would expect, a sort of ionospheric layer that becomes more dense and then less dense as you go through that ionosphere. But at all the gas giants, something really weird happens, which is that you sort of have that sort of spike, but it's filled with weird wobbles that we don't really understand. So Juno will be starting an occultation in an hour or two from now. It will be communicating with Earth, and they will measure that radio signal cutting out. But unlike normal, where we have this weird signal that we don't understand and no context for it, today will be unique in that we will have James Webb observations of exactly the same position at the same time. So we will be looking from James Webb at Jupiter at exactly the location where Juno will be disappearing. And so we'll have two separate measures of the ionosphere at the same time. And if the weather holds at the top of the mountain, we will also have Keck observations of that region as well, so from Earth. So we will have three different views, one from Juno behind the planet, one from James Webb out in space, and one from Earth looking up at the planet. And then very soon after, we will get IOTF as well. So we'll have this sort of multi-view of the ionosphere that's never been done before for any planet other than Earth, I think. Yeah. It's fairly unique.
Very exciting. I can't believe today's the actual day. It's been planning this for so long. We submitted a proposal, James Webb proposal, in January?
Right.
Working on it since.
Yeah.
It's can't believe it's about to happen. Let's cross our fingers. I keep refreshing the it will tell us when the James Webb observations are going to start. So that's another 25 minutes from
exciting.
now.
Okay, another 25 minutes. Okay, definitely highlight that. That would be great. Thanks, Henrik. Thank you.
Henrik's counting down the seconds.
Yeah, I really am. Yeah, very cool. But you showed, I can show the, where is it? I can share my screen. To just show you, you saw an animation of these. So this is, they produced these charts to confirm that the observations are going to do what you expect them to do. So the little green box on the limb, so Tom mentioned this, the imager on James Webb has a massive field of view, but this instrument we're using is called NIRSpec, which has a tiny field of view. So see that little green box right on the limb of the planet, on the top sort of top left part of the planet. That's the field of view of this instrument. So it's really tiny, and to get coverage along the limb, along the whole limb of the planet, basically go around 360 degrees, we have to step this tiny box in very small steps around the planet. And that takes a long time. So the whole thing is going to take about 24 hours. We're going to start in over 25 minutes and we'll end at about 2 p.m. tomorrow to get all these observations. So when will we actually see these observations? Well, James Webb talks to Earth every 6 hours or so. So it depends when that communication window falls, and it'll send the data back. It'll end up on some server, some James Webb server, and then we can download it from that. So certainly by the end of today, we should have this data in hand, which is kind of cool, thinking it was just taken in space by the James Webb Space Telescope. So there's a lot of these plots, but this is the first one. I'm going to move, actually, we're going to move clockwise around the planet. So these plots are useful because when you design these observations, it's just numbers in a spreadsheet. It's nice to have a visual confirmation that what you're putting into the spreadsheet is actually correct. There's also other green boxes you can see here. There's two really big green boxes. That's known as the micro shutter array, and they use that to look at galaxies and things like that. If you have a big field of lots of galaxies, this micro shutter array, you can basically open little flaps, little doors in this array. It only lets light in at certain positions. The smaller boxes are what's known as fixed slits. So to the right of the setting we're using, they're always open. So we're hoping to get some data from those slits as well. Yeah, can't wait. 18 minutes now.
That's great.
Now I wish we had a countdown clock or something.
I know. Don't worry, Henrik will.
I'll let you know.
He'll let us know.
So it's worth talking, I think, about just how special it is to observe on James Webb. It's an incredible spacecraft, an insanely powerful telescope. I was looking at our program, and although we have 22 hours of observing, nearly all of that is moving the telescope around and getting it positioned up. So we only end up with, I think, just under 2 hours of observing time on the planet, taking light into the telescope and measuring Jupiter, which sounds very inefficient, but it has to be built that way in order to ensure that you look at the thing that you're looking at. So you might think that only 2 hours on an object is pretty low. We've got 6 hours to look at Jupiter with Keck tonight, and we've been looking at Jupiter for 2 hours every other night for the last month on IOTF. But it's 100 times more sensitive than Keck, and that's not the telescope itself being amazing so much as the fact that it's in space. If you could launch Keck into space, it would be even more profoundly amazing, but that's impractical. Being able to get a telescope of this power into an incredibly difficult radiation environment, and you've got the sun on one side heating everything up. You have to make sure that everything is cooled properly, but you are able to be above the Earth's atmosphere is such a insane step forward. So when you actually work out the amount of time, if you scale it in the number of hours to Keck, it's a couple of weeks of taking over Keck, basically, the observations that we have tonight on James Webb. It's as if Keck gave us 2 whole weeks by ourselves, which will never happen. Keck will never give you that much time to do a program like this. For instance, we have 3 or 4 half nights for the upcoming program that we have that we're going to take the first observations for tonight. So even if this was an object like a galaxy in the sky that didn't vary very much with time, that would be super important because it would give us so much more light. But Jupiter is this broiling bubble of activity where things are changing constantly. And so being able to observe it in a short period of time and pull up that much light is profoundly different to anything we've done before. We have very fortunately had a few James Webb observations so far. None of them were won through sort of the competitive bidding process that this went through. They were part of the early release science and the guarantee type observations that were some of the most important, most profound results. So the wider community, the astronomical community, knew that there was certain things that they just had to do straight away. And some of the observations that we've been getting already from different planets have been included in that. And so one of the things that Henrik has been working on is observations of the Great Red Spot. And we've had observations of the Southern Aurora that have given us a hint of what we're going to see. And every single observation so far has confused us because it's so profoundly better than anything we've seen before. So we're still trying to really understand what we're seeing in any of the observations that James Webb has taken of any of the planets so far. And that's what happens when you have this profound advance in our understanding.
Just have a quick question, since you say that you guys get to move the telescope, which is amazing, and that it's in space. And I was wondering if you have an idea of like how long does it take? What's the delay time for when you make a change or a turn, and then it turns.
Henrik, do you want to talk about that?
Yeah, I guess the observations, at each step on the limb, the observation is not very long, maybe a few minutes. And in total, we're allocated half an hour for that observation. So it takes about 25 minutes between each frame to move the telescope slightly. We'll see how those predicted pannings turn out. Predicted timings, I should say, pan out in reality. We'll see that when the data comes out. But we're not moving the telescope very far. We're moving it along the limb of Jupiter, but Jupiter itself is also moving on the night sky. All the planets move relative to the stars, and so the telescope is tracking Jupiter and tracking these points on the limb of the planet. So technologically, it's impressive, I would say, to be able to do this. And there's limits to how fast the telescopes can move as well. So we can certainly observe all the planets, but if you're observing, say, a comet that's really nearby, the telescope might not be able to track that comet. So it has a built-in speed limit, effectively. And they did try that, didn't they? They had it was the, what was that impact test they did last year when they slammed a spacecraft into an asteroid moon, and that was moving incredibly fast, 3 times faster than the actual maximum allowed speed, but it actually worked. And so, like anything with this telescope, it turns out it's a lot better. DART, yes, thank you, Lucinda, the DART mission. So every single instrument on the telescope is overperforming expectations. So they're all much more sensitive than they thought they were when we tested them on the ground. And that's because it's really difficult to test how things behave in this is extremely cold environment they're in. So the telescope and the instruments are minus 240 degrees Celsius, so extremely cold. And this temperature allows us to get these exquisite images and data of the giant planets and the rest of the universe as well.
It's worth pointing out that, you can see Henrik has a couple of laptops and looks not too panicked with, 20 minutes left to go before he starts observing on James Webb. The reason why he is somewhat calm is because he has spent months already planning the observations. So because of the way the telescope works, we don't control it at all from the in situ, in time, unlike Keck, where we're waiting to get on and we have full control over the telescope. We can move it and change our plan however we want during the night if we see something interesting. You just can't do that with a space telescope. And so the full program for the next day or two for James Webb is already fully set. They know exactly what they're going to observe, when they're going to observe it. Every individual program that makes up the current day or two of observations has individually said specifically what they want the telescope to do, and then people who work more directly on the telescope have stitched those together into an observing plan. And that way you can continuously observe with James Webb without having any downtime or people not knowing how to do stuff. So it's quite unusual for us because we're used to doing ground-based observations where we have much more control about what we're doing. And with planetary observations, that's often very useful because you can think about on the fly what you should do. I'm actually very glad that we don't have to do that with James Webb, because the opportunity to get distracted is too great, right? You could easily see something really interesting and want to do that instead. It's much nicer to know that this is what we've said we want, this is what we're going to get. And people who are much more used to the telescope and we are going to do that on our behalf in order to produce the amazing data. And they've been working with us, making sure they understand what we want over the period of time running up to this of several months now. Basically, we were contacted almost as soon as we were informed that we had the observations, which was, I think, June, July, and we've been working with them since then. So Henrik doesn't have a lot to do today in terms of James Webb because he's worked so diligently and hard for months beforehand, and will be working after we get the data back too. So it's actually, it's an inverse Santa Claus, right? It's the one day of rest you have between the year of work.
Yeah.
Well, you might be busy over the weekend processing some data.
Yes.
I've heard. But I just wanted to chime in really quick just to remind our attendees that Dr. Mellon will be talking about JWST in about 30 minutes. So he'll give us a nice presentation on what JWST is and what it does, and hopefully talk a little bit about what the work that he's doing as well. There's a question that's come in kind of part of moving JWST, and Steve asked a really good question, is what happens while JWST is just waiting for instructions on that dead time, and is it still observing at things as it's waiting? Or do you guys?
It's always observing. So the program is uploaded onto the spacecraft and it does them sort of autonomously. And so whilst it's observing, it can also speak to the ground at the same time to download the data it has on board. I think the storage is something like 65 gigabytes on the spacecraft. So you have to keep emptying that memory down to Earth so you can refill it with new data. So it speaks to the Earth every 6 hours and it's always doing stuff. I only know one break in the observing, and that was something was triggered with an instrument. Nothing to worry about, but with these things, it's always safety first. Always err on the side of caution. Something looks a bit weird, check it out. And we want this telescope to last another 2 decades. So, yeah. The initial length of the mission was nominally 5 years. It's built to last 5 years. And the real limiting factor of how long this telescope can be in space is the amount of fuel it has. And so the amount of fuel you have once you go to your position in space, which is this Lagrange point 2 point, but 3 times further away than our moon, it all depends on the launch. How good is the launch? How much fuel do you have to spend to correct your course before you enter your final orbit? And so I'll show a video of the launch later, but it was absolutely perfect. You couldn't ask for a better launch. So a lot of fuel was saved just by the fact that the launch was so great. No much need for course corrections. And so the predicted lifetime now is 20 years, which is amazing. I'm looking forward to another 20 years. Of, we have had 1 year so far, and what we've had is, breathtaking. Right? So another 20 years of that. Yes, please.
Yeah, really looking forward to seeing day 2 as well of the processed imagery. Just get a few questions now. I don't know if you guys are interested in taking a few questions. Great. So one is from Robert, who asks, is your team concerned about the Deep Space Network communications capacity crunch? I'm not familiar with this. I don't know if you are. Particularly that time allocated to JWST could be restricted. Have you heard anything about that?
Not specifically, no, but I mean, I've certainly heard about that more generally, the limitations on data from deeper space is really problematic sometimes, getting data downloaded from space missions. I've not heard about it in context of James Webb specifically, but I mean, I could see it being problematic if it did become an issue. Yeah. I would imagine it is not a huge concern for James Webb, just because James Webb is relatively close to Earth. And so I would think the power that you would need to transmit is probably a lot lower. You can imagine, basically, as you move further away, a signal decreases with distance because, you know, the beam size is narrower and narrower, and it's harder and harder to get measurements. So if you're at Neptune trying to transmit using a little dish back to Earth, it's incredibly difficult to do. But especially for now, at least, I would imagine James Webb is a huge priority. So for now, at least, I don't think there will be an issue. And I would imagine too that because it's continuous, if it does start becoming problematic, they may invest in better infrastructure. But I don't know the details. So,
Was that Henrik? Did you have anything to add to that?
Sorry, just looking if something's happened yet. No.
Yeah, no, you look something interesting. See, I knew I wanted to see your screen.
Yeah, I mean the it's amazing. So this telescope sits 3 times farther away than our moon. It has a little dish on it. It's built by a company called Beyond Gravity. It has it built in Gothenburg in Sweden. So hey, but I can transmit 3 megabytes a second down back to Earth. So that's pretty impressive given you're in deep space. So I guess it's to work out. Want to download 65 gigabytes, I want us to take it 3 megabytes a second. That's a maths for the home viewer.
Great, thank you. And I know, Rosie, you're going to talk about the ionosphere later. There's a question maybe that might be for you here from Nigel regarding Jupiter aurora. What molecular species are ionized and given rise to the aurorae? So you're probably going to talk more about that, but do you want to?
Yeah, I'll definitely talk more about that later. But so at the Earth, we have lots of nitrogen, as you know, and oxygen. So those are the molecules that are mainly getting ionized at the Earth to make our northern and southern lights here. But at Jupiter, there is loads of hydrogen. Like heaps of it. So that's mainly what's getting ionized at Jupiter and making the aurora there. So I really like to think you can just imagine exoplanets, like what would be the molecule there and what would the aurora look like there. I always think that's really exciting. But yeah, at Jupiter, the main molecules that are being ionized to make the aurora are hydrogen. So when we say ionized, that's a neutral molecule, like molecular hydrogen, and then it's like excited, it's given some energy, and then it makes a charge. It makes it into a charged molecule, which is known as an ion as well.
Thank you. And Henrik, Nigel chimes in that 3 megabytes per second is about the same rate as terrestrial standard definition television.
There you go. Excellent.
Okay, let's see, what else do we have here? Professor Stallard, I'm glad you came back. There's a question here for you. Asking if you could elaborate more on the occultation results, especially between the Juno X-band and Ka band downlink frequencies and the state of the Jovian ionosphere ionization. That's quite a lot.
Actually. That is a lot. And some of it is almost as confusing to me as to you.
Casey, I think you're going to have to wait the whole 6 hours to get the answer to you.
What I would say is, I always find the specifics of radio transmission very confusing. But fortunately, we have people. Sorry, we have people who are very good at that kind of specific detail, and it's a well-known and understood science of, to me, somewhat magically extracting details about what the ionosphere is doing from a radio signal, being attenuated by occulting behind the ionosphere. As I said, that one of the problems we have with Jupiter is that it's very strange. The gas giants are very strange, and they don't act in the way that we would expect a planet to do. And so, you know, it's natural, I think, to be concerned that things aren't working, right? But the technology itself is so really well understood, and you get incredible measurements from Earth and from Mars. So it's clear that whatever magic juice they put in to get out these detailed maps of, and basically what you can do is measure how many electrons there are at different layers of the ionosphere, and they sort of work their way down, peeling the ionosphere like an onion. So you can imagine that the onion has multiple layers. When you first start slicing into the ionosphere, you only see that outermost layer, and then you can then account for that as you slide in deeper. You're seeing that top layer and the second layer of the onion, and as you go deeper and deeper, you've got more and more layers, all of which are attenuating what you're seeing. And so by unpeeling that onion carefully with the data, you're able to reveal how much attenuation happened in each of those layers, and reconstruct that through the model to understand what that means for the ionospheric density itself. So specifically how many electrons are in that layer of the atmosphere. So you get this count called total electron count, which is just how many electrons in total are there in each of the layers of the ionosphere, which is a really important number because it tells you an awful lot about what the ionospheric conditions are like. And it's something that we understand fairly poorly for the giant planets, partly because what you would expect, what theory tells us, that a classic Chapman ionosphere is that, you know, something, let's say sunlight, at the equator it's always just sunlight is hitting the atmosphere, and all of that EUV light is hitting the ionosphere and atmosphere and turning neutral material into ionized material. So for Jupiter, it hits molecular hydrogen, which is 2 protons and 2 electrons all stuck together into a nice solid H2 molecule, and you ping it with something really energetic and it pings off one of those electrons. So you have a free floating electron, E-, and you have H2 plus, because it's the hydrogen with a H, with an electron missing. So now it's a positive ion. And so they're able to measure that electron moving around, added up over the whole thing. What we're looking at is H3 plus, basically because H2 plus is very reactive. It hits another hydrogen and it steals a proton and an electron. And so it becomes 2 electrons and 3 protons. And that produces this thing called H3 plus, which we are all team H3 plus. We love that molecule so much because it allows us to do all the science that we're interested in. So there's different species of ions and electrons in the top of the atmosphere. And what you would imagine is, you know, all that energetic material swamping the top of the atmosphere, and you would have a very nice, clean, increasing amount of ions up to a certain layer where it's the strongest amount. And then as you go deeper, it sort of decays away again, because partly because the light isn't able to penetrate deeper because it's being absorbed, and partly because you're getting so dense in your atmosphere that it's just able to recombine all of that ion material immediately anyway. And so, you know, if you made some ions in the atmosphere down here on the surface of the Earth, you would immediately lose them again, because the neutral atmosphere would just jostle them into non-existence immediately. And the layer that we look at is this sort of magical layer between the two, where it's just right for ions to exist. And the classic Chapman model of that, the classic idea of that is that, you know, you have a nice gentle increase and then a gentle decrease as you move in latitude, which you see at the terrestrial planets. We don't see that. So that's one problem that is an intrinsic problem that we need to solve. And one of the things we're really interested in trying to solve with these observations. But the other problem is that assumes that you're moving behind the planet nice and cleanly. So you move from the top to behind the planet in a nice straight line. And what Juno is doing is very different to that. In classical observations, it's very far away and it just sort of sees the Earth disappear as it sets behind the planet. But Juno is really designed to look at the planet really close to. So actually it's much closer to the planet than it would normally be for this kind of observation. So there were worries, could we even get the information out? But fortunately, we've already had one orbit from Juno doing this new style of very close to measurement, which we couldn't look at with James Webb because James Webb was not in the right place in the sky to be able to look at it. And so we know that that's very encouraging because that does show that that method is now worth working with the really close to measurements of Juno. So there's a whole array of problems and snags that potentially get in the way of us doing what we want to do. And somehow we're still here. Somehow we're still taking this data. I don't really understand how this has happened.
It takes an incredible team. And you had spoken earlier on when you were talking about people, where they are around the world helping this. And I wonder if you could just give us a number of how many people actually are helping out today.
Okay, let's see. So we've got 2 people in Japan, Katie and James, who are going to be taking the lead on the IRTF observations because it's Katie's program and we've been training her up to do that. We have Luke and his students out in Boston. So depending on who is around, that will be Kate and Khalid, so that's 3. And then in terms of James Webb, I mean, profoundly do not know how many people are helping us with that.
Sure.
Henrik is leading that. We know of at least 2 or 3 people we've directly worked with in order to get those observations in place, but there could be potentially other people involved in that. We have the telescope operator on IRTF, the telescope operator on Keck, the support astronomer on Keck will be directly involved. We have people involved in Juno, so directly that would be Paul Withers is leading the observation in terms of the program design and everything like that. The Keck observations come specifically from a program from another colleague of ours at Boston. And then we have the team that built the James Webb proposal, which is, in addition to me and Henrik and the people we've already talked about, at least 5 other people. So there's Imke de Pato out in Caltech. We've got Riccardo in Italy. We've got, a lot of other people there.
That's over 20 people already that
Yeah.
we talked about. So that's quite.
So it's rare enough that you get a team together that is able to get observations with James Webb individually, but then there's the whole of the Juno side, which equally has huge numbers of collaborators to produce that Juno observation by itself in isolation. And then being able to get time on Keck takes people, and IRTF is a whole separate program as well. And there's overlap in there with people.
So can I ask that? Did you
Yes.
guys plan to do 2 different observations on the same day?
Yeah, we did. So
That's
it's incredibly hard to do this because if you want observations on Keck and IRTF won't give you any benefit of the doubt for Keck because Keck might not give you the time, and Keck won't give you any of the benefit of the doubt for IRTF because they won't give you the time. And similarly, if we wanted to do Keck and James Webb at the same time, neither would give you the allowance of the other telescope. And in fact, it would be seen generally as a detriment, because what if you don't get time on Keck? Well, we can't do that. So it's a very hard thing to resolve. And we had huge issues in the past with trying to do ground-based observations with, say, Hubble observations. There are some routes that you can go through to fix that. The pinpoint glue that has stuck all of this together is that Juno will definitely be taking data. That's been programmed in for a very long time. The fact that it was planning to do these Juno orbits has been known at least to within a day or two for more than a year now. And so the fact that there was this one thing that we could write proposals aiming towards for all these different telescopes has allowed us to congregate on the same observation, and mission support and being able to support Juno in that way is really important. So we would have loved to have done that kind of mission support for James Webb. I mean, in fact, it's more important for James Webb than Juno in some ways, because we want to be able to support this amazing observation that we've gotten. But doing that would have been really hard, because by the time we found out that we had time on Juno, it was on James Webb, it was too late to propose on any of these other telescopes. So the intention wasn't to support James Webb, it was always to support Juno. But now, for me at least, James Webb has sort of taken over as the priority, because Imke Tabato always famously argues that we're not supporting Juno, Juno's supporting James Webb. And I do like that point of view. So
And
a little bit controversial, but ultimately, the more different views you have, the better the science that you can get out. And so we're really lucky that Juno was doing this unique new thing that allowed us to write really exciting sounding proposals for lots of different telescopes, and we're able to engage with the community. I'm not sure if people are aware of how you get to do these observations, but it's we can talk about it in more detail later. But basically, it's a very long process of having to convince other scientists that your science is more important and interesting than a whole bunch of other scientists who have equally profound sounding science. You just have to sound more profound than they are. And
that's a whole nother topic in itself that'd be kind of interesting to discuss, actually.
Yeah.
But maybe Henrik can tell us more when he's going to talk about JWST. But as a JWST fellow, Henrik, what else do you have to add? Anything to that?
Well, just to say that right now, James Webb should be pointing at Jupiter. We should have started at 8 past to get data. I've not seen a confirmation yet, but it should be happening right now. It is, too exciting.
Perfect timing to bring you in then. So did you have your countdown clock? Just kidding. You're doing enough already.
But this, I can show you this website. So it'll tell us, I don't know if there's a delay or something else afoot, but this is what it looks like. Oh, you can see it. So this is our program, just the Space Telescope Science Institute. This is our program 3665. It'll tell us exactly when each observation is going to happen. So right now it's still scheduled. At some point that will change to ongoing, and then when it's downloaded from the spacecraft, it will say archived. So that's what we're waiting for, just a confirmation this is all going to plan. So we'll keep an eye on this page, basically.
Each one of those is, as you can see, is half an hour, 45 minutes.
Yeah. Where
the actual time that we are taking light through the telescope is actually much shorter than that. But yeah. If you want to pull that movie up, listen.
Okay. Yes, I have it here somewhere. Just curious, that's a static spreadsheet that you just showed us, Henrik? That's not going to update or change or anything when it is.
It will update.
Oh, it will. What will it say? How will you know?
It's going to change the status of the observations. I think it's going to say ongoing or something like that.
Okay, cool.
Collecting, that's what it said, collecting. It's going to be collecting the data, and then we'll send the data back, and then it will be archived.
Okay, I think this is what you were, this is,
Yeah, this is the observational set, and it's basically a clock moving all the way around the planet. And the first observation is the one that's going to be happening right now.
Yeah.
The last one will be happening in about 24 hours from now.
Yeah.
Maybe a bit less. It takes that long to kind of circumvent the entire disk of the planet. But we'll be able to get inside that little green box is where we will see. And we will see a relatively small bit of the planet in insane levels of detail.
wow.
Just not even the sort of pixel scale detail, which is probably not that different to what we could get with Earth, especially with adaptive optics. But it's the depth of the light bucket, effectively, because when we're on Earth, we have to look through Earth's atmosphere. We're in the infrared. Greenhouse gases absorb infrared light, and so we're looking through a huge filter that blocks most of the light that we see on Earth. So we can't really see very much through that filter. We've got a little window that really kind of, we're looking through bits that are more transparent, but the level of absorption is just really extreme on Earth. And so even though the dish itself collects about I would say about a quarter of the light of Keck. I think that's right. Just doing maths in my head. Yeah, it's about a quarter of the light of Keck, for instance. Keck, or most of what Keck sees is Earth. And so it's 100 times more light from Jupiter, despite having a dish that collects a quarter of the light. So it's 400 times more sensitive than Keck, one of the best telescopes in the world. It is more like 1,000 times better than some of the other really profoundly good telescopes. So we're looking at a little bit of the planet with eyes that can see things in the dark vastly better. I don't know if this is true, but it's one of those comparisons that really sticks in your mind, which is that it would be able to observe a bumblebee on the moon. It's kind of insane, and you get told these things, and then you start seeing the results come in, and I think we share a kind of beholdenness that everyone watching this stream have to some of the amazing results from other fields. Some of these amazing observations of galaxies at distance, and some of the ways that our understanding of the universe is profoundly changing as a result of these observations. But it's a very different experience to seeing observations from something that you've looked at for years. Even though to someone outside of the field, it might not look that different. It's jaw-dropping how different what we can see with James Webb is from anything else. And it's sort of, we as a community, our little tight-knit community have had several days in the last year where we've just been completely lost for words. None of us have known how to express even what we're looking at with the data that we've been getting back. It's not exciting. These observations coming up are not exciting, really. They're nerve-wracking, because it's going to be really difficult to understand what we're going to see, I think. And it'll take time to really get to the guts of it. So, on Monday, all things going well, we will have things to show. It'll take a little bit of time to download the data, a little bit of time for Henrik to be able to squeeze it into something that we can look at. That's not the difficult bit, and we'll show you what we can see and try and explain what we're looking at. But it's unlikely we will not see something that we just don't understand in this data.
Yeah. And that's the fun part, right?
That is the fun part. Yeah.
Any update on the on JWST?
No, not yet. But Keck should be starting observing now. Am I right?
I feel like they should. I don't know if there's anything going on yet, but the telescope is moving right now.
I'm not sure if you did this earlier, Tom, but did you share your screens yet? And have you?
I did share it briefly. I have lost one of the 4 windows, so I'm going to set that up again.
And then
One of the joys of remote observing is things regularly fail.
so, yeah, and that's the fun part, I think. But when you do that at some point, and I apologize, my cat Kepler is in the room and he's dying for a cuddle right now. When you get your screen up, it'd be good to talk about different panels for those who might not be familiar with all those things which you see all the time. I just wanted to give you a heads up, a reminder about that.
That's good.
And we've got about 2 minutes before we get started with Dr. Mellon, but I'll leave it up to you when to start. You're all free to go.
Okay. So I have pulled up the panels for Keck. No obvious observations just yet, but they should be starting soon. I could share that, or we could just have Henrik start talking about James Webb for now, and we can come back to Keck. I'm sure in half an hour there should be something interesting happening, unless something bad is happening. We can find out whether something bad is happening too, quite easily. Henrik, do you want to take over for now?
You're on mute, Henrik.
Rookie error. Oh. Right. That's my first slide. There. Okay. You can see that? You can hear me?
Yes.
Brilliant. Okay. So I just want to give a little introduction to the James Webb Space Telescope. And this is an artist's impression of what the telescope looks like in space. Obviously, in reality, you can't see the mirror because it's completely shaded. You can see there's some reflections in the mirror, but that's about it. So I want to start really at the very, very beginning and ask the question, why do we even want to put telescopes in space? It's expensive, it's really complicated. And so why do we want to do it? So here's a picture of the famous Royal Greenwich Observatory, which sits right on the 0 longitude line. Lots of history there as well. I think it was built essentially to try and establish clocks that work on seas, so seafarers could determine their position, latitude and longitude. You can see a picture of the moon there that's taken with a telescope on the ground. I'm not sure it's from Greenwich or not, but you can see it's blurry. And that's a result of our atmosphere moving around, and light moves, gets scattered with our atmosphere, and so things move about. And this is the problem with the atmosphere. It's lots of turbulence and it distorts our images. So if you're at the Greenwich Observatory, you get about 60 clear nights a year. So 300 odd are cloudy. So it's not the best place to do astronomy in the world. So what you can do, you can move up in altitude. And this is where we are observing from tonight. And this is the Keck 2 telescope right to the left there. And this is a number of observatories sit up here at an altitude of 4.2 kilometers above sea level. And then at that altitude, you're above most of these weather layers, and you're not affected by turbulence and things like that as much. So this is an even better place to do astronomy than, say, Greenwich. So on the summit of Mauna Kea, we have about 300 clear nights a year, which is a marked improvement compared to Greenwich. I took this picture, by the way. You can see it's taken just at dawn, and you can see the shadow of the mountain as the sun rises behind you. It's a beautiful place, and even though it's Hawaii, you can see there's lots of snow. It's extremely cold on the summit, around sort of 2-3 degrees Celsius. and can get freezing as well, hence the snow. You've all heard, of course, about the Hubble Space Telescope. This is the next step, right? You're on top of a mountain. The next thing to do is to void the atmosphere completely. And so you send a spacecraft. In case of Hubble, it actually orbits the Earth. It was launched in 1990, and it was a bit of a disaster when it first launched. It turns out that the images that the spacecraft sent back were, well, they were terrible, and they were a lot worse than, well, they lacked the fidelity we expected them to have, essentially. You weren't doing much better than using telescopes on the ground. And it even made the front page of the New York Times. It was generally seen as a massive embarrassment for NASA. You know, spend all this money making a telescope and it's out of focus. And it's not what you can do when you have a telescope in space, right? You know, fixing it is really difficult. And the reason why the Hubble Space Telescope was out of focus is because the mirror was ground wrong. So you ground the mirrors to a particular shape, depending on the type of telescope you have. So the mirror that was launched was made by the Perker-Elmer Corporation. And this mirror, it passed all the tests. So according to their tests, this mirror was in perfect shape. But it turns out, the investigation turns out that the tests themselves were faulty. So they had wrong assumptions in them. And so even though the mirror passed the test, the tests were actually asking the wrong questions. There was a backup mirror made by Kodak, seen on the right there, which is now in the Smithsonian, how do we say that, museum in Washington, DC. And that was the right shape. So they could have launched a perfect telescope without any issue had they used the other mirror. The Hubble Space Telescope is designed to be serviceable. So you can send the space shuttle up, visit it, take instrument out, put new instruments in, upgrade parts of the telescope. And in 1993, they actually fixed this focusing problem. And there's been 5 other missions since then, and that includes lots of instruments upgrades. And the last upgrade was in 2009. So no one's visited the observatory since then, because the space shuttle is no longer flying, and there's no vehicle that can go up there, grab the telescope, and exchange the parts, for example. So it's at this stage 33 years old. It's been in space for a long time, but it's still doing extraordinary science. But it's showing signs of aging. But when we think about the Hubble Space Telescope these days, we think of it as an extraordinarily successful mission. And some of the most iconic images we have of the universe today are taken by the Hubble Space Telescope. Here's just a few examples, including my favorite, Jupiter, of course. So even before the launch of the Hubble Space Telescope, people were thinking about the next step. What was that next telescope going to be after Hubble? And it was originally called the Next Generation Space Telescope. And this was back in 1989, so 1 year before the launch of JWST. And so it's been a project in the works for an extremely long time. And so that said, it's not been exactly plain sailing for the telescope whilst it's been on the ground. It's garnered some pretty bad headlines throughout the years. So it's had a number of delays, a number of cost overruns. In 2011, I should say, the US Congress actually threatened to close down the project altogether because nothing was on time. It was hugely delayed. The cost was ballooning rapidly. And so it was only when Barbara McCluskey, a US senator, stepped in and saved the mission that it continued to being built. And in her honor, now the archive on which we download the data from is called the Barbara McCluskey Archive, which is kind of nice. There was another incident in 2020. We're doing some testing to put the whole telescope inside a vacuum chamber. And it's an acoustic test. You're subjecting the telescope to a lot of noise, basically vibrations, to simulate the launch. You want to make sure that the telescope can survive the launch. And so they did this test you've got this big chamber, put the telescope in, do this acoustic test. They open back up the chamber, and at the bottom of it, there's a handful of screws and a handful of washers. So things are literally falling off the telescope as they're testing it. And this is not good, right? You don't want bits of screws, maybe important screws, falling off during launch. That was, of course, jeopardized the whole project. So a lot of bad headlines and a lot of comparisons to what Hubble went through when it was launched. Is this another failure for NASA? Well, it turns out, no, all this testing has paid off. We have a telescope that's extremely, it works really well, I should say. It's been working now for 1 year and no real issues. So this is what the telescope looks like. It's quite a flimsy telescope, has this big primary mirror, that's 6.5 meters, but it's a large telescope. It's a large telescope in space, so like 40 meters wide, 22 meters in the other dimension, 10 meters high. And so you can't stick this in a rocket without folding it up. And this is sort of the space origami that the whole mission went through. So there is a way of folding this structure up, which you can see on the left there. But you have to do that so it fits inside the nose cone of the rocket. So you can see an illustration on the top right there. This folded up structure sits inside the rocket. And then after launch, the trick is to unfold it to this shape you see on the left. Not trivial engineering at all. And this is part of why it's been such a complex project. So finally, we had launch on Christmas Day 2021, so about a year and a half ago. It was a very exciting day. So this is about 20 past 12 in the afternoon. It's kind of nice. It's Christmas Day, so you're allowed to have a drink at lunch just to steady your nerves. But everything went flawlessly. An absolutely beautiful launch, perfect launch. And about half an hour later, we got to see the observatory detach from the launch vehicle. And here it is moving into outer space. We're going to spend this time in this location 3 times further away than our moon. We're about to see the first of about 300 individual deployments, and that's the solar panel folding out. It's right here. And now the observatory has power. And so what happened after this is a sequence of unfolding events that took place to make the telescope the shape it needs to be. And here's an illustration showing that. So the solar panel went out, we had a communications antenna, we have the very large sun shields. So the way this telescope keeps cool is actually quite simple. It's like when you're on the beach and you're sitting underneath the parasol, you're a lot cooler than if you were in the sun. So it's a passive shading, effectively, that keeps the telescope cool. So this is a fabric that's being stretched out. It's aluminum-coated Kapton, I believe, so sort of a classic space blanket. And there's 5 of these layers shielding the telescope and shielding the instruments from the sun. So at the bottom of the spacecraft, the sun comes in, is about 85 degrees Celsius, which is like a hot cup of tea, basically. On the shade side, it's minus 240 degrees Celsius. So extremely, extremely cold. We're about to see the mirrors fold out now. And here we are. Everything went without a hitch, and the telescope was this shape in sort of early 2022. A truly extraordinary journey. Each step was carefully planned and carefully executed, and it actually worked, which is nice. So, like any large international mission, it has to be, any large space mission, it has to be an international collaboration. And the principal partners here is NASA, the American Space Agency, ESA, the European Space Agency, and the Canadian Space Agency. And here at Leicester, which is where I'm streaming from, we've been involved with a project for decades. There's 4 instruments on the spacecraft, and we built parts for one of those instruments. It's called Mirror. And here's on the right, you can see one of the engineers over at Goddard Space Flight Center with the instruments sticking it on the telescope. Just to compare just the sheer scale of Hubble and the JWST, on the left you can see the Hubble mirror, the faulty Hubble mirror. So that's 2.4 meters in diameter. It's a pretty large mirror. It's small by terrestrial standards. We'll be using a telescope today, the NASA RTF, which has a mirror of 3 meters in diameter, which is smaller than the Hubble mirror. But you compare that to the James Webb mirror seen on the right there, which is 6.5 meters in diameter. You can see those people admiring the mirror to scale there. There's 18 individual hexagonal elements, each measuring 1.3 meters. And it's all gold plated, not just to make it look pretty, but to make it really reflected in the infrared, which is the wavelengths the telescope is observing in. So one other difference between the James Webb Space Telescope and the Hubble Space Telescope is that JWST is going to do a lot of spectroscopy. What that means is you divide the infrared light into its constituent colors. And what's cool about that is that every atom and every molecule in the universe has its own unique fingerprint in this sort of color space. And so if you use Webb and you look at a planet, say, around another star, and just using this spectroscopy technique, you can determine what's in that planet's atmosphere. So if you see a planet with, say, nitrogen, maybe it's got some oxygen, and you go, hang on, that's just like the Earth. And what if you can see water? And then we can ask questions like, is this a place that could harbor life as we know it here on Earth? So it enables us to determine what remote objects are made out of, and are there places like the Earth out there? So here's a comparison between the Hubble Space Telescope and JWST of the pillars of creation. It's one of my absolute all-time favorite images. So on the left, you have the HST image, and this is a star-forming region. Within these dense pillars of gas, new stars are born, sort of like a stellar nursery, if you like. You can see the HST image is really dusty. There's not a lot of stars you can see. Well, you can see some stars, but nothing in comparison to the JWST image on the right. And that's one of the great features of the infrared. In the infrared, you can actually start to see through dust. So now you can see into where these stars are being born. And seeing through dust is generally good because there's lots of dust in the universe that enables you to see things that are further away or hidden in the visible or in the ultraviolets, like HST sees. This is a protoplanetary system. So imagine that this is what the solar system looked like 4.5 billion years ago. A large collapsing cloud of gas, and in the center, I don't know if you can see my mouse, but in the center there is a disk within which, at the center of which, a star is being formed. Fusion hasn't actually started yet, and so it's just glowing with heat, all this stuff collapsing. You can also imagine within this disk there's young planets being formed as well. It's a stunning image, as all of them really are. This is sort of what the telescope, one of the primary design drivers of the telescope, is to do pictures like this. So you stare at what you think is basically an empty bit of sky for a while, and with this extremely sensitive telescope, you can begin to see hundreds, if not thousands, of individual galaxies from the very distant universe. The very distant universe is also, of course, a very young universe just after the Big Bang. So one of the missions is to see what happened after the Big Bang. So what happened is the Big Bang went off, everything was really hot, the universe expanded really rapidly. As it expands, it cooled down. And at one point, it was filled with mostly hydrogen, but there was no light in the universe. The first stars weren't actually born yet. The first galaxies didn't exist. And so this is what we call the Dark Ages, the era before light was in the universe. And so at one point, imagine, I like this analogy of being in a stadium, like a rock stadium, and it's completely dark, all the lights are off. And someone holds up their phone and turns on the flashlight. Imagine that's the first star in the universe. then another one pops out, another one, and then another one. And soon enough, the whole stadium is bathing in this light. That's the end of this dark ages. And the question is, what do those first stars look like? What do those first galaxies look like? And so here we have two galaxies in the middle, and the bottom one is only 350 million years old. So it was formed we're seeing it as it was 350 million years after the Big Bang. So it's one of the things that design decisions were made. You think about what we're doing today, we're looking at Jupiter, one of the brightest objects in the night sky, with a telescope that was designed to look at the first galaxies in the universe, a very different sort of brightness of objects, really. Another thing that the telescope is designed to do is to look at planets around other stars. And this is using a technique called coronography. It's quite clever. You put a little disk around the star. So this is a contrast problem, essentially. You want to look at a star, you want to look at a planet that's orbiting a star. The planet is maybe 10,000 times fainter than the star. So an easy way of dealing with that problem is putting a little disk over the star, and that's the actual star shown in the bottom panels. The other blob is a planet. So here we're directly imaging a planet around another star. And using different filters, we can basically do some spectroscopy to determine what this planet is made out of. Right, let me just briefly go on to the solar system, which is what really we care about today, at least. So here's, Tom showed this at the beginning. Here's the first image of Jupiter taken by JWST, returned to Earth in July last year. And it's absolutely beautiful. You see the iconic belts and zones, this really fast-flowing atmospheric storms, Great Red Spot, the largest storm in our solar system. You can fit the entirety of the Earth inside that storm, and that tells you how large these planets are. You have the northern lights at the top, you have the southern lights at the bottom glowing red. Now you can play around with the contrast of this image a little bit, and you get something that looks like this. And Tom mentioned this as well. And we begin to see things we're not used to seeing when we take pictures of Jupiter. Because JWST is so powerful, new things just pop out. For example, you can clearly see the rings of Jupiter. To really think about Jupiter as a planet with rings, but here they are popping out because the telescope is so sensitive. Tom mentioned this layer that sits on the dusk limb. I can zoom in, maybe just show it clearer. So you can see this layer appearing to sit right above the planet. When we first got the data, we were thinking, this isn't like an artifact in the image. Like there's a few features like this, but actually everything we see in these images is real. That's the power of JWST, right? So we've not ever seen this before, but this is the ionosphere glowing above the limb of the planet on the dusk side. And that's what we're doing today. We're investigating the properties of that layer by scanning the disk, scanning around the limb of Jupiter. We've also had pictures of Saturn. This is only a few months ago. And here we see Saturn looking quite eerie, actually. This is at a wavelength that absorbs a lot of the sunlight that hits the planet. So the disk of Saturn actually appears really dark here. We have these rings just floating in space, effectively. You can see different rings, the Cassini division, which the Cassini spacecraft flew through in 2004, I should say. On the bottom right, you have an image of Saturn that I took using the NASA Infrared Telescope facility, not with the camera designed to do science, but really just for fun. We also have pictures of Uranus. You can see Uranus is a weird planet. It's the strangest planet we have in our solar system. It rotates on its side. It has this extreme season, whereas half the time, one of the poles is facing the sun, the other half, the other pole is facing pretty much the entire time towards the sun. So it's really slow, extreme seasons. It also has rings and a number of moons. You can even see, it's really hard to see this, but there's a cloud, a bright cloud on the disk of Jupiter. So we can begin to do stuff like meteorology at Jupiter, and this is Neptune at the ice giants. This picture of Neptune really nicely illustrates the power of Webb. You want to take a picture of Neptune, right? But you end up with this background field of galaxies. So here you have hundreds of galaxies appearing sort of free of charge when you want to take a picture of Neptune. And this, as planetary scientists, probably consider this background noise. But if you're a galaxy person, I think this is gold dust, additional gold dust. This turquoise blob at the top is Neptune's moon Triton. And we can zoom in on Neptune. And here you again see the rings of Neptune. There is one faint ring that sits right here. It's a little hard to see, but it sits right inside where my mouse is. You can see it. This is a ring that's only been seen once before. It was seen by the Voyager 2 spacecraft in 1989. So we're rediscovering things we've not seen for a long time, again, because it's such a powerful telescope. And yeah, that's what we're doing right now, looking at Jupiter. That's what I have for now. So thanks very much.
Thank you. That was excellent, Henrik. Thank you so much for that. Really good overview of JWST and the work that we're doing. Exciting to see that launch again.
Yeah. Oh, awesome.
Were you there? Because you were saying you were having a drink at lunch with Christmas.
Oh no, it was launched from French Guyana, out in the European spaceport, which is ironically in South America. But yeah, no, I was not there. It would have been lovely.
Yeah. Well, thank you so much for doing that. I was wondering, I thought while you're giving your presentation today, I thought, oh, weren't we supposed to go start our JWST? Waiting for that spreadsheet to go from scheduled to, is it scanning?
Scheduled to collecting. I've just updated it. I've not seen it yet, so
let's take a look.
It's probably just a delay. It's nothing to worry about.
Of course not. We've been there before. That's okay. Can you share your the update of that screen with us, just so we can get a look? Maybe some people have joined us late, and so that's what we're waiting on. And you keep refreshing it to see if the highlighted schedule that he's got at the top there changes to collecting.
Yeah.
So is that the same observation that's scheduled there? Oh no, there's two. How many are those all different observations on the same day? Yeah, so we have, to cover the entire limb, we have 36 observations. They all have different names.
I think are we an hour out from the first one?
Yeah.
It is right now 10:55 UT.
Oh, I see. Okay, so I thought we were going to start. So we have another hour.
Oh.
So Henrik's going to double check that, because I think we had an idea that we were going to start now, but that is
10:55. Oh yeah.
A little too excited, which is understandable.
That's okay. I'm glad then that you didn't miss it, because I thought, during your so we still can wait, and that's okay. While we do wait, I'm just going to quickly share my screen and talk about why we're here again today and what we have planned. I think it is almost 12 o'clock. Let me share my screen. Here we go. So you are watching Eyeing the Ionosphere, Juno, JWST, and Jupiter. We just had a wonderful presentation by Dr. Henrik Mellon on JWST, and Professor Stallard has gone over the work that we're doing today and the different observations that are being made and the many people that are involved in doing today's observation. We didn't get into getting chosen for JWST, but maybe another time, all the difficulties and the challenges of having what you want to observe chosen. So this is very generous of Professor Stallard and his team to share this with us. the Royal Astronomical Society, and our viewers. So thank you for being here with us. Please do put your questions in the Q&A on Zoom if you have any. We're also live streaming on YouTube. So if you're joining us from YouTube, you're welcome to leave questions there for the astronomers today. And we're going to take questions throughout the day. I think we have it scheduled a little bit later. So let's see, the time now is about 12 o'clock. We're about to hear from Dr. Rosie Johnson on ionospheres. And I think what I heard from Tom and Henrik right now, we still have another hour before we start scanning via JWST, or collecting via JWST.
Just to interrupt, so I've got a separate Zoom call on a different laptop, and they are now they're taking calibration data on a star as we speak. So the observations at Keck, which is, on Earth, but on the other side of the Earth from us, are starting to spool up onto getting to Jupiter.
Excellent.
So I could either show that a little bit of that now, or we could
so basically between now and 1 o'clock, we'll have an update and Dr. Johnson's presentation. So we can definitely ship those around. That is fine with me if Dr. Johnson's okay with that. So
yeah, go ahead, go and show everyone a star.
Excellent. Thank you, Rosie. Appreciate that.
No worries.
So I'll stop sharing, Tom, and you can go ahead and start talking about what we've got.
Great. So this is going to look very confusing, and it is profoundly confusing for our students when they first see this as well. I believe you can now see a ridiculously large screen with a lot going on it. When we're observing with a telescope like Keck, it's very difficult. They built Keck to be observed from Hawaii, so they were not thinking about how it would be easy to observe remotely. They were thinking about how to get the most information possible. So on this screen is what we would typically want to look at on a particular night to try and understand what's going on. There are 4 separate panels here. So if I can carefully not press anything, but I can move this screen here. This is one of the 4 panels, and you can see them laid out. Top left, middle top, middle bottom, bottom left. You can hear in the background Luke talking. He's on that call, but they can't hear us. And so we have 4 instrument panels, each showing you something very different. And then on the right-hand side is a little bit of information just for us. So there's a live stream, a really nice live stream produced by someone that I don't know who that is. And you can see the night sky of Manikir, where the observations are happening from with Keck. The moon coming up, I can see the Pleiades in there. So that tells us the sky is at least clear enough to see the stars, and there's no cloud around, which is great. A little thing telling us what the current conditions are. It's pretty high humidity, which is a little worrying, but not so high as to block us out. And then in the bottom right of this giant screen is what the aurora of Jupiter look like right now, which is not very interesting right now, but that's fine. We're not focused on Jupiter right now. So I have 4 panels. The top left panel all the way over on the left, and I'll go and zoom into each of these and show you them in more detail. The top left panel, you can see some weird blue striation lines and a big pointy arrow thing. The pointy arrow is the slit rotation. So in order to get our spectra, we have to have light go through a thin slit, and you can see that slit in the bottom left image. So on the bottom left is an image, a beautiful image of a star. So you can see the 6 points that are caused by the hexagon of the dish of Keck, and it is moving around and trying to position up on that star. And so there's a bright and a dark spot. Basically, stars are interesting in their own right, of course, but for us, we're looking at a particularly boring star in order to just have a measurement of the flux. So we know that we gathered 10,000 photons from this star. We know how bright the star should be, so that allows us to calibrate all our data. So this is all just data to calibrate with. So on the bottom left is where we will see Jupiter come up when we move there. But right now it's taking data in 2 positions. And the top left instrument is the setup for those observations for the spectrometer. So we're going to be using measurements to try and understand what's going on in that. In the middle top is where those spectral data will come out. And right now it's a calibration, so you can just see some stuff. That will not be necessarily very obvious, even with a lot of explaining what's going on, but that's the meat of what we want. And in the bottom middle is a wider view of the sky, and you can see that in the bottom there is a weird looking image, which is a big dish, a big black circle, looks like an eyeball with again 6 spikes. Behind that is the star. So the star is occulted here. We can't see the star. And there's a little black box with a dot in it. That's a faint star further away. And Keck is guiding on that faint star. So it's looking at that faint star and saying, okay, I want to make sure that star stays in exactly the same place. And so by using this off-axis guiding, you're able to make sure that the data is accumulated in a really effective way without the object moving around. And so what they're doing is taking data in this bright star. On the bottom left, you can see a sort of a nice square box, and that's the image of the star. Basically, we want light to go through a slit to get spread out into different wavelengths. And so that weird black line that has some green dots along it is our slit, and the light will go through that slit and become scientifically interesting. But the slit itself is polished, and so everything that doesn't go through that slit bounces back into this instrument and we can see it. So you just saw that star move. It moved from one position to another. And so we're taking data in 2 different positions, and hopefully we will get light coming through that slit that gives us the information we need to be able to calibrate our data. So once this sequence is done, then we'll be moving to Jupiter and starting to position up. But for now, for us at least, this is sort of just the background, getting everything we need to be able to understand the science that we want. And so I can leave it there for now. What I'll do is when we get to Jupiter, I'll zoom in and share one of these windows, but this gives you a flavor of the kind of madness that we encounter as scientists, because we have to see all of these different panels and understand them. When you're at Keck, it's actually 4 separate screens spread out with other screens giving you other information as well. So it's quite overwhelming when you first do it. And I'm lucky that it was much more simple than this when I started doing observing. It was only 1 or 2 screens, so I've grown used to it. But I'm sure our new students really struggle with it. And so it's just getting used to this overwhelming sense of information and trying to figure out what you actually need to do with that. Okay.
Thank you. On that panel, did you have, you said they were starting the observation on Jupiter, is that correct?
Yeah, that they are currently on the star.
Oh, I see.
We'll take that star spectra first, and then we'll move to Jupiter. Yeah.
Okay, so then maybe you could let us know how long do you think that might take?
It's probably 5 or 10 minutes.
Okay.
Yeah.
Would it be all right then if we get back to it after Rosie's?
Yeah, that would be good.
Well, Dr. Rosie Johnson is going to speak with us next. She's going to talk to us about ionospheres. Thank you so much, Dr. Johnson, for agreeing to being with us and having this presentation for us to understand better why we're doing these remote observations today. So I'm going to send it over to you. Thank you so much.
Okay, thank you so much. Let me just share my screen and check that I don't share the boring bit. Okay. Yeah, everyone can see the present. Well, you know, standard protocol applies. If you can't see my screen or hear me at any time, please shout. But okay. So hello, I'm Rosie Johnson and I'm a lecturer at Aberystwyth University. And today I'm going to chat to you about Jupiter's ionosphere, hopefully give you a little bit of context to these observations, although Tom and Henrik and in general, we've already been giving you lots of ionosphere facts already. So this is a picture that I took. Everyone's got to include a picture that they took of a telescope, and this is the NASA infrared telescope facility. So this is a telescope that we'll be using later. It's just over the road from Keck on the top of Mauna Kea. And so, yeah, this is a a picture I took after some observing during my PhD. So I wanted to start on the Earth because that's where we live, and chat quickly about the Earth's ionosphere. So the Earth's ionosphere is the top layer of the Earth's atmosphere. So it's this charged layer. So on this little schematic here, it's right up here at the top of the diagram. So we live down here in the thermosphere, and that's where we get all our weather, and we've got all our landmass, our mountains, everything's in the troposphere. We don't spend much time out of the troposphere unless you're an astronaut, I guess. But we dip into the stratosphere. So the stratosphere, that's where you've got like the ozone layer, polar stratospheric clouds, you might have seen them. They're very cool and colorful. Mesosphere has some cool things going on, such as air glow, noctilucent clouds. They're great, might have seen some of them over the summer. And obviously everyone's favorite natural phenomena, the northern lights and the southern lights. I might just be a little bit biased towards the aurora, but yeah, so the aurora happens there in the thermosphere, which the thermosphere layer like overlaps with the ionosphere. And so the ionosphere is populated by charged particles and molecules, and these are also known as ions. So the neutral molecules, Tom mentioned this before, so the neutral molecules, they're being ionized globally by extreme ultraviolet radiation from the sun. And then in the polar regions, that also can be ionized by energetic particles, so electrons coming in through various auroral processes. And over here on the right hand side of this plot, of this like schematic, I've got the different layers of the Earth's ionosphere. So I've got like D, E, and 2F regions. And then you can see which wavelengths, so which wavelengths of light are able to penetrate down through the Earth's atmosphere. And happy for us, visible light obviously gets down to the Earth so we can see what's going on, but also infrared rays can reach the Earth's surface, which is great, keeps us warm, but also means we can observe Jupiter in the infrared. So onto Jupiter's ionosphere. So compared to the Earth, we have much less data taken of Jupiter's atmosphere. So we've got this one nosedive that Galileo took. So Galileo was a spacecraft and it was going around Jupiter for quite some time. And then when it came to the end of its mission, it took a dive into the atmosphere, taking data until it wasn't able to function anymore. And so this is a little schematic here of like the vertical profile of Jupiter's atmosphere. And then like the Earth, the ionosphere is that top charged layer at the top. So it's this hot upper atmosphere part that we're interested in. And then over here on the right, this is a picture of Jupiter. This is a picture of Jupiter's hot upper atmosphere. So this is at the wavelength of about 4 microns. So this is Jupiter in the infrared. And this is why it's so important to observe Jupiter's ionosphere with our ground-based telescopes, because we've got this one nosedive from Galileo, but this is so extremely limited that we need to continue to look from the ground to get these remote observations so we can learn more about Jupiter. So this is Jupiter in 4 microns, and you can see, so at this wavelength, it's the H3 plus ion, which we've already given lots of airtime to. So the H3 plus ion gives the bulk of the emission at this wavelength. So globally, it's created through ionization with extreme ultraviolet radiation. So it's a 2-step process. So first, the molecular hydrogen is ionized by this extreme ultraviolet radiation, and then that makes a H2 plus molecule, which quickly goes on to react with more hydrogen in the ionosphere to make H3 plus. So this happens globally from EUV, and then there's a more concentration of H3 plus at the poles because of the precipitating electrons there, which cause the ionization. So here's Jupiter's northern lights and Jupiter's southern lights. And H3 plus can stick around for quite some time at Jupiter. So at the equator, it can be there for about like 1.6 hours, but in the polar regions, it's kind of only going to stay around for like tens of seconds. So some transport can happen while we're taking the data. So while we're taking our spectral images, the H3 plus can move around a little bit, which means that like these images aren't always as sharp as maybe like if you see the UV images. So Jonathan Nichols will be talking about the UV aurora later. So it doesn't look as sharp as that. So here's my little picture of H3 plus. So it's made of 3 hydrogen atoms which share 2 electrons, and they make a sort of equilateral configuration. And it doesn't have electronic states like where electrons are like jumping up and down energy shells to make light. It has rho vibrational excitation, which is where this triangle is distorted by centrifugal forces. So as it's moving around, the triangle doesn't keep the exact perfect shape. And then this makes the rho vibrational states that emit light that we observe, well, that they're observing right now at Keck. So what does the spectra tell us? So what can the spectra of H3 plus tell us about Jupiter's ionosphere? So I won't go into too much details about like the observing procedure and what the spectra look like, because you're going to see a whole bunch of spectra today, and amazingly for you from 2 telescopes. But just super quickly, for this study in particular, we put the slit of the instrument right at the top of the planet. So we put it at the top of, this is the northern hemisphere of Jupiter, we put it at the top and then step it down through the planet. And then so for this particular slit position where I've drawn a white line, this is a spectral emission line of H3 plus. And so we can, from this line, we can get the intensity. We can find out exactly how bright H3 plus is at every position along that line. So it's sort of like an intensity profile across Jupiter. So just to orientate yourselves, this here is the dawn side of Jupiter through the aurora, and then through the middle of the aurora to the other side of the aurora, which is a bit more broad and diffuse, as you can see from the image above, and then off the dusk side of the planet. And then what I've done here is plotted that onto a little map of Jupiter. So we're looking down on Jupiter, the rotation of Jupiter's rotational pole is there, looking down on Jupiter's northern lights. We can also get the velocity of the H3 plus ions, so we can find out how fast they are moving in Jupiter's ionosphere. So this is the same spectral emission line. And what I've done here is I've just added a horizontal dashed white line. So you can see that this spectral emission line isn't completely flat. It's got a slant to it, and that's due to the Doppler shift of that line. So, you know, Doppler shift, if you're hearing an ambulance driving down the road and you get that pitch change as it's coming towards you and passes speeding off down the road. So we work out the exact position of the peak in the intensity all along the spectral emission line. That gives us, then we can calculate the velocity of the H3 plus ions. And then that's the solid black line that you see here. So if those ions were just going around with the planet, then they would follow the dashed black line. So if we come over to my projection map, so here we've got a blue shift, the ions are rotating towards us through the center of the planet, and then the other side of the planet is rotating away from us. But we've got some super fun stuff going on in the auroral region. So due to how the aurora is created, the H3 plus is moving around and it's not rotating just with the planet. Hence why we've got this wobbly black line, which has loads of fun information in it. We can also work out the temperature of Jupiter's ionosphere from our observations. So we've got the ratio of 2 spectral emission lines, Q1 and Q3, some really excellent lines there. And you can see that the intensity is different. So we take the ratio of that, and from that ratio, we can calculate the temperature. And then again, I've made a little map of the temperature. So my work primarily focuses on the aurora, and Jupiter has some of the most, well, it is the most powerful aurora in the solar system. Here's a little sneak preview of Jupiter's aurora in the ultraviolet, just laid over the visible light. And that's taken with the Hubble Space Telescope, which Jonathan Nichols might talk about later. And then we've got Juno currently in orbit around Jupiter and has taken this image of the southern aurora, which is just fantastic spatial detail because we're so close to the planet, obviously, when we're on the Juno spacecraft. But Juno cannot measure the H3 plus velocities. And that's why, again, it's so important for us to do these ground-based observations, because it's the only way to measure the spectrum. It's the only way to measure the H3 plus velocities. If we could put, I think someone mentioned putting Keck into space, but if we could put IOTF into space, we would have the amazing spectral resolution to be able to do that, but we don't. So that's why it's really important. We need to continue to observe from the ground. I'll just explain a little bit of background to the aurora so that we have it in the context of H3 plus. So Jupiter's magnetic field is super strong, and it expands into this massive bubble, this purple bit here that surrounds Jupiter, and it's known as the magnetosphere. And that rotates super fast, like once every 10 hours, and it's all filled up with all this plasma. And that plasma originates mainly from Jupiter's volcanic moon Io. So here you can see Io is a super colorful moon from all of these fantastic eruptions. And here's a little video from New Horizons that grabs a video of an eruption on Io as it was speeding past on its way to Pluto. So all of this plasma, magnetic field spinning around once every 10 hours. But as you move away from Jupiter, further and further away, it gets harder and harder for that plasma to keep up and for the magnetic field also to keep up. And eventually it lags behind, can't keep up anymore, it slows down. And this sets up a huge electrical current that goes through the magnetosphere and it flows along the magnetic field and it closes in the ionosphere, making the aurora. And this is, this is where we are studying our H3 plus emission. So H3 plus is giving us how it's moving in the ionosphere. It's giving us loads of information about what's actually going on out in the magnetosphere, which is super cool. And although we have got Juno there flying through the magnetosphere, taking measurements, we've only got information along that spacecraft trajectory. But if we view the H3 plus emission from the ground, we can see the whole of the aurora, the whole of the planet. This gives us information about quite a large area of Jupiter's magnetosphere, which is super great. So another reason why it's very important to be observing Jupiter in the infrared from the ground. So what can Jupiter's ionosphere tell us about its magnetosphere? So here I've got the intensity map, so that the brightness of H3 plus. So again, just to reorientate you, I'm looking down on Jupiter's northern hemisphere. So the rotational pole here is at the top in the middle, and this is Jupiter's northern lights. And then here's the velocity. So blue shift coming towards you and red going away. And then you can see in the auroral region, there's a lot of different flows going on, but I just wanted to highlight one, this little white area here. That's where the H3 plus is stationary relative to everything else that's whizzing around once every 10 hours. And this sort of provides evidence to show that the H3 plus, that it's coupled to these magnetic field lines that are going out and reaching out into to interact with the sun's solar wind. So these charged particles bringing the sun's magnetic field out into space. And this is really interesting because what I just explained before, the main thinking of how Jupiter's aurora is made is that it's all to do with the plasma coming from Io and the strong magnetic field all getting spun around really, really fast. So HU plus can sort of tell us about these different processes that are going on in the magnetosphere and how the sun and the solar wind and space weather can moderate these. There's also something else going on at Jupiter and the outer planets that's really interesting and known as the energy crisis. So the gas giant thermospheres, they're several hundred degrees hotter than solar input alone can explain. So we don't know exactly where this extra heat is coming from, but we have got some good ideas about where we think it's coming from now. And so over here on the left, we've got a picture of Jupiter at 4 microns. So it's just scaled a little bit differently because the aurora is really bright. So we've scaled it so that you can see the lower latitudes. And here is the position of the Great Red Spot. So James O'Donoghue, who will be on the call later, found that the Great Red Spot is much higher than the surroundings, over 1,600 Kelvin higher than anywhere else on the planet. And it's thought that, well, we know at Earth that storms can heat the upper atmosphere. And the same thing is happening at Jupiter. So if you look at this schematic, we're thinking this turbulent storm, the Great Red Spot, is making these acoustic waves, gravity waves that are heating the upper atmosphere. And this could contribute to the excess heat that's measured in Jupiter's ionosphere. We've got a video here that will hopefully play. Because another solution to the energy crisis is the redistribution of auroral energy. So the aurora is really hot. James, again, who will be on the call later, he found, him and his colleagues on that paper found these waves of heat coming away from the auroral regions. So sort of in the past, models have thought maybe this isn't possible because the strong rotation of Jupiter, the strong Coriolis forces mean that the heat couldn't travel down. But these observations showed, you can see this temperature gradient, really hot at the poles and cold at the equator. And then, you know, this gradient in between, showing that this heat is getting redistributed. So again, could be another reason why the upper atmosphere is so hot. And away from all the fun stuff, well, in my opinion, aurora, Great Red Spot, very fun. We have the lower latitude ionosphere, which, you know, has previously thought to be maybe a little bit boring by, I don't know, maybe me, but anyway, Tom and his colleagues have done some work on the lower latitude, so towards the equator, that shows it's really not that boring, and there's actually quite a lot of structure here, primarily. So now we can see, so it's just changed the scale so that we can see the dimmer stuff. You can see this like dark ribbon, and that's coincident with the magnetic equator of Jupiter, and something really similar is seen at the Earth. So that is super interesting, and maybe could be because of how the particle electrons like to travel along the magnetic field. So they're diverted away from the magnetic equator, leaving this ribbon of reduced H2 plus production. In that video, you might have spotted that there was this region near the pole, near the North Pole, and it was marked Great Dark Spot. So Tom has found this localized dark spot that's much cooler, around 200 Kelvin cooler than the surroundings. And although it has changed in shape and size, over 15 years of data have shown that it's sort of sticking around. So it's kind of thought to be an auroral generated weather system, but not super sure what drives the weather features, like probably some vortex similar to the Great Red Spot. So yeah, those are all of the main features of the ionosphere of Jupiter that I could think of right now. And and have time to explain. But thankfully, there are a lot of the authors of those papers on the call throughout the day. So if any of those things really piqued your interest, you can ask them for more details. But thank you so much for listening. And if you have any questions, I'll be happy to answer them. Also, here is me stood inside the NASA space. No, not Space Web. That's not Hubble. Imagine. No, it's IOTF on Hawaii.
That's
There
still
you are.
really
That's
cool.
what the inside of IOTF looks like. I wish I was stood inside. Well,
It's-
or do I?
Absolutely brilliant, Rosie. You really connected the dots for me, really. I mean, having done 4 of these already and just kind of visualizing, seeing where H3 plus is concentrated. Also that heat distribution is really interesting. And I guess that's more recent research that's been published from the team. Just really fantastic. Thank you so much for that presentation.
Yeah, no worries.
Understanding of ionospheres and H3 plus, what we're looking at. Really great. We have a thank you, great explanation from Dr. Rosie from David Gwynn-Astro. So, and I wonder if this question might be a little bit related to what you were discussing, and no worries if this isn't your specialization, but AC asks, does the huge Jovian magnetic field modify the layering of the ionized and charged ionosphere molecules?
Yeah, so I sort of briefly touched on that because so the charged particles and the magnetic field, they're really strongly coupled. So they can pull each other, like the H2 plus ions can go one way and they can pull the magnetic field. And sometimes the magnetic field might say, hey, I want to go this way, and pull the H2 plus. So when, yeah, the magnetic field can moderate the flows of H2 plus, especially with varying conditions in Jupiter's local magnetic environment. So if the eruption rates at Io are changing, there's more or less plasma, or if there's something coming from the sun that's going to squash the whole of Jupiter's magnetosphere. So we can tell a lot about the magnetosphere from looking at how the H3 plus is moving around. And yeah, I hope that answers the question.
Yeah, brilliant. Thank you. And Nigel also says, thank you, Rosie. Super job. AC has another question about Jupiter's magnetic field. They want to know if Jupiter has an analogous magnetic anomaly, these regions, such as the Earth South Atlantic magnetic anomaly.
So yeah, so Jupiter's magnetic field is like, yeah, it has anomalies. Like, so in the northern aurora, it's, well, I always think it looks a bit like a kidney bean shape. So it's not like at the Earth we have our auroral ovals, but we tend to say like main auroral emission at Jupiter because it's not an oval in the north, at least. In the south it is more circular. And yeah, so with Tom's work looking at the reduction of H2 plus, so that dark ribbon that was going around the equator, it's like, obviously it wasn't like a perfect circle. So these sort of clues from H2 plus observations, again, showing us that, you know, that Jupiter's magnetic field is not like a bar magnet dipole. There's anomalies going on. Oh, you're on mute, Lucinda.
It happens to the best of us.
It does.
But thank you so much for everything. I don't see any more questions today. Thought I would then share my screen and get back to our program for today. Thank you, Dr. Johnson, for that wonderful presentation. So you are viewing Eye in the Ionosphere, Juno, JWST, and Jupiter, and we would love to show you what we have done today and what we plan for today. So we just heard from Dr. Johnson on ionospheres, and I'm really excited to get back to Tom and Henrik, because before we started this talk, we were going to start, I think, observations via the IRTF, because that was still getting set up, and we could check in with Dr. Mellon as well to see if the collection has begun via JWST. So I'm going to hand it over to those, and then we're going to have another talk in about 30 minutes. So we have plenty of time. If you have any questions about any of the things you've heard and seen so far, please don't hesitate to put them in the Q&A. And we're also on YouTube live streaming this. So if you're watching us on YouTube, you are welcome to leave us any questions there. I am monitoring it for any questions that I can relay to the scientists on your behalf. So thank you, Tom and Henrik, on to you.
Great. Well, we have, I did my timings wrong. So the difference between British summertime and universal time is 1 hour. And I went the other way. So the observations are scheduled to happen in 40 minutes. Rookie error, rookie astronomy error. But time zones are tricky, as we know.
It happens to the best of us.
Yeah.
So I've only just popped back in because I was helping Luke position up on Jupiter. So we are on Jupiter. Well, we're just off the limb of Jupiter right now on Keck. So I can show that if people would like to see Jupiter. I don't know if people would want to see Jupiter.
Yes, please.
Okay, let's see if I can
We
do
always want to see Jupiter.
that. Let's see. So if you remember, I showed you the big panel with 4 different screens. I'm going to look at just one screen now, which is the one that we're using to position up on the planet. And hopefully you can now see a much crisper image of Jupiter in the field of view. So this is an instrument. As we said, we want to look at the spectra. We want to look at the light coming through a slit. That slit is that little black hole in the middle of this gray box, and the black hole is where data is going to come into the instrument. So right now we're looking just above the limb of Jupiter, and you can see half of Jupiter, the northern half of Jupiter, in the field of view now. So they're just positioning up and getting ready to start the scan. The reason I had to get off is because telescopes are confusing and hard, and so knowing which way is up is actually really hard. We can get a sense of which way is up in terms of Jupiter on this image because Jupiter's slightly inclined towards us in the north, and so there's a slight curvature to the clouds, and so we know that we're in the north. But then how do you move the telescope up? Well, there's 2 little arrows, red arrows with positives, and so the obvious thing to do if you want to move the telescope positively away from the planet is to put a positive number in. And when we did that, it went the other way. So telescopes are never easy. So I was just helping Luke figure out what direction we need to scan in, not in terms of where we are on the planet, but on where we are in terms of how the telescope moves on the sky. And so in order to move down, we have to put a positive number in, which is completely counterintuitive, but there you go. So that's what we've done. So Luke is now positioning up again, and we'll run a macro where it will move the slit slowly down through the atmosphere of Jupiter, and that black gap in this plate, this polished plate, will have light falling through it, and then that light falling through it is the really exciting and interesting bit. So right now the planet will disappear, and you can see it shooting off the next frame. There's no planet at all, and that's because, as I said, we're looking through the Earth's atmosphere, and the Earth's atmosphere at 4 micron, where we're looking, is really bright. Global warming makes the atmosphere of the Earth hot, and the instruments that we're using are so sensitive that they see that as a really bright glow in the instrument. And so in order to get rid of that, we have to look at nothing. Now, theoretically, and I tell my students all the time that we're looking at nothing here, but if you look at that James Webb image, we're looking at all sorts of stuff in the background, so that can make things a little bit more confusing. But generally speaking, there's not too much going on in this frame. We're looking at a boring bit of sky near Jupiter that will let us look and hopefully get a measure more of what the Earth is doing than anything out in space. So we're seeing what the Earth looks like when there's hopefully nothing in the night sky, and taking that data in order to be able to understand what we're seeing when we're actually on the planet. And so we'll do this frame first, and then we will switch back to Jupiter and hopefully then take a series of observations with that dark slit starting to move through the planet, and we should start seeing data come in more and more. And that's where we're at right now. So the observations for James Webb are coming up in half an hour or so. We are starting to take data on RTF, on Keck right now, and then in a little bit later in the night, we'll be taking data on Keck as well. So lots going on. I will leave that up for now because I'm sure people want to look at Jupiter when it comes back. And there we are on Jupiter. But I'm happy to field questions or explain more or whatever people want me to talk about.
How long are these exposures, Tom?
So the imager is pretty fast. It's only about 5 seconds or so. And then the spectra that we're taking are going to be about a minute long in total each. So we're going to take light in from the sky and work that way.
And are we going to get to see some spectra at some point?
Yeah, we will hopefully soon see some spectra. I haven't seen any come in yet.
Oh.
There is a question in the question and answer about a fortuitous impact. I did see that in the news. I was hopeful that we would actually have seen the impact, but we've been observing every other night on Jupiter with the IRTF, and unfortunately, naturally, the impact happened between 2 nights, so we missed that impact. The impact itself was very bright. You could see it from Earth using amateur astronomy, but the effect it would have had on the atmosphere was fairly small because it wasn't particularly strong impact. And so even though we were able to look the next night, I don't think there'd be any signature or indication of that impact had happened. But these things are happening all the time. And we have had instances where we've been able to provide context and information about impacts. There was the classic Schumacher-Levy 9 impact back in the 90s, where there was all sorts of disruption. That was such a big impact that it actually changed the atmosphere and ionosphere up in the layer that we're looking at. But more recently, there's been impacts where we wouldn't see anything in our data, but we've allowed other people to use some of our time when we've been fortuitously observing just after the impact in order to take data that shows the change in the lower atmosphere as a result of that. But yeah, nothing significant, I don't think, from that particular instance.
And that just depends on the size of the impactor, size of the space rock that hits the planet.
Exactly that, yeah.
Well, with Schumacher-Levy 9, weren't they able to predict that was going to hit Jupiter? And that's why everyone rallied the telescopes.
Right. So Schumacher-Levy 9 is so named because of the 2 discoverers, Schumacher and Levy. And it's the 9th target that they detected that year. And they observed it moving through the night sky and realized that it was entering the gravitational well of Jupiter and that it would impact. And I think they had about a month or so forewarning, maybe a bit longer. And so were able to set up a series of observations. It's just before my time, so I wasn't involved in any of that, but my supervisor went out. People were observing at the telescope for a month, and every telescope on the entire mountain was looking at Jupiter for that period because it was one of the biggest events ever to happen in astronomy, effectively. And yeah, absolutely profound moment in astronomical history, really, because it's very rare that you get to see something so dramatic happen. It was a once in 100-year impact, effectively. So really interesting science coming out of that, and some really interesting stories of the experiences that I feel very jealous about not having been involved in. So we have just had the question asking whether Jupiter's magnetic field flips in the same way as Earth. And well, the answer to that in theory is yes, but in practice is that we have no way of knowing. The only reason we know the Earth's magnetic field flips is because there's a record within the rocks of the Earth. When you heat a rock up above the Curie temperature and then cool it down again, the magnetic field gets frozen into the rock. And so because of that, volcanic events across the world have allowed us to have a frozen in memory of what the magnetic field was like throughout the past history of the Earth. And that's how we know that the magnetic fields flip. And it's also how we know plate tectonics is real, because we see those reversals spreading out from the mid-Atlantic equator, mid-Atlantic rift. And so you see mirrored flips on either side, and we know that that region is spreading apart. We have records of about 30 years at the most at Jupiter in terms of the magnetic field. So there's no indication of a flip there, in the same way as there's no indication of a flip in any of the data for Earth in the last 100 years. These things are very long timescale changes, but in theory, there's no reason why it wouldn't flip. And it's very likely that that does happen for all planets. One thing that's really interesting is Jupiter and Saturn have magnetic fields that are very like Earth, but Uranus and Neptune are really weird and different. They are not mid-flip. It's impossible, I think, statistically, that both of them will be flipping at the same time. But in many ways, I think that people who talk about what happens when the magnetic poles flip have changes in the conditions at Earth that are approximately similar to what you see at the ice giant. So that's one of the reasons why we're really interested in understanding the magnetic environments around those worlds, is because it really feeds back into our understanding of what happens at Earth during a magnetic anomaly like that. So there's a lot of analogy there. Actually, when you look at Jupiter from most spacecraft that orbit at a distance, the magnetic field seems relatively similar to Earth. Very dipolar in shape, off axis, just like Earth is. But when you look at the aurora, it's more complicated than that. It looks weirdly distorted. And it's only once Juno arrived and did a very, very close orbit and a very inclined orbit that we were able to start seeing some really weird stuff going on at Jupiter that doesn't look anything like the Earth. So while it's not undergoing a reversal, it's got some weird stuff that implies all sorts of weird stuff going on in the interior of Jupiter that doesn't happen at Earth. So you end up with some really severe magnetic anomalies. We have very small scale anomalies at Earth. There's a mid-Atlantic anomaly, and that's moving. So right now, the mid-Atlantic anomaly is no longer over the Atlantic. So that tells you that it's moved over the time that it's been registered. But that anomaly is vastly smaller in proportional sense than some of the anomalies you see at Jupiter that are really, really strong anomalies and distort the magnetic field to the extent that the aurora changes its shape from being a sort of roughly circular shape to being incredibly distorted, as you saw in Rosie's talk. So there's some really interesting stuff going on there. I'm just looking at some of the data coming in, and I haven't seen any change in the data, so I don't know if that data feed is not coming through, but we are clearly on the planet and seeing some, should be seeing some spectra coming through soon, so I'll keep an eye out on that.
What's the current view of Jupiter? Do you have that plot? What we expect the aurora to be right now?
We'll just update it. So what we should be seeing is almost nothing in the north and something of an aurora in the south. I can share that rather boring looking plot just for a second. You can see what that looks like. So this is as if we were looking at it in the night sky with a perfect imager that looked at the aurora. The blue lines show you the mapping for the Io spot, which is the dashed line, and then the main auroral oval. So you can see in the south, we should see an auroral oval, but the north, where it's much cleaner and more easy to see, has not rotated into view yet. And so we're going to start our observations with James Webb over on this left-hand side, below the auroral region, because that's where the occultation is coming into view. And right now, Keck is positioned over the North Pole and scanning downwards, so should be starting to see some really interesting spectra coming through, but I'm not seeing them yet. So I'm going to check in on them now and see whether something's up, or if they just not, if I've not got the right thing loaded up or what. So I'm going to go silent just for a second or two and see whether I can figure out what's going on.
Great. Yeah, so we're 25 minutes away, hopefully, this time for the web data to be taken.
Very exciting. So
Mhm.
did you, when you know, the timings of starting the James Webb Space Telescope observations, are they timed to be that you're going to be going up the limb as the, oh no, wait, this is the view from Earth.
Well, the view from Earth is not that different from.
It's not going to be that different. Yeah,
No.
yeah. So my question is, yeah. So did you decide that you needed to start the observations, James Webb Telescope ones, at this time so that you could like sneak up along the aurora, or was it just like the scheduling? That's the time you were given.
Well, we had to observe 35 north on the dawn limb
Mm-hmm.
at 1:30, because that's
Yeah.
when the observation happened.
Yeah.
So we knew we had to be there at that time. And then the only question is, are we going to go clockwise or anti-clockwise?
I see.
around the
Yeah.
rim? And I did some modeling that showed if you go clockwise, you can actually capture the northern aurora quite well.
Yeah.
And there is actually a gap. So we do from 35 north or over the North Pole to 35 south.
Yeah.
And then there's actually a break of about 6 hours. So from 6 o'clock this evening till midnight, there's a little break. The telescope does some other stuff and then comes back to Jupiter and finishes the circle.
Yeah.
And
In the
that's
same place. So it just like picks up where it lets off, and then it's like
exactly,
just
yeah.
the south. Okay.
That's actually quite good for us, because that
Yeah.
means if our plan is right,
Yeah.
then we should capture the northern aurora.
Yeah.
If there is that 6 hour break. We
Yeah.
should also capture the southern aurora as well.
Yeah, because it will really rotate into
Yeah.
view. Yeah. Yeah, it's kind of cool that the view from James Webb Space Telescope is very similar to the Earth's view. Then otherwise you'd have so much more to wrap your head around.
Yeah.
It's so, yeah, I think that's one of the things that I really struggled with and probably still struggle with, just the orientation when you're in space.
Yeah.
Yeah, it's confusing.
It's confusing. The good thing about James Webb, though, is got all these star trackers,
Yeah.
really accurate pointing.
Yeah.
The telescope moves around in space as well. It orbits this L2 point.
Yeah. Yeah.
But
Yeah.
we have incredibly accurate pointing information. So one of the products they produce is a file that says the telescope is here in space, pointing in this direction. And so we can work out the geometry of Jupiter quite easily. In other words, where exactly we're pointing on Jupiter with a telescope.
Yeah, that's perfect.
Yeah.
That's really ideal because, as you know, for the ground-based stuff, it's a little bit more hand wavy, isn't it? We look at the Jupiter and we go, yeah, the slit looks like it's in the middle. And then, yeah, we've all been working on recently some ways to really figure out exactly where we are on Jupiter, because that is quite critical, isn't it? We want to know exactly where we are
Yeah.
It doesn't necessarily change the data, does it? It's like you still can measure the temperature, you can still measure the velocity, but to really know where you are exactly.
Yeah, and that's why those images are really useful.
Yeah.
That Tom showed earlier. It gives us
Yeah.
a location of where that slit is pointing to. Oh, hello.
Oh, spectra.
Okay.
This is fun. So I was still sorting things out.
Oh, yeah, sorry, I was
Yes,
talking
here
to
we
no
are.
one.
Yeah, I was like, Tom is silent.
There's a lot of buttons to press because I have to mute everything on this stream to talk
yes.
to them, and then I have to make sure to mute everything on them before I get to unmute everything on here.
The old double
Breaking
zoom.
My brain. Okay, hello. So one of the 4 panels had frozen, and I didn't know until I clicked on the panel when I was talking to them. They were seeing spectra, but we weren't, because that's what happens. So I restarted everything again, and now we're on the panel that shows you what's coming in. So we took a sky and we're subtracting the sky off. The sky itself is a bit murky, so it's not a perfect subtraction. And so you can see a very confused picture here, but this is a multi-wavelength piece of data that shows you lots of spectra. And so each of those individual slices that you can see are different bins of wavelength. So if we count down from the top, you can go 1, 2, 3, 4 from the top, and there's lots of white lines and lots of black lines in that panel. So that individual slice has wavelength left and right and spatial information. So the sort of the slit's position on the moon, on the planet, in that up and down direction. And you can see all the dark bits are where we haven't subtracted the sky out perfectly. And so we're seeing Earth a little bit. And then all the bright bits are the H3 plus emission lines emitting from the top of the atmosphere. If you look at the very top of those slices, so the slice at the top, you can see lots of thin lines, but also lots of broad, bright white. So it's lots of white in that top slice, and that's reflected sunlight. And you can see the same in the very bottom slice. So in those, we're looking at wavelengths where there's lots of sunlight hitting the atmosphere and bouncing back to us. And so we're able to see the planet in those wavelengths. But what makes this wavelength window really great is that global warming gases like CO2 are really effective at absorbing the light. And so Jupiter has so many of those that it absorbs all of the sunlight completely. And in these wavelengths, basically the planet is dark. The planet disappears, but we can still see the top of the atmosphere above all of that global warming gas. And so we see just the ionosphere. So a lot of the data that you were seeing from Rosie's talk comes through those nice bright lines, and those are the ionosphere of Jupiter, a slither of aurora on the limb of the planet, but mostly it's just atmosphere, the ionosphere away from that auroral region, which is in itself a really interesting layer of the atmosphere. Right now we're scanning from the top. There was a lot of discussion between the telescope operator, the support astronomer, Luke, and myself about which way is dawn. Fortunately, because I'd looked away and was talking to you guys for a while, I got to see a jump in where what the planet looked like, whereas they were watching it move. And so I could see that when we were looking at the image, there was a little storm in the atmosphere, and that storm had definitely moved away from the limb, which meant I knew for sure that which was dawn and which was dusk. Because when you're looking at a planet in a nice picture on the internet, everyone has done the work to make sure that it is represented in the way that you want. But often with telescopes, you're looking at something raw, and often there's a flip in one direction or another because you're using a whole bunch of mirrors. And so sometimes it can get really confusing. But hopefully we now know that dawn is up, And so we're going to move towards the dawn so that we can scan through the specific area of the atmosphere that the Juno mission will be looking through and James Webb will be looking at the same time. So that's the aim. It's great we're getting real data. We can see some really nice emission lines here. It's really unusual for us to look at data that looks like this, by the way. Keck is a really powerful telescope and it's really hard to get time on it. And so we tend to look at, in this kind of wavelength, at the really weak and difficult to look at stuff down near the equator. If we want to look at the aurora, we'll use different settings that tell us other things, and they're much weaker lines, but they tell us more depth of information because it tells us about the neutrals. It's very rare that we actually use this really bright stuff, these really bright emission lines in the polar regions. It's kind of fun that we're going to get some really, really bright stuff. The plan is to do observations of that limb region that James Webb and Juno will be looking at initially. But then we've got 5 hours on this telescope, so we've got plenty of time for the planet to rotate. James Webb will be moving from that Juno occultation up towards the pole as the planet rotates. And so by the time it gets to the pole, where the aurora is, the aurora will have rotated into view, and we will be moving there too and scanning and getting auroral data at the same time. So we'll be getting data that we've never had before on Keck. It's stuff that I wish that we'd gotten for a decade. It's going to be super bright and amazing, and immediately will be superseded by James Webb. So really fun. But of course, as Rosie was saying, that kind of observation, that kind of measurement can give us winds as well as temperatures and all the other things we're interested in. So that's what you can see. It's very confusing to look at, and it's quite hard to explain, especially without pointing. And the reason I can't point is because this is a live instrument. So if I start moving my mouse to explain what things are, the observers will see that, and it might even stop them from doing what they're doing. So frustratingly can't do that right now, but hopefully you can see this interesting set of data. And what I will do is switch back to looking at the imager, because right now we are in the B-beam, but we will come back and hopefully see.
It's like Christmas today. It's really exciting. And I don't want to interrupt any data, but we do have to switch a host in a moment. So let me know when's a good time in the next 3 to 5 minutes, or is now a good time?
Well, you know, I think Johnny is up, and I'm always happy to.
He is, but if you have something that needs to be shown now, because I don't want to miss anything.
No, I mean, I think we've had a chance to look at Jupiter. We've had a chance to look at the kind of complicated and weird data that we get out in raw form, and Rosie's had a chance to tell you about how that turns into science for what we're doing. But I think it'd be really good to hear from Johnny about what we can do with a space telescope, different space telescope, but a space telescope nonetheless.
We've had some phenomenal observations, but I mean presentations so far. Just want to remind everyone you're watching Eyeing the Ionosphere. Thank you so much for being with us. We need more questions, so put them in the chat box, or sorry, not the chat box. So we're not using that on Zoom, but the Q&A, or the Q&A on YouTube, because we are on YouTube here today, live streaming. And I'm going to say goodbye for a while. I'll be back after Professor Nichols' presentation. Thank you so much for being with us, Professor Nichols. I'm handing it over to my wonderful colleague, Royal Astronomical Society Education Outreach and Diversity Officer, Dr. Sheila Kanani. Hello, Dr. Kanani. And she's going to introduce our next guest. Thank you so much. And just a really quick review of where we are today. We are halfway through, it seems. And we're starting off here now with Professor Nichols on far UV auroras. On to you, Sheila. Thank you.
Thank you so much, Lucinda. It's been absolutely incredible this morning. I've really loved watching and listening and learning, and some of the images that have been shown as well are mind-blowing. It's great to remember why we do what we do and be able to broadcast it as well. So thanks to Lucinda for everything that you've been doing up until today, and obviously to the astronomers as well. And it's great to see some familiar faces. Tom was one of my PhD examiners, so it's always nice to see you in a more familiar setting, Tom. It's great to hear what you've been up to. So next up, we've got Professor Johnny Nichols from Leicester. We're really happy to have him with us today, and he's here to talk to us about Jupiter's far UV auroras over 15 years of data collection. And he'll also give us a bit of an update on Juno. So Johnny, over to you. I can see a screen.
Great, excellent.
Myself.
Thank you. Thank you very much for that introduction. Can you see that screen now?
Yeah, that looks perfect. Thank you.
Great, fantastic. So what I'm going to do today is I'm going to give you a bit of an introduction to Jupiter's auroras in the ultraviolet. So I'll get rid of this screen. What you see here is perhaps what you might be more familiar with in terms of the auroras, which are the Earth's auroras. Now, the Earth's auroras shine very brightly in the green and the red and magenta. The other planets have auroras too, but they shine in different colors. And you've been hearing a lot about Jupiter's infrared auroral emission this morning. I'm going to tell you a little bit about what we see in the ultraviolet. But just to give you a bit more of a background as to what causes auroras on planets, it all starts with, or it often starts with the sun. And this is a great movie from the Solar Dynamics Observatory spacecraft, focusing in on a region on the sun. And what you're seeing here is what we call a coronal mass ejection. That's where energy that's built up and stored in magnetic field lines near the sun snaps, and that's then allows this material to be released into space and blown off the surface of the sun at very high speeds. And we can zoom out into the wider solar system by using different spacecraft. There's another one here called SOHO, which allows us to zoom out and take a full view of the sun. And what it does is it lets you see all of this activity on the sun and the material being emitted into the solar system in various different directions. The next one shows you here the solar wind blowing away from the sun in all directions. Now, this is the context in which all planets in the solar system are embedded in this solar wind that's constantly blowing outward from the sun. And this is ultimately what drives the Earth's auroras. So this is a nice cartoon here showing the solar wind blowing away from the sun in radially in all directions. It hits the Earth's magnetic field at about 1 million miles an hour, and it causes the magnetic field to stir around. It grabs hold of some of the magnetic field at the front, drags it over towards the night side, and that sets up basically a stirring motion in the Earth's magnetic field and its upper atmosphere, and that is what drives the Earth's auroras. So when the solar wind is blowing hard, the Earth has nice bright auroras, and when it's not blowing hard, it's quite dim. And there are subtleties to do with the magnetic field involved in all of this. But the point is to say that the Earth's auroras are driven ultimately by the sun. You get a really nice view of the auroras if you can go up into space and you look down on the auroras, and what you see is a ring of auroras surrounding the pole. This is the Earth's ultraviolet aurora. Earth has ultraviolet aurora, just like Jupiter. It's emitted from hydrogen in the upper atmosphere, and you can see that the auroras are changing. Sometimes the oval is small, sometimes it's big. You can see the day side of the Earth in white here on the right, and that tells us the nature of the processes, the energetic processes that are occurring in the Earth's upper atmosphere. Now, the reason why I'm showing you that is because obviously we don't get a view looking upwards at Jupiter's auroras, but we always have a view looking down. And we use various observatories like the observatories that Tom and colleagues have been talking about. But we can also use spacecraft like the Juno spacecraft and the Hubble Space Telescope. Now, Jupiter's magnetic field, just to put it in context, is 5 times bigger than the sun. It's also 5 times further away than the sun. So if you could see Jupiter's magnetic field in the sky, it would appear as large as the sun in the sky. It also stretches beyond the orbit of Saturn. So it's the biggest coherent structure within the solar system, or within the heliosphere. And as such, it's a very important analogy for more distant astrophysical bodies like brown dwarfs, exoplanets, perhaps even pulsars, that we can't send spacecraft to, but we can send spacecraft to Jupiter. So it allows us to move away from the Earth's magnetic field, which is one very important and interesting data point, to another planet where we can get a feeling for how these processes operate in very different environments, and then perhaps even extrapolate those to beyond the solar system. Now, how do spacecraft and observatories like Jupiter, like HST help? Well, Juno is specifically designed to be a polar orbiter, so it's orbiting around the poles, so it gets a really nice view down on the poles, and it also allows us to measure the magnetic field and the particles that are causing the aurora. So aurora are caused when energetic particles are caused to funnel down the magnetic field lines. They hit the atmosphere and they make it glow. So at the Earth, it's green and magenta and red because of the nitrogen and oxygen, a bit of hydrogen in the atmosphere. At Jupiter, it shines brightly in the red because there's lots of hydrogen and there's a bright hydrogen line in the red. It shines brightly in the infrared, and that's the H3 plus that has been talked about by Tom, and it shines brightly in the ultraviolet. And the ultraviolet needs to be observed by us above our atmosphere, because our atmosphere absorbs ultraviolet, and so we need to use something like the Hubble Space Telescope. So this is an example of an image of Jupiter's auroras using the Hubble Space Telescope. So Hubble is above the atmosphere. It can take pictures in the far ultraviolet, and this is Jupiter's northern magnetic pole, as taken with the Hubble Space Telescope. So there are a number of features on here that I want to talk about. The first is that you can see that there's a ring. So just like the Earth, there is a main auroral oval, we call it, or main auroral emission sometimes, because it's not really an oval. You can see it's kind of broken up here. It's distorted like a kidney bean in shape. Some regions it's bright, some regions it's dim. And so, you know, we call it an oval sometimes, but actually it's not really. It's more like a main auroral kidney bean, but that doesn't quite fly so well in scientific papers. But that's not the only feature of Jupiter's aurora. There are a number of other features that we see. So there's a spot here with a line behind it. There's another one here, another one here, and these are what we call the satellite footprints. Now these are magnetically connected to the Galilean moons, the biggest moons of Jupiter, and they're caused for a number of reasons, but fundamentally due to the fact that Jupiter is rotating very rapidly, and these moons are moving through this very rapidly rotating magnetic field. And I'll tell you a little bit more about that in a second. But there is also this emission up here near the pole, and that is still very mysterious, and it's still something that we're looking to understand with the Juno spacecraft. And I'll show you a movie shortly so you can see just how amazing this polar aurora really is. So I mentioned the rotation of Jupiter. Well, it all comes down to this moon here. So this moon is called Io. It's the innermost Galilean moon. It's extremely volcanic. Its volcanoes spew out sulfur dioxide at the rate of about 1 ton per second into Jupiter's space surrounding Jupiter. And this material, some of it falls back down to Io, but some of it is released into space, whereupon it becomes ionized. That means the atoms are split into electrons and positive remaining ions. And when they're ionized, they feel the rapid 10-hour rotation of Jupiter's magnetic field. They become propelled outwards to form a vast rotating disk of plasma surrounding Jupiter. And as it moves outwards, it wants to try and slow down, because if you imagine you're an ice skater and you put your arms out, you'll slow down. It's because it's something called conservation of angular momentum. But you see, what Jupiter doesn't want to slow down, and Jupiter's sort of attached by its magnetic field to this plasma in the equatorial plane. And so there's a tug of war between Jupiter on one hand and this material that's flowing away from Io. And that tug of war is conducted through electric currents. What is an electric current? Electric current is a flow of charged particles. And when those charged particles flow downwards along the magnetic field line into the planet, they cause aurora and make it glow. And we can actually see this process is going on. This is a New Horizons movie of one of the volcanoes on Io. This is the cloud surrounding material surrounding Jupiter. And the ultimate result of all of this is Jupiter's auroras. So I just apologize if there's some background noise, by the way. It's some electricians working on on the electrics here. But anyway, what this movie here gives you a great view of the auroras, and you can see that they're not always the same. Just like the Earth's auroras, sometimes the auroral oval is bright, sometimes it's dim. Sometimes the aurora in the polar region are bright, and sometimes they're dim. Sometimes they're flashing, sometimes they're not. Sometimes you see waves of aurora propagating over the polar cap. Sometimes you see really bright patches of aurora down equatorward of the main auroral oval, and sometimes you don't. So this gives you an idea about how variable the system is. Now, the first thing to say then is that I described the process of material being released from Io and moving outwards and the planet's tug of war. Now, that we think is causes this main auroral oval. Now, there are some questions that we still don't understand. We don't quite understand why it always varies in the way that it does. We don't quite understand why there's a difference between the two sides and various other things. So there's lots of active work that we need to do to understand all this. And this is one of the things that Juno is looking at, because it can look at what's going on in the magnetic field, and we can compare that with what is happening in the auroras, and we can infer what's happening in the space surrounding Jupiter. And that's one of the things that we've done recently. We've looked at how the magnetic field varies, and we've shown that when there is lots of electric current flowing at Jupiter, the main auroral emission is very bright, and when there's no electric current, the main auroral emission is dim. So that's telling us that there is a strong link between these currents and the brightness of the aurora. We've also recently shown that patches of auroral emission that are equatorward of the auroral region here are caused by ongoing periods of this motion of this material away from Io. So what happens is you have a blob of plasma. Blob is the technical term. A blob of plasma that's been created by Io moving away from Jupiter. And just like bubbles in a pint or a drink, you have a bubble moves upwards, and it's actually been replaced by liquid as it moves back downwards. And so what you have is the material moving outwards and bubbles effectively of very hot but very tenuous plasma moving in to replace it. And it's been thought for quite a long time that this kind of process is responsible for some various distinct bright patches of emission that we see on Jupiter's aurora. But that's really only been circumstantial. We've never actually seen it because we've never had a spacecraft in the right place, in the right time, when we've been looking at a series of auroras, and when the spacecraft is on the right magnetic field line. Well, we've seen that recently. And so that's another really nice demonstration as to how Jupiter's auroras can be used to diagnose what's happening in Jupiter's magnetic field. So another thing that that you can see here is that there's all this flashy, repetitive aurora here on the dusk side. we think that is possibly due to the way that this material is released down out of Jupiter's magnetic field, down the magnetic tail, that we call it. But again, the details aren't really fully understood. And one of the observations that we show here is a really bright enhancement. Here we are, a bright enhancement of the aurora on what we call the dawn side. So the side on the left-hand side is from our view from Earth. Now these dawn, what we call dawn storms, we think are produced when effectively, again, you have what we call a large-scale reconfiguration of the magnetic field. So you might imagine, for example, that Jupiter's magnetic field builds up and builds up full of plasma from Io, and oftentimes this material has been lost down the tail, but perhaps it could build up to such a degree that it suddenly goes pop, and a lot of the magnetic field reconfigures, and you get material flowing down the tail, and then you end up with this really very, very intense emission. This emission here that I've shown you here was at the time the most powerful auroral emission ever observed by humanity, and the total emission here was 6 terawatts. Now we've since beaten that. We've had an emission that we observed earlier on this year, which went up to 9 terawatts, and that is incredibly powerful. Well, and also there are been some more recent detections of radio emission from objects outside the solar system, which would be more powerful. But at the time, this was the most powerful auroras ever. And this is so powerful that it's very difficult for this energy to disappear in Jupiter's atmosphere. So you end up with supersonic expansion away from the auroral zone, and it's this energy that is being that has been dumped into the atmosphere that's revealed here by the far ultraviolet auroras that ultimately leads to the H3 plus that has been observed by my colleagues on this call. So what happens is these, as well as exciting hydrogen atoms, allowing them to release that energy and glow in hydrogen, sometimes it's even powerful enough to knock off an electron, and you have all sorts of chemistry that can then occur, and it produces the H3 plus, these 3 protons sticking together that can then rather efficiently radiate this energy away. And so what we've got is a chain of events starting out in the magnetic field, where you have Io and you have plasma moving away, you have electric currents, you have then energy being dumped, sometimes in vast quantities, into the upper atmosphere of Jupiter. Then you've got all sorts of chemistry and auroral emission, and you've got to figure out how that energy moves away from the auroral zone. And that's a really intense topic of research at the moment, how all of this relates together. And there's even hints that this energy can get as far down as the stratosphere in Jupiter's atmosphere. So there's some really cool stuff going on here. Now, just to mention Juno, these are some images of Juno's auroras, of Jupiter's auroras, as looking down on the planet using Juno. So you can see that we get it's not, I would hesitate to say a better view. You get a different view looking down on the planet, because of course from the Earth we're always looking from the same side, and we're sort of limited in when we can observe the north and the south of Jupiter. But Juno can always look down wherever, and so this kidney bean could be pointed away from the sun or towards the sun, and that's really important to figure out how, what different processes are causing different auroral emissions. And Juno is close enough to get some really nice detail in the structure of the auroras that we can't sometimes see with Hubble. The difference with Juno is that it builds up images by scanning across the auroral zone. So the images that you get aren't really images, and so they're limited in what they can tell you in that respect. But because it's very near, you get great detail. And so we can compare what's going on with Hubble with what Juno sees, and again, that's very helpful. And you can see that there's the main features that we can see here are very similar. Bands of emission, dots, and various other things. But my heart still lies with the Hubble observations, because they're really nice high time resolution and the morphology that you get from those. Just to say that Juno can also observe in the infrared, and this is the same emission that Tom and colleagues focus on. This is observed by Juno, and again, the detail that is in all of this emission here is unbelievable. So we can focus really in on that spot that was associated with the moon Io, and you can see that it's not just one spot, but there's a whole bunch of spots behind it, almost interleaved, almost looking like what we call von Karman vortices behind, say, a pillar on a bridge in a river. You get interweaving eddies behind the pillar, and perhaps that's what's going on there. We have the trail behind Io is sometimes split up into two different trails. You can't see that with Hubble, and so that's some really interesting detail that we're getting with Juno that you can't get from the Earth. And this structure that you can see in the aurora, again, it's unprecedented detail. And I remember the first time the team saw this kind of image, when the GIRAM team showed this image for the first time. It was your jaw hit the floor. It was unbelievable and amazing detail that we've never seen before. And just to sort of round up, I mentioned we can tell that this kind of process goes on outside of the solar system. There are these objects called ultra cool dwarfs, which are sort of smaller the low end of stars, high end of planets, and they emit radio waves. And these radio waves can sometimes be observed to pulse, bing, 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 like this. And they look very like the radio waves that are emitted by Jupiter. So not only have we got ultraviolet, we've got infrared, we've got visible auroras, there's also radio auroras pulsing around out from Jupiter like a lighthouse in the solar system. And we see this kind of emission from other objects in the universe as well. And so it gives us a very strong indication that auroras and the auroral-like processes are occurring on Jupiter. So just to summarize then, we've got Earth. Auroras are produced by the solar wind. Jupiter, you can take the solar wind away and you still have auroras, because it's powered by the rotation of the planet, coupled with the volcanic moon Io, propelling this material away from Jupiter. A tug of war between Jupiter and this material from Io produces Jupiter's main auroral oval, and we can study it with not only Juno but also spacecraft like Hubble, where we can observe the auroras and how they change, and then we can actually extrapolate this to bodies elsewhere in the universe. So that's it. I think my time's up. So thank you for listening, and I will hand back.
Thank you. That was absolutely fascinating. We do have a couple of questions, and if there are any other questions, please do send them through either the Q&A on Zoom or on YouTube. We're checking both things. I also had a question as well. So I'll start with the audience question from AC, who's asking, saying, is there a correlation between the Jovian radio emission storms in the high frequency, like 10 to 20 megahertz range, and the auroral activity and brightness from either poles?
Yes, absolutely. There's a very strong correlation. In fact, so Jupiter's, the magnetic field of Jupiter was discovered before the Van Allen belts were discovered around the Earth in the 50s. That was the first evidence of Jupiter's magnetic field. And we've been observing Jupiter's radio emissions ever since, in the frequencies that you mentioned, and other ones as well. And they vary. They've been shown to vary as the moon Io moves around in its orbit. So when Io is at different positions in its orbit, sometimes you get bright bursts of emission, other times you get bursts of emission at other times as well. And so we know that there's a very strong correlation between the brightness of Jupiter's aurora and the position of Io, but also how fast the solar wind is blowing or how strong it's blowing. And those very same features are observed in the infrared or in the ultraviolet as well. So we know there's a very strong correlation between the behavior of the radio and the aurora.
Thank you. And then I had a question. So you mentioned quite near the beginning of your talk the relationship between Io and Jupiter and the aurora. And obviously Io's volcanic, and that's how the material gets spewed out into the atmosphere of Jupiter. How long, or do we know how long Io is likely to remain active, or so active that, and when it stops being so active, will Jupiter lose a lot of its aurora? Yeah,
that's a really good question. In terms of geological timescales, Io has probably been active for as old as the solar system. It's losing a ton per second, but you multiply a ton per second over the lifetime of the solar system, you only get a fraction of Io's mass. So it can keep losing its mass for the foreseeable future. It does vary, however, in the rate at which material is pumped out, and we see variations in the numbers of active volcanoes and the brightness of the cloud that surrounds Io, and those vary on the timescales of months, so several months. Now, the relation then between how that variation then connects into variation in the timescales that we see in Jupiter's magnetic field, there is not quite clear. We think there's probably a several tens of day turnaround time with material flowing outwards from Io and empty magnetic field coming back round. So we do know that it varies on sort of several tens of days. The problem is that so does the solar wind out at Jupiter, and so you see a very similar timescale in variation as the solar wind blows hard and then it doesn't blow hard. So all of this stuff is interconnected, and it's quite difficult to untangle what's going on. So that's again the subject of ongoing current work.
Oh, that's absolutely fascinating. Thank you so much. I can't see any other questions for Professor Nichols, but thank you so much for being with us today, Professor Jonathan, and speaking on far UV auroras. What we're going to do now is check back with the team. You're welcome to stay and see what's going on. Obviously, if you need to get off as well, you're welcome to leave. But yeah, we're going to check back with the team, and we'll go from there. Was there a question from the team for Professor Nichols?
I just wondered whether he wanted to update us on what's next in terms of the observations for Hubble and other associated observations. I don't know what you've got in the pipeline coming up.
Yeah, of course. All right, so what's coming up? Well, of course, Juno is still there. And Juno's orbit is such that it's getting closer and closer to Io. So it's sort of tilting down, and as its orbit changes, we get a better view of the very polar region in terms of the magnetic field and particles, and also it's crossing the equator closer and closer to Io. So that's the focus of the mission now, is the inner region of Jupiter. So the inner Jupiter's magnetic field. So the where all these currents are flowing, the interaction between Jupiter and the moons, and that's going to be the focus. Certainly, we've got ongoing Hubble observations looking at that, and there's just been a new, very large program of observations of Io accepted at Hubble for the next year. So we've got our ongoing program. There's a new program of observations of Io. So all of that work will be going on over the next year, and as you know, many years following. But also, I was very excited that we got a proposal accepted to observe Jupiter's auroras with Hubble and JWST simultaneously. So that'll be really fun, because what we'll do is we'll see the flashing of the UV aurora, and then we'll see the H3 plus hopefully brighten and then fade away over a time scale as well. So that's all to come over the next year. So yeah, plenty of things to keep us occupied.
That is very cool. And I love the fact that you can see different things. I know this sounds really obvious, but that you can see different things with different instruments and piecing it all together as one massive puzzle. That's been brilliant. Thank you so much, Professor Nichols. What we're going to do is switch back to the observation team, and you can see the schedule on the screen. We've got Dr. Prosser from the RAS coming up at 2 p.m, Katie and Dr. James at 2:30, an observation update at 3 o'clock, and then 3:30 we've got Dr. Dunn with the Orbiters team. So stick with us, we've got some exciting things coming up. So anything to update from Professor Tom? Anything?
Sure. Yeah, just to follow up on what Johnny said, I mean, isn't it amazing that it shows how interesting and important the work that we're doing is, that, you know, of all of the planetary observations that have been proposed, we have 2 separate accepted proposals to look at the aurora and the equatorial regions. It's a real testament to the importance of this layer and what we're doing. I'm so excited for John Nichols's program. The idea of looking with Hubble and James Webb at the same time at anything is really interesting, and you know, there's always, but to do it for the aurora is just going to be absolutely amazing. And I have predictions of what we'll see. I won't say what they are, but I think if I'm wrong, they're going to be really important, and if I'm right, they're going to be even more important. So just really, really cool stuff. Really exciting.
This is the first time that we've done anything like this with James Webb and Hubble and Aurora.
It's an interesting question, actually. I'm not sure if it's not going to be the first time we've ever done this, ignoring planets. I know that this observation we're doing today is the first scheduled observation of any planet in the solar system that's gone through the standard kind of bidding process rather than a guaranteed time or an early release science. This is the first time we've ever observed a planet using just the standard requesting time system today. So that shows how unusual this kind of thing is. We've always tried to do simultaneous observations between Hubble and other telescopes, and we have, in the history of 20 years of Hubble, maybe 3 times or 4 times ever been able to observe the aurora at the same time. And that's using ground-based telescopes where you can bid and ask for time over and over again. And even then, it's super rare that this happens. And whether it's something that we should check back with Hubble and James Webb about, because I'm not convinced that will have happened. They will have looked at the same targets at different times for sure. You know, we've got those wonderful comparison images, but those are objects that change on timescales of centuries and millennia. To be able to observe something that's actually actively changing, it's possible it's happened before, but I don't think it's very likely. So,
yeah, Hubble and JWST observed the DART impact together.
Right.
That's the only example I can think of.
Yeah.
And I think there's one, when I was looking through the literature, there's one example of overlapping ground-based and HST observations. That was taken with the NSF cam that you'll be familiar with, Tom, of course, which is now defunct.
Yeah.
And that's partially overlapping, but it doesn't get this. You know, I mean, you know what James Webb is capable of. It's a completely different ballpark. So yeah. Fun times.
Right now, the Juno occultation is happening, and right now, James Webb is looking at the same part of the limb.
I'm going to show my full screen again. It's going to overwhelm everyone because it's yes, but that's fine. So this again is the kind of thing that we would see when we're running a telescope. There's a lot going on in here. What I would point you to first is the top right corner, which is the view of what it looks like at the mountain right now. And you can see the moon, and you can also see a lot of cloud. So we're not taking the most pristine data right now, unfortunately. Jupiter is a little bit higher than the moon, but you can see the waves of cloud rushing through. We're able to observe through that because we're in the infrared, but it's going to distort our image, what we can see a little bit. Moving down to the bottom left-hand side, you can see Jupiter on its side. And that image is not as clear as it was maybe an hour ago, because this cloud is sort of catching up with us. So we're battling the clouds a little bit here. But what you're able to do is still take data through the slit, that black line in that image. We've just moved to the sky. We're taking a lot more sky frames than we normally would because the variability is so high. In the middle at the bottom, you can see that there's a weird image where everything is blinded. That normally is the off-axis camera. It's an incredibly sensitive camera that looks at really weak stars, and we've moved to the sky, which means Jupiter's moved away from our frame of reference into that guider. So basically being blinded by Jupiter right now, can't see anything at all. So in the middle bottom is what the telescope operator looks at to try and figure out where we are. And then if you go to the top middle, you can see the spectra coming in, and they're pretty messy right now because we've got a lot of cloud, but hopefully with some diligent care, we will be able to take that information and use it, because once we move back to Jupiter, you'll see we're pointing almost exactly where Juno is passing its radio beam through the planet back to Earth. And so we should be measuring the occultation of that radio signal and measuring in situ, as close to in situ as you can manage, measurements of the total electron count at the same time as James Webb is imaging that region from space above all of these terrible clouds and getting very, very detailed information, but over a very small area, much smaller area than is covered by our slit with Keck. So Keck gives us some really good broader context of what is going on in the ionosphere, as long as we're able to pull that information out from all of this cloud, which will be the fun job of a poor student at some point in the coming year, I imagine. And so that's what you can see here. What I will do now is share the imager itself, which is not showing anything particularly interesting right now, but hopefully will again show something interesting once we move back to Jupiter.
One thing I thought we could show is this. So the Juno is talking to the Deep Space Network.
Yes.
And you can monitor what a Deep Space Network is talking to at any given moment.
Oh, yeah, let's do that. That sounds good.
I'll send the link to you, Tom.
While you switch across, just a really naive question. Logistically, when you're, obviously you've shared your screen here, but when you're working at home or in the office, how many screens do you actually have? Do you have like 15 to cover all this information, or?
So moving to Northumbria, I got cheeky with my requests, and I got a very, very nice monitor. And so that's what I was sharing. And it's unique in being able to show all the panels at once. Yes. In the past, it was really hard because at Keck, when you're at Keck, there's 4 separate decent monitors, right? So you need 4 monitors, and it's really hard to get 4 monitors in the one room if you're not dedicated to doing just astronomy all the time. And so it's one of the reasons why observing from the UK is harder, because ultimately you basically have to have remote desktops and switch between them. So it makes it much harder. So one of the joys that I have now is that I'm able to see all the panels at once, much more like the experience of observing at the telescope. But it's unusual to have that. It's the first time I've had it ever. And trying to squeeze 4 screens into 2 is always a bit of a nightmare. Some of these screens we look at less, and some of them we look at more, right? So we look at the instrument panel when we're setting up, but generally you don't need to see that all the time. Although, of course, when it all goes wrong, that's where you find out it's gone wrong. So if you've not got sight line on it, it can be difficult and frustrating. And then some of the stuff that the telescope operator looks at, you don't need all the time. So with 2 screens, you can kind of get away with the 2 panels that are most important, but it's not necessarily useful. But yeah, I mean, it's difficult to do these observations remotely. Generally speaking, you want to do them with a setup that can control and run things. And if you're able to be at the telescope, it really helps with that, because even here with a really fast setup, you have about half a second delay, quarter of a second delay, because of the light travel time between you and Hawaii. So all of these things become considerations. So
can I share my screen quickly?
yeah, you share a screen. I mean, just before you do that, you can see now Jupiter appeared, and we have moved the slit over to the dawn side. So that's how we know that we're looking at the same region as James Webb. The James Webb is looking at a bit of the box, basically at the one end of this slit. I will stop sharing now, and you can share.
So I'll just show you this. Firstly, this is the Deep Space Network satellites, and it shows you what spacecraft they're talking to. So I have 2 dishes in Madrid receiving the Juno occultation data, but we also have a dish in Goldstone in California talking to Webb, and we just received confirmation that the first observation is indeed collecting from the observatory. So we're getting data right now, confirmed.
That's so cool.
Yeah, that's nice.
Wow, that's really amazing.
It's all happening. Plus, of course, the ground-based data, which is... And the RTF, we should start on the RTF in 3 minutes.
Okay, interesting.
I feel like we should break out a bottle of champagne or something.
Yes.
Good idea, right?
Yeah, we should.
Cocktail hour somewhere.
If we were all in the same room, it would be more meaningful.
Yeah.
Yeah.
I've got a cup of tea. Will that do?
I got a flapjack.
So I have got a third laptop now on my desk, so I'm going to be logging into the Zoom on my ITF at the same time as Keck, at the same time as you guys. It's ridiculous. I don't know why I'm doing this, but it's useful to be able to talk to everyone in some way or another.
I can support the RTF though.
So yeah, I mean the sky is variable, but right now, if you there was posted in the stream earlier was a link to this sky cam that we have that we're looking at. I can see Orion appear behind the clouds right now, so it's intermittent, but there are gaps in those clouds, which is really positive. And so hopefully we will get some good data. The image coming through is better now. I will share that again.
Log into the Zoom for the RTF.
I just shared a link that has the stars over the sky, the night sky at Mauna Kea, and I'll send that to the attendees as well. That was something that Dr. O'Donoghue shared. It's pretty cool.
So I haven't logged in yet, but I can see James O'Donoghue and Katie Knowles on IOTF now talking with the telescope operator. So they're in Japan contacting a telescope about 150 meters east of the Keck telescope. And Luke is in Boston talking to the Keck telescope to the west, while we're looking at all the information in the UK, streaming out to Hawaii. It's a pretty insane world that we live in, I think. So we will talk with them in a little bit. We're going to let them have some time to set up and get going on the telescope.
Oh, there you go.
And in fact, at some point, I can actually show you what they're seeing as well. Right now, you can see Jupiter is rotating. So we've got this lovely view of the planet, and the slit is cutting out over the dawn side, which is the location that
this star here that I just imaged as a guide dog was a 8.2 magnitude, so it was already
Like, chills. Like,
but the spectra is looking decidedly ropey, but that's fine. I stop sharing for a second. So there's nothing happening on IRTF just yet. I think the instrument change is happening as we speak, or is in place. In fact, they may be focusing up now. And I can show you that in a second. Great. Okay. I'm sorry to everyone who's just staring at us, looking left and right, but there's a lot going on right now. Great. I don't know if there's any questions. I saw a question that came up earlier, and I had a little poke to see whether I could answer it.
I just
It
have
may have
to
been
share
answered.
the video. Just to show the observation.
Oh yeah, sorry. Where am I? Over here. So this is what James Webb has started doing now. We're taking data with James Webb. We've seen the confirmation of that from the data collection system, and we've even seen information showing one of the California radio dishes talking directly right now to James Webb, providing it with information. It's the very first frame of this long cycle, so you can see that the planet itself is being moved so that we're basically following a clock-like shape around the planet. And the reason why that's important is the layer that we are interested in is the uppermost layer of the planet. Now, what we've seen is that when we're looking at the aurora and the lower latitudes, we can look at the disk itself. We can look at the distribution of light across that disk, but often it's very difficult to pull out specific information, especially because we want to compare it with Juno. So the real aim of the James Webb data is to try and look above the limb and see in profile the distribution of the ionosphere above that limb. What we found from our very early observations with Keck and now with James Webb is that we're able to see light well away from the planet itself. So the H3 plus and the ionosphere is fading away with altitude to much, much lower densities, but we're still able to pick up that light and emission well away from the limb of the planet. And so that's really interesting because it's giving us this view that actually ties in with some of the orbits of Juno. Juno is at about 8,000 kilometers when it's closest to the planet. it's doing really close in orbits and measuring things in that region. And our frame of image with James Webb will extend to about 10,000 kilometers. So if we were able to resolve Juno, we would see it in the frame of view. So we've got these very, very detailed measurements in situ from Juno that actually fly through the atmosphere. That's at a different time, but that again ties back to the occultations it's going to be taking now. So we've got this wealth of new information where we're able to use the occultation measurements to get very specific values for the ionosphere in a view directly with Earth, which it's doing right now, as we saw. But at the same time, later in its orbit, it's actually going to be flying through the ionosphere at these altitudes. So by using James Webb, we can hopefully start gluing all these separate different pieces of information together. And with James Webb and with IRTF, we can provide broader context to that. So for Keck, the detailed information we're going to get out is going to give us a really detailed view of the brightness of emission above the limb and, you know, around onto the disk, and follow those kind of shapes as the planet rotates a bit more than James Webb is able to do. And then with IRTF, we've actually been observing the planet for the last month, and we've had a sequence of observations every other night. We've taken about 2 hours of data of Jupiter. So we have multiple nights over the past month where we've seen the changing conditions in the ionosphere leading up to tonight. So hopefully there's a huge sway of context for that information, where we will try and understand all of the different inputs that Johnny talked about into the aurora, but also how that washes down equatorward and how it affects the ionosphere and atmosphere. And it's a lot to take in. There's a lot of information there, but the hope is that we can try and start getting a much broader view of the processes that are happening as a result of trying to combine these data sets in a way that hasn't never happened before.
I keep seeing really big smiles on Paolo's face in the room with Henrik as they're looking at their screens about their JWST observations. I just wonder if there's anything that they have to share with us. Oh, it's interesting looking at their faces as I guess stuff. I don't know if they're receiving anything.
So what they're seeing is colleagues in Japan taking the first star spectra. So hold on, if I share my screen, if I can do this. I've never done this before. This is mad.
Oh.
I'm going to share my screen so you can see what I can see, which is Keck. And then I'm going to switch my desktop here, and now we're looking at another telescope. So this is IRTF taking some of that star spectra that we talked about, and that's taking the first observations of a star. So on the right hand side is the same kind of guide camera image looking at a star, and they're going to, you can see a thin slit, just like with Keck. It's a different angle because all of these instruments are built by different people and do different things, but they're broadly the same. So on the right hand side we have an imager, and on the left hand side we have the spectrometer, and they're taking some calibration data. So they're looking at the star and hoping to see spectral lines characteristic of the star so that we can calibrate the data later. And so they're waiting for the first of those to come in. So that is James and Katie in Japan running the telescope in Hawaii at the same time as Henrik and Paola in Leicester, talking to them to confirm what's going on, while Luke on my screen over on the right hand side is working with Katie and Max in Boston to do this other screen, which is the Keck data. And all the while this is happening, both Juno and James Webb is taking data as well. Oh boy.
Is that YouTube video of this, is that live? Is that still, because I can see the clouds have kind of gone, or is that updated recently?
That is live, and okay, so maybe there's a break in the clouds.
Yeah,
pointing slightly the wrong direction, so it might be that there's something behind us that is a bit more, but that is somewhat positive. It
Okay,
does
cool.
clearing up a bit. Yeah, definitely. Okay, so I don't know if there's any questions people have, or if there's anything you want us to talk about.
So it looks like the sky over Mauna Kea is clear. Is that correct?
That's the hope. Sometimes it's a bit difficult to tell, but the image you can see down on the bottom left-hand side, the imager from Keck right now, that image looks way crisper and nicer than it did about 10 minutes ago, right? You can see that Jupiter looking much cleaner in the sky. You don't have a fuzziness associated with the what we were seeing earlier. So it looks like, for now at least, some of those clouds that were over have blown away, and we're seeing through a much cleaner set of sky. This image is, you know, not being designed to be perfect for science, and it's certainly not as good as some of the things that we see from amateur astronomers, but it is a joy that we're able to get such amazing images, basically just by reflecting light off of the science instrument that we want to take the data on. So yeah, some fun stuff going on for sure.
We just have a few more minutes until Dr. Prosser joins us. I'm just going to email. Oh, she is with us.
Okay.
So we just have a few more minutes before we get started there. Happy to do a quick kind of what we're up to, who we are, and what is going on here. Been quite busy, very exciting. I had asked for champagne earlier because we started the JWST scan. So really excited about that. Hello. Hi, I'm Lucinda Offer, Education Outreach Officer for the Royal Astronomical Society. And we are here with the H3 Plus team, Professor Stallard from Northumbria University in Newcastle, Dr. Henrik Mellon in Leicester, along with Paula, his student. And I think we also have, do we still have Dr. Rosie Johnson from Aberystwyth? We are eyeing the ionosphere. We've heard already about JWST. What are ionospheres and why are they being studied? We got an update about Juno, looking at far ultraviolet auroras from Professor Nichols. And we're about to hear from the Royal Astronomical Society librarian, who has brought us and will share with us some of the things about Jupiter from our collection. So very excited to have Dr. Prosser with us. And of course, we are still observing from, I think, is it 3 different observatories, 2 ground-based, 1 space telescope? This is incredible. So we've got the Keck, we've got IRTF, and we've got JWST, and they're doing a fantastic job, and it's been very informative so far. And again, you can join us on Monday. Register with us via Evenbrite. You can go to the Royal Astronomical Society website for our events to see Ionosphere, eyeing the Ionosphere 2. So we're gonna have a second day. We're gonna, for the scan that's happening today for JWST, we're gonna see those processed images on Monday, we hope, fingers crossed. Sure. So for now, I think we're gonna bring on Dr. Prosser. Looks like she's setting up. And might have some things for us. So wonderful to have you, Dr. Prosser. She's our RAS librarian and hopefully has some really cool, fun stuff to look at regarding Jupiter. So hi, Sean.
Hello, how are you?
Excellent. How are you?
I'm really very happy to be here in the library, but also I've really enjoyed listening to all the conversations and seeing the observations earlier from the live stream, and just really blown away that this has been an opportunity for Tom Stallard and his team to share their telescope time viewing Jupiter using JWST and Juno and Keck. And I'm very happy also to take you back in time to, 400 years ago, when somebody else was using their own telescope, one of the first telescopes, and that was Galileo Galilei, operating in Tuscany. So I'm going to basically switch my camera around. And while I do this show and tell in the library of the Royal Astronomical Society, please, Lucinda and guests, just chip in just as if you're in the room with me. If you want me to clarify anything, go over anything, because one of the things about doing a live show and tell is that I don't have any labels or captions that I would show in the PowerPoint. So I'm going to mention the names of the people whose works I'm showing you as much as possible. But if you want anything clarified, or you might want to correct me, and I've got some questions as well as we go along. But let's go back to 1610. Now, this book, this is the title page of a book called Storia e Dimostrazione. I'm not going to read the whole title. I'm not great at Italian, but this is quite confusing perhaps. Why would I show you a book that is actually about sunspots, macchie solari, that Galileo published in 1613? Well, it's just a, you know, sunspots are so interesting. This has got an amazing series of plates of, you know, copper plates of his sunspot observations that he carried out very early into his time. But I wanted to show you particularly, because it's relevant to the topic of this live stream, some copper plates at the back of this volume where Galileo has shared his observations of Jupiter. Now, I had the pleasure of joining you all in July 2020, where I showed another very well-known book by Galileo called Starry Messenger, or Sidereus Nuncius. And at the end of that book, where he shows his initial telescope observations of the moon and the stars, he uses a series of diagrams involving asterisks and capital O's to show his initial observations of Jupiter and the stars that he was able to discover using his new telescope that were alongside. And I recently realized that this diagram is even easier to see, that where it's more a copper plate that's very similar to the original manuscript, his handwritten observations, which are, I believe, in the Galileo Museum in Florence. But you can see day after day the the engravings of his notes with Jupiter in the center and the changing positions of the satellites, the moons, alongside. And as I said, back in July 2020, and as many people have known for hundreds of years, Galileo had that amazing insight using his telescopic observations that Jupiter is its own mini system. You know, just as the moon orbits the Earth, Galileo has noticed that Jupiter had its own orbiting satellites. And as an exponent of the Copernican system, where, you know, the theory was that the sun and not the Earth was at the center of the solar system, he put this forward as, you know, some persuasive evidence. I'm not going to go into the whole life story of Galileo and the implications of his discoveries and the way that he communicated his work, and the fact that, you know, due to some of the ways in which he communicated his discoveries and his disagreements with the church, he did end up spending his life in house arrest, not immediately after making these discoveries, but yeah, it's definitely a fact that he had some curtailments to his freedom. Any questions so far?
I was wondering, Sean, I don't know the limitations of the technology. Thank you so much. It looks great. We can see the whole pages. Is there any way to zoom in to maybe some of those notes on Jupiter?
Yeah, I'll zoom in.
Oh, lovely. Thank you. Oh my goodness.
Yeah. Hope there's not too much of a shadow. Yeah, it's quite fine detail, isn't it? And I'm hoping that people aren't going to get too seasick as I do this. But here we are. In Latin, at the top, it refers to these as the Mediciorum Planetarum, the Medicean planets, because he named these 4 satellites after his patrons, the Medici family. Okay, he didn't actually name the satellites themselves, the 4 brightest moons of Jupiter. It was actually Simon Marius, his contemporary and rival, who named them after the 4 lovers of Jupiter, according to classical mythology. So it was Io, Juno, Callisto, and Ganymede. Okay, I'll move on to something else now. So Galileo, using the best telescope that he had access to at the time, was able to discover the brightest satellites of Jupiter. And that was in 1610. And a few years later, in the 1630s, generation later really, other astronomers were taking advantage of, telescopes with a higher resolution to see even more interesting features. So this is a beautiful book by an astronomer called Francesco Fontana, Novae Coelestium Terrestrium. And there are so many interesting things about this book. For example, it contained at the time some of the most detailed drawings of lunar features. But what I'm going to show you is a series of observations from 1630 onwards of Jupiter, where he, using quite a crude to our eyes nowadays woodcut, shows that banded feature. In the early days of familiarizing themselves with this planet, some astronomers sometimes saw 2 bands, sometimes 3 bands. I'll just keep turning the pages. There's quite a few of them. From a book history point of view, I do wonder, did the printer really dread astronomers coming up and asking for whole plates to be completely covered with ink in order to
Yes,
render them?
I wonder, did that black transfer to the page on the left, or is it the black bleeding through the page behind it?
It's a good question, Lucinda.
Oh,
I think it's both. Both is happening. Yeah.
Oh, but they're beautiful, especially to know that they saw this banding and took note of it.
Yeah. And they're also showing the different positions of their satellites at the same time. Okay. So a generation later, people are able to see even more details of the surface of Jupiter and other planets. Some of you may have heard of an astronomer called Robert Hooke, who was one of the founding members of the Royal Society, and he was most famous for a book called Micrographia, in which he shares his observations using a microscope. There's a really famous engraving of a flea that he drew. He also had a telescope and made some really detailed observations of lunar craters. And he made some observations of Jupiter as well. Now, this book that I'm showing you here, it's volume 1 of a huge atlas published in 1696 by someone called Johanna Zahn. And it being a kind of, it's more of an encyclopedia type work on physics and mathematics. And he was able to, in 1 page, present a number of historical observations of Jupiter. For example, in the bottom right hand, here is Hooke's observation of Jupiter, including a distinctive spot. And alongside, we have Huygens' observations of Jupiter. I don't have any observations by Cassini today, but Cassini is known to have observed a similar red spot the following year. Giovanni Domenico Cassini at the Paris Observatory in 1666. So at the time, or historians of astronomy in like the 18th and 19th centuries, looking back at this period of observation, refer to this as the permanent red spot, or the permanent spot rather. I'm not sure if they referred specifically to a color. And there were various schools of thought. Is this the same as the red spot, the great red spot that we see today? is it the same phenomenon that just went into abeyance and reappeared, or is it a different planetary storm or vortex? So,
Sean, before you put that book away, I was wondering, because all those observations are showing horizontal banding, except for one. And I wonder, is there any note on underneath that says to why that one's drawn diagonally?
So not actually beneath it. I'm afraid that I do not know where. Like this is a numbered plate somewhere in this book. They will be referring to figure 6 on, page 95. The series of observations by Grimaldi and Riccioli, 2 Jesuit priests and scientists who are actually responsible for our system of naming lunar features after astronomers. So, they came up with the Copernicus crater's name, etc. But yeah, sorry, Lucinda, I don't know why it's on a different orientation there.
Yeah,
but
thank you. Curious.
We can look into that because actually, as you pointed out, last time the live stream visited the library, we had a bit of discussion about the Great Red Spot. So I thought I'd bring out some more things. So I'll look into this for the next time we do this in 3 years' time.
We do have a quick question while you're switching there. Were there early astronomers that were able to determine the period of Jupiter's rotation? I guess maybe once an observation of the red spot, I wonder, or the spot, excuse me.
I don't know when they started to have really precise calculations of the period of rotation. What I will show you are some observations by one of the greatest astronomers of all time. That's William Herschel. This is basically a notebook, it says Jupiter. And this is like a fair copy of all of the observations he made of Jupiter from 1774 to 1811. Like one of the last ones is, I showed my son, I'm going to bring this closer. I showed my son and that's John Herschel, founder of the Royal Astronomical Society, and his mathematical tutor. So in 1807, John would have been a young boy. The shadow of the 3rd satellite of Jupiter in its passage over the disk, and we also saw the immersion of the 4th satellite at the time contained in the Nautical Almanac. I think at this time, William was really trying to get his son interested in astronomy, and eventually John did take over the family business, so to speak, and became an astronomer in his own right. So, really early on in his observation career, 1774, William was making his own telescopes, and he was basically doing his own thing as an amateur astronomer, just looking at absolutely everything. And obviously Jupiter would be of great interest. He speculated about its inhabitants and what the conditions must be like for them. Here we can see the orientation of the bands is quite similar to the orientation in that last engraving you were asking about, Lucinda. And yeah, they were very much preoccupied with measuring the rotation and the speed. So we mentioned the permanent spot that Hooke and Cassini saw. Did William Herschel, one of the most assiduous and dedicated observers of all time, see anything similar? Well, he talks about spots, but mainly, white spots or there's quite a few shadows of the caused by the transits of satellites across the disk, which people would, even today, obviously really preoccupied with. Let's see. Here in 1778, he says, the darkish spot in the white belt in the first quadrant, the air is full of smoke, bad for seeing. So yeah, weather is a perennial problem for astronomers, obviously. Yeah, so he's observing a spot, but and he sees 3 spots here in 1778. But it doesn't seem to be, I don't think I'm not sure if anyone's made a connection saying that this is the antecedent of what we know as the Great Red Spot today. What we can say is that in 1831, in the following century, that is when we start seeing traces of the phenomenon known as the Great Red Spot today. I'm going to fetch another book. I'll be right back. Right, so this is a book from 1831. It's one of hundreds of notebooks we have in the archives by someone called a German astronomer whose surname was Schwabe, and he carried out a campaign of observation of the sun to find out whether there was a planet X. People were speculating about the existence of a planet between Mercury and the sun, which was given the hopeful name Vulcan, which never appeared. But because of his years of observations, he did make a huge amount of sunspot observations, and he was the person who discovered the 11-year sunspot cycle. So, but he made other observations, and on September 5th, 1831, in this drawing of Jupiter, can you see in this dark band that there is a kind of notch?
Yes, I can see that. Yeah.
So this is known by people like William Denning, who is a major Victorian amateur astronomer of Jupiter. This is referred to as like the Great Red Spot Hollow. And so that was September 5th, 1831. And September 19th. You can see the same phenomenon again. Yeah.
Oh, yes. So,
yeah.
So it's curious, like it's formulating, but it wasn't visible.
Yeah. And on the 5th of November, again. So he didn't publish this at the time, but the Royal Astronomical Society awarded him the gold medal for his sunspot observation work. He couldn't come to any kind of ceremony. We didn't have award ceremonies in those days, but Richard Carrington, he of the Carrington event, the greatest solar flare ever observed, went over to Germany to give him the gold medal in person. And Schwabe was really touched by this, and he generously left all of his life's work to the Royal Astronomical Society for the benefit of observers. And that meant that people like Denning had access to these archives in the 19th century and were able to say, so this is where we first see traces of the red spot. Because when did it really become red and really really noticeable? Well, that was in the 1870s. There was an astronomer called W.S. Pritchett in the US, who perhaps made one of the first observations, but there was also an astronomer called G.D. Hurst in Adelaide in Australia, who sent a drawing to the Royal Astronomical Society in 1876. It being from Australia, it didn't arrive until 1877, but I'll show you, it's in the archive.
While you get that, John, I'm just going to share with you that a Declan Fleming on YouTube says they have huge love for you from a very grateful RAS visitor who got to see some of these in the flesh, thanks to you.
Oh, it's thanks to the Society and the Fellows for looking after these manuscripts and books for hundreds of years, and for having that public outreach mission. And thanks to Lucinda and Tom Stallard and colleagues for generously sharing, you only have a few hours of telescope time, and you're sharing that with, the whole world. And I think that's really fantastic. So G.D. Hurst, 1876, what do we have here? Okay, a normal day on Jupiter. I'm just going to turn the pages of, basically, our secretary, William H. Wesley, who's, he was the paid employee, asked for and received drawings by astronomers from all over the world. We have quite a few drawings by Hurst. Again, not many noticeable features in this drawing, but then, has anyone seen this before? It's I was looking at Sheehan and Hobbes' book on Jupiter, where they feature this.
That's an amazing illustration. They're showing the shadow of the moon about to cross the disk.
Yeah.
That's amazing.
Yeah. So once this reached the Royal Astronomical Society, there was great excitement, and we have like hundreds more of the drawings by Hurst and other astronomers from the 1870s onwards. But as you experts on Jupiter know, it was not a very stable phenomenon. Let me show you. So Nathaniel Green, an astronomer who is also a really phenomenal artist and illustrator, he published an article about the belts and the markings of Jupiter, and he gave the manuscript of the article to the library. Basically says library copy, and it being a manuscript, this is like a marked up plate where he shows the evolution from 1880 through 1881, 1882, 1884, 1885, 1886. So yeah, you can really see how the spot is fading, which he renders in these beautiful pastel drawings. We do have the originals here, but they were just a bit too fragile for me to shove under the camera at short notice. So
that an
elongated a quick tour. Sorry?
That looks like an elongated red spot.
Yeah.
It's quite large in that image. But those are fantastic. A quick tour. That was amazing. Thank you so much, Professor.
Any other questions? Just really showing me, Linda. Sorry.
Yeah. Looks like we got through the question from Q&A on Zoom. If anyone has any more questions, please feel free to put them in the Q&A on Zoom or on YouTube. So we just had that one question on Zoom, and a shout out to you, Dr. Prosser, for all the work that you do at the library, and for the being able to see them in person is amazing. How can people come and see any of these things in person at the RAS?
You can get in contact via the library. If you want to make an appointment to look at something specific, then I'll be very glad to hear from you.
Do they have to be a fellow?
No, you don't have to be a fellow.
Wow, I did not know that. So it could be anyone, any member of the public.
Yeah.
Amazing.
So we have group visits and tours as well. We'll be running open house tours on Saturday the 16th of September, although those tours are fully booked now. If any of you are anyone in the audience is a member of an astronomical society or another group, for example, you might be in U3A or studying astronomy, if you want to get in touch, I can, it's so great that we are open again, that we can offer group visits again for groups of up to 15, and we can check things out on a specific subject, or it could be, or you could just let me show you things that I think are interesting. But yeah, we have quite a few researchers coming to use the collections over the years. A lot of historians of astronomy, but people from other disciplines as well. people looking at the history of women in science, looking at the relationship between art and science. Yeah, lots of different disciplines.
Well, thank you so much, Dr. Prosser. Those were lovely. Thank you for sharing those with us. You didn't think you would fill 30 minutes, but it's gone by so quickly. I know. Did this, so you have much more to show about Jupiter. So, I mean, and if you want to visit the Royal Astronomical Society, as you just heard, you need to contact Dr. Prosser. You can go to our website at res.ac.uk to contact her and find out more about perhaps being a friend of the RAS or become a fellow of the RAS. But fantastic. Thank you very much. And just a quick check-in before we get into we've had some more astronomers join us from far away. But before we get to them, I wonder if we could check in with Tom or with Henrik, if there's any new updates that you want to mention before we move on.
So last time we were looking, there was a lot of cloud. It had a beautiful period where there was almost no cloud at all. We managed to get some really clean images and hopefully data too. I can now see a little bit more cloud coming in, which is frustrating, but we are in the B-beam for both instruments. But what I will do is I will try and get myself onto the screen again. If I share,
Henrik and Paula have their video up.
Do half of it,
Yes.
but probably not. Hold on, I'll just.
We have too many screens up. It's not a problem.
Right now, it's a bit of a mess. I was hoping to see if I could do a third of the screen, but I don't know if you can do that. But what I've done is, this is what we saw before, and I've dragged this in from that other screen. I'm hoping very soon we'll go back to the A-beam in our Keck data. Right now at the top, you can see IRTF taking observations. So this is an image from IRTF. And on the bottom is what Keck is seeing. And I didn't think it would affect me so much, but being able to see Jupiter from two different telescopes at the same time live on my living room desktop was pretty stunning. So for me, it's a pretty profound thing to see. It will flip back fairly shortly, I think, and we will start seeing both at the same time, which is just a bit jaw-dropping. And it's only jaw-dropping till you remember that you've got the best telescope in the world also looking at the same time. There we go. So on the left-hand side now, you've got the view of the same planet with two different instruments on two different telescopes on the same mountain, half a world away. The top is IRTF, and the bottom is Keck, and you can see that Keck, the slit is rotated up down mostly, whereas on IRTF it's east-west, so left-right, but you can see the same atmospheric features in both, which is pretty crazy.
Henrik, any updates from you?
Yes, exciting stuff. We have confirmation that the observations are taken, and some of them are already downloaded to the Space Telescope servers. So,
is your spreadsheet updated then, so it shows more?
Yes.
Oh.
Yeah. So we're on to the next set of observations, and the first set of observations seem to have been archived already. I can show you.
That's fantastic.
I have to update this. Yeah. So
Oh, look at that.
this was updated 2 minutes ago. So this is already downloaded from the spacecraft.
Excellent. Wow.
Selecting the next one and working our way down.
I just got chills. That's just phenomenal to be able to collect the data and already have it sent back and,
Yeah.
play safe in real time.
Yeah.
Since we've been observing this morning. That's incredible.
And we can see that the Goldstone Deep Space Network is talking to Webb, and the Madrid one is still talking to Juno about these occultations. Very cool.
So we've got some special guests with us who have come in all the way from Japan, but it's easier to do via Zoom these days. But we've got Katie Knowles, it looks like, and I haven't even checked in with them if they're ready to go to turn their camera on or anything. I'm just going to talk about them anyway. But maybe Professor Stallard can, because Katie's your student.
There we go. There we
Yeah.
go.
And Dr. James O'Donoghue, welcome. Thank you for joining us.
You guys are muted, I think.
I think that their mic is on, but I'm not sure if they're having any technical difficulties. We can see you. We just can't quite hear you yet. I show that your mic is on, but it's not receiving any sound on your end.
Can you hear us now?
Yes.
Sounds like it.
Hey.
Hey,
Hello.
thank you for welcoming us. Yeah.
You want to tell us what you've been up to, what's going on? I mean, how exciting. Katie's all the way in Japan. And what year are you in your PhD? Can you tell us a little about you, Katie? How about that?
Yeah, sure. I'm in my first year of my PhD at Northumbria University, nearly my second year as of the start of October. And I'm here in Japan working with James, who works at ISAS for JAXA, which is kind of crazy. I was previously at the University of Leicester, and pretty much all my research experience has been in this wonderful planet Jupiter. But that makes me by no means an expert.
And you guys are from Japan. In Japan, Dr. Donoghue, why don't you introduce yourself? Tell us a little bit about you and how you're supporting Katie and her work. I'm assuming, Katie, you're the PI for this research, and are you an advisor, Dr. Donoghue, or what's your role?
Yeah, I'm one of the advisors. I'm not the main one, but yeah, Katie is over in Japan working with me in the Japanese Space Agency, JAXA, to look at some Jupiter data. And it just so happens there's a big observing campaign at the same time. So we're very busy over here looking at all the data. And yeah, Katie will be here for about 3 weeks and touring JAXA and meeting lots of colleagues and having a good time, getting a lot of work done. And and we're basically doing the same kind of work. We're looking at Jupiter's upper atmosphere with IRTF and combining it with all the other data that we've seen earlier today. And the observations are going really well so far. We thought the weather might be bad, but actually it's coming up pretty good, thank goodness.
Yeah, if you see us looking distracted, it's because we've, at the moment, as Tom just gave you a glimpse of, we've got 2 windows which display IRTF and what's going on. So we're constantly checking if everything's going okay. Jupiter hasn't disappeared on us or, exploded or anything.
No. Yeah, it's always so interesting to see your faces, and so can see that you guys get excited about what you see or concerned about what you see, but we don't get to see your screen until you share it with us. If you wanted to share your screen or anything, I'm assuming it looks similar to what Professor Stallard has been sharing with us.
If Tom could share the screen.
Yeah, I can share my screen.
Thank you. That would be great.
We have about 3 different laptops here to juggle with this. I think Tom has a mighty huge screen that can do it all in one go. This is really good. Yeah, the stuff that you'll see is it looks very purple. That's Jupiter looks purple and white in this image, as you're about to see, I think.
Right now we're on Keck, but I will move us over.
Just gonna quick.
Okay.
Magic.
Thanks, Tom.
To IRTF.
Yeah. There we go.
Hopefully you guys can see that.
Yeah. Yeah, on the right there we have Jupiter, and this is in infrared. So we can't see infrared, so normally we basically a black and white image, but we can decide ourselves what kind of colors to represent black and white. So we have white, but we go down to purple and everything else just to keep it funky and interesting. And you want to talk about the observation pattern, or?
Yeah, I can talk about the observations. So yeah, like James says, on the right, we have Jupiter. That's in real time. And then you should hopefully see on this big purple thing we promise is Jupiter, there's this black line. That is what is called the telescope slit, although it's just disappeared now. But that is actually where we are taking spectral measurements of Jupiter, and you can see it's lined horizontal. You can't see right now, but it was lined horizontally with the planet, so it's lined east-west, and we're scanning from the North Pole in this case tonight, going down in small steps all the way past the equator, and it'll be down to the South Pole. And we take a couple of spectral images of Jupiter before we then go to a random area of sky where there is like no bright objects, there's no Jupiter, which is what you're seeing now. That's why Jupiter has disappeared and it's all quite dark purple. In a sec, we'll go back to Jupiter and we'll carry on taking measurements, and it'll repeat a cycle. Oh, there we go. We're coming back to Jupiter. But yeah, that's the whole point of these observations, is we're trying to scan Jupiter from pole to pole in a relatively short amount of time in terms of telescope observing standards. We only have 2 hours to do all our telescope calibrations and actually to observe Jupiter, which is why we're constantly keeping an eye on everything and checking that everything looks okay.
Is your 2 hour window is happening now?
Yes.
Yeah.
Oh my goodness. Well, thank you so much for coming. I thought you guys were going to be done by now and then would join us. So wow, that's
this is it's prime time. It's luckily a lot of the routines they're kind of automatic. You just have to look at them every so often in case they've stopped for some reason. So it's automatic thanks to code that is pre-programmed in that we made earlier on, like a recipe basically. But it's it's scanning from pole to pole and building up this pattern, this kind of global map of the upper atmosphere, and providing a kind of a global context to the observations that are more pinpoint by James Webb and Juno spacecraft. Yeah, this is a full-scale assault of Jupiter. All the telescopes are pointed at it right now.
So is that a script that you or Katie had to write, or you were writing?
That's Tom, isn't it?
That's all Tom.
Tom.
Yeah.
Thank you, Tom.
Yep. Yeah, Tom wrote the script for the telescope.
Yeah, quite handy. Then so you guys have to just monitor it and make sure that it's collecting what you want it to collect and that there's no issues. There's not much you can do if there's an issue, other than we've had an issue with the primary mirror in a past observation, so I know that you work with the people on the ground.
Yeah, so there are little issues that we can handle, and but yeah, we don't expect many issues. Not with this telescope. It's a real workhorse. Really not very problematic, I think. But we do have to keep an eye on things. The main issue, I guess, is whether or not we can keep Jupiter in the center of the image all the time, because telescopes tend to lose track of planets and things like that. They drift away. So the green box that you can see there, that's basically, it's called a guide box. So that's the computer it understands that's what we're trying to guide on, and it will try its best to keep that pattern of that image inside that box. And in other words, it will keep the telescope pointed exactly in that position as best as it can. And that's how we fix our position in space on the planet. We have a lot more to sort of deal with on the ground compared to James Webb. You have things like humidity and wind, and the temperature changes can cause the telescope itself to sort of bend slightly, just ever so slightly, and all that kind of thing, stretch and bend because of the thermal expansion and contraction. And so there's little things like that, I suppose, that add up and could make the guiding slightly off. But in general, it's pretty smooth. Yeah, we're getting some good data. We've been scanning from top to bottom, and there's a little white little storm that you might be able to see. Oh, you see the great red spots on the bottom right, actually. And then there's a couple of other big storms that are reflecting a lot of light in infrared. That's why they're bright there. And we've crossed over that region with the spectrometer slits. In other words, we've taken data of that little storm. Maybe there'll be something interesting there. We'll see in a few months or weeks or days. And yeah, that's what we're doing so far. And I guess we started an hour ago, and we're 2 hours in total. So yeah, pretty much 50% of the way through, or nearly 50% of the way through. And you could probably tell that's the case, because we started at the top of the planet and we're nearly halfway down right now. And we'll keep going down all the way to the southern pole as well. So there'll be quite a big, we'll see the whole face of Jupiter basically in these observations.
And we got the great red spot on the limb. Is that right?
Yeah.
Yeah.
We just missed it.
Yeah.
Ah.
Yeah. So close.
So close.
Yeah. In the past, we've looked at the great red spot and we've seen a lot of emission. A lot of it was very bright above that region. The upper atmosphere that we studied was very, very hot at that time, and we think it was because of the great red spot itself sending basically sound waves or gravity waves up from above it into the upper atmosphere that kind of break in the upper atmosphere like waves crashing on a beach, and that could heat up the upper atmosphere above it. So that's why we're interested to sometimes record the great red spot and other storms that you can see. We think that the auroras are the main source of heating globally in the upper atmosphere of Jupiter, and but we think that there might also be some extra heating coming from these other storms dotted around. But so far we've only seen it once above the great red spot. Other observations didn't show it, so it's still up in the air whether or not that's the case, I think.
Katie, do you want to talk about how these observations helped us test what James just said, specifically that we think that the temperature is mostly driven by the aurora?
Yeah, I can talk about that. Yeah, so just for a bit of context, I'm the principal investigator on this observational campaign. So I wrote the application for the telescope time with the help of everyone you've spoken to on this webinar. And the whole reason behind these observations, we are monitoring Jupiter across an entire month, which for the sun is a complete rotation. And we are observing Jupiter every other night for 2 hours. But in actual fact, we're going to have a total of 17 nights of observation, which I think James said was about 10% of this observational semester's telescope time.
Yeah,
I think that's right.
Yeah,
which is kind of crazy. So it's a huge campaign, and like James said, we believe that the aurora are the dominant heating source for heating the rest of the upper atmosphere on the planet. But we need more concrete proof, which means we need more observations, which is what this whole campaign is for. So the sun is very, very variable. We have weather here on Earth, but there's space weather out there driven by the sun. And so the sun is very variable across a month, so a solar day. And even though Jupiter is very, very far away from the sun, Jupiter can still feel those space weather effects. And so we're trying to monitor the temperatures of Jupiter's upper atmosphere over a solar day and see how it varies with the sun's activity, to try and prove, is the aurora heating this giant planet, and is this heating enhanced by the sun's activity at all? So that's the goal, as well as other fun science we'll hopefully get out of these observations, fingers crossed.
Yeah, I don't know if you saw Rosie's, Dr. Rosie Johnson's talk on ionosphere. She showed the video, I think, James, I don't know if that was a video that you made, about the waves of heat, I guess, that get distributed from the aurora. I don't know if you have that or can show that again, or if
Yeah.
that was, go ahead.
If it looks very red, that was probably mine.
Yeah, or if Rosie,
Yeah, it was your video. It was
Okay.
yeah, you know the one.
Yeah, I know. Yeah. Yeah. That's what we were thinking is how it is how the heat is distributed from the aurora down to the rest of the planet. It's basically blowing really, really fast winds away from the aurora in the polar regions to the rest of the planet. It's kind of the opposite thing going on as it would be looking at the lower atmosphere, the cloud tops that you can normally see at Jupiter, and even for that matter, Earth. If you look at the Earth, usually the equator is the hot part. But if you look at the upper atmospheres of planets, generally it's the polar regions that are very, very hot because the aurora are causing a lot of electric currents and things like that to run through the upper atmosphere, and it causes a lot of heating through lots and lots of collisions. So that's pretty much why the polar regions are very warm. But away from the poles, yeah, it should be pretty cold if you only use sunlight alone. Jupiter's upper atmosphere at the equator, for example, should be about let's see, 200 Kelvin or so, something like that, which is only about -50 or so Celsius. But instead, it's measured to be many hundreds of Celsius in temperature. And so, yeah, it's really, that's kind of the bedrock of a lot of our work. It's the one of the biggest mysteries is, you know, why, and it's very simple as well. You know, why is it so hot outside of the auroral region? And we think it could be simply solved by the auroras spreading their heat around the planet. Now that actually happens at the Earth, and that's fine. The auroral heat is spreading from the polar region around the rest of the planet, but Jupiter and the other giant planets, they're rotating very, very fast. So the wind speeds on those planets are very, very high, and they actually act to stop things from traveling from the pole to the equator. So if you're trying to move your heat away from the pole and put it down to the equator, you've got to go south or north if you start from the south. And the main thing that we thought was stopping that was actually these winds that are blowing kind of sideways around the planet. And so what we're finding is that maybe the heat is spreading and it doesn't, these winds aren't strong enough to stop it. So we're not really sure what the process is that is allowing that to happen. It might be that the winds that are going sideways that are keeping the heat confined to the polar region are a bit weaker than expected, a bit slower. It might be that the auroral winds are a lot faster. Something is happening. We don't know what yet. We're hoping that by this full-scale assault with all these instruments and telescopes looking at the same time, we'll be able to get a nice kind of 3D picture of what's going on. Yeah, I see the movie here. Yeah, I definitely made that. Yeah. And there's actually real real physical models that for Earth that show this kind of thing happening for Earth, but we just didn't think it until recently that it actually occurred at Jupiter as well. But it seems to. Yeah, I probably should have made that video loop or something. It's so small. Yeah, so this is your infrared eyes. If you were looking at the upper atmosphere, it might look something like this over the course of days and weeks. We previously have seen a big heat wave, caught it in action coming down, which is what this, actually not this movie shows, but we've caught a big heat wave in action coming down from the pole, but we've only seen it in one observation. So hopefully with the observations that Katie has got here, 17 separate scans of the planet, we might see these heat waves in some of them on day one. So on a Monday, you might see this big heat wave in a certain position on the planet, and then on Wednesday, you might see it in a new position, move further south, and then we can estimate how fast it was going, because we don't really know right now how fast these things could move away from the aurora. So there's a big scope for learning a lot about basically upper atmospheric weather and climate in general from these observations.
And also, with like, as well as all like this like fundamental thing we're trying to find out about what is heating Jupiter's upper atmosphere. What has been a really happy coincidence with these observations is that we are bracketing Juno and James Webb, so that, yeah, like James said, if we see something a couple of days before Juno and James Webb, which all the Juno and James Webb scientists are like, what is going on with Jupiter? We're able to offer that broader term context to help provide some context to their observations as well as our own.
Yeah, that's right. If James Webb sees something of interest today, then we can look at that same region in the past and actually in the future and see what how it went, what was it like before and after? Was it a very unique event? That kind of thing. Yeah, that's what the context is all about. Yeah. So we have context by tracking the whole of the planet. We also have context in time by looking at a really long time window as well. Yeah.
So I think Henrik said he was changing the guiding. Maybe we could go back and, I don't know if he's already done it. He's very efficient, so he might have already done that. Nothing to see here. So
Yeah. So
I changed it to the south.
Well, thanks, Tom, and thanks, Henrik.
Yeah, thank you.
My pleasure.
Yeah, so what Henrik has done, you can see the green box on the south of Jupiter right now. We were going from north to south, and we were using the northern part of Jupiter to be the guide, but we were moving further and further away from it to the point where Jupiter was moving off the screen. So now we have to switch to the south and pick this feature for the telescope to guide on. It's very, very clever that the telescope can guide on like a part of an image of a planet, I think.
Yeah.
Typically what happens is people are looking at something a lot smaller than Jupiter, like a star or something like that. And you can easily guide on something like that because it's very small and very pinpoint, and the telescope knows what to do. But typically larger telescopes aren't able to easily stay on target with something like Jupiter.
Did I run the macro? Oh, someone is running the macro. That's good.
Is it running?
No.
Not yet.
No. Oh, got it.
Okay. There we go.
So okay, that was the last AB frame.
Gotcha. Yeah, so we're the script is now running again to go from the equator to the south over the next nearly an hour or so. Is it? Okay.
And how's Keck getting on?
Yeah.
Whoop.
Whoa.
I haven't checked in with Keck recently, but everything looks pretty good. The spectra coming through, you can see the planet quite cleanly. There's some light cirrus washing over in Mauna Kea right now. So it's not perfect, but you can see that they're actually not a dissimilar location on the planet to where IOTF is. If we could pull up, if I go to IOTF and pull up IOTF and over, we should be able to compare the two once we are back. You can see that down in the bottom bottom left-hand corner here, we're cutting through sort of sub-equatorial region, which is just about where you guys had gotten in your scan as well. So there, it looks like there's going to be a point at which we get light into the spectrometer from both spectrometers on both instruments on both telescopes, basically on the same bit of the sky, on the same bit of Jupiter at the same time, which is pretty awesome. They're the two. In fact, right now they are very close to each other, so that's pretty nice. Some direct comparisons that we can make between the two, because Keck is a bigger dish, it can gather more light, but IRTF has a much broader wavelength range, where we can look at many more lines. So there's a lot of cross comparison that we can do that could be really, really interesting there. Keck looks good. They have a lot longer, of course, than IRTF do. So we're going to complete a scan here as quickly as we can so that we can get all the data we need. If you look down at the bottom here, you can see what Jupiter looks like right now. So the aurora is actually starting to come up in the north. So we should be able to see the aurora in the north towards the end of the night. If we have a little bit of time, at the end of the scan, we could grab some of the north as well, but that will depend on how well we do. It seems like we're moving a little slowly today, so it's unlikely we'll get to it, but we will certainly do that with Keck at some point soon, I think, because that's where we're going with James Webb, right, Henrik? We're heading up that way.
That was going to be my question. So right now we should be observing latitude on the dawn side, 65 north. Can you indicate what that is on the Jupiter thingy?
Okay.
10.
I think this is in steps of.
There's some nice labels.
I did. For some reason, it only works when the aurora isn't there, and when the aurora is there, it always collapses. I haven't fixed my code yet. I think that you are going to. What did you say? 60?
65.
So it's going to be around about here.
Perfect.
So right now, James Webb should be just looking at the aurora on the limb of the planet, cutting through this auroral region here, which is really nice. Yeah. And we'll see a little bit of the main oval stuff above, and then some of the dark region inside, potentially. Should be really good.
Yeah. Yeah, this is great. I'm getting, 65.
Read. So Lucinda, if you could like go to the second or third frame of the movie. I think it's the frame after, yeah,
65.
one back.
So
there we go. That's where we are right now. Fun.
exactly. Yeah. And that's only the fourth observation out of 36.
Amazing.
Yeah, this stuff seems to be appearing on the server as well.
That's great.
Thank you to Dr. James Donahue for this animation.
Oh, you're welcome. I just stole the images from James Webb and stuck them together in a video. But yeah, it's quite an amazing experiment, I think. Yeah.
So one really cool thing that Henrik pointed out is we're interested in this box. This is the science that we want. But James Webb is taking all of the data right now. So all these other little slits are also taking data right now. And one of them right now is on Jupiter. So for completely free, we get this weird little sideways slit view of Jupiter. So the one that sits right there, yeah, that one is giving us an extra piece of information. So completely by itself, accidentally giving us probably the 4th or 5th best spectra ever taken of Jupiter's ionosphere. So that will be a fun extra resource, because that's looking down in the same kind of region that both Keck and IFTF are looking right now as well. So there's even more opportunity for cross comparison there, because those will all cut through that same equatorial region at the same time and give us some really interesting kind of comparative stuff that we can do, really trying to understand what's going on there.
It's hard to believe that it was only under a year ago that we saw that first image of Jupiter from James Webb.
Yeah, absolutely. And you know, it's easy. I think you might imagine that we would be less than effusive about it because we're, you know, diligent scientists that are trying to understand the deep meanings of the universe. But we were actually at a meeting for the magnetospheric community at that time. The first image came down. The image came down in a really weird way because, as I said earlier, the very first images they took of Jupiter weren't really interested in Jupiter as an object. They were really interested in how well James Webb could deal with bright light and looking at weak signals. So it was looking at the moons around Jupiter and comparing it with this really bright source. So they took a lot of observations of that. And so the very first the very first release of information about that from James Webb, it was in about 14 pages deep in a document about dealing with saturated light and dealing with scattered light on the instrument. So it was this very technical document that was describing how well James Webb has been able to calibrate its light leakage. And then in page 14 of that document was this amazing image of Jupiter. And so we managed to dig it out and find it, and we threw it up at a break at the magnetospheric meeting, and basically had an entire room full of magnetospheric scientists just staring flabbergastedly at the screen, trying to understand what they were looking at, because we were all just completely overwhelmed by the kind of insane images we were seeing. So that was a lot of fun because we kind of got to give them a taste of this new data that we were going to get and what the profound changes. And even in that data, you could see this kind of crazy level of detail that you would never expect to see normally.
Is it possible to put the OG image of Jupiter from James Webb with the labels on, or the purple one? Yeah. That was when we saw that, we were all floored, and we were trying to understand what we were seeing on the outside of the planet, the outside of Jupiter at the time, all the way around the edge basically. And there's a lot of debate, you know, what is that? But the image alone can get you pretty close to figuring out what it is, but we really needed to split that light up spectrally, like a prism, like we're doing with this new campaign. Yeah.
But this isn't quite the OG, right? Because this is multiple filters put together to give you a clearer picture of what's going on. And it's been worked with by an artist to make it really pretty. But it was something like this, wasn't it? It was certainly this slice of light along that dusk limb and the brightening. And what's really important for me is that you can see it bright and then it dims right here. It gets dark here. So it means that there's stuff going on in the upper atmosphere. There's variations that you're actually just seeing in an image like this. And we took a long time trying to figure out exactly what we were seeing in this image in a scientific basis. And it's actually a weird mix of the neutral atmosphere and the ionosphere sort of pulling out that information. So there's all sorts of stuff going on: the aurora, the ionosphere, the neutral atmosphere, maybe some lower atmosphere as well, and a lot of complexity to the kind of stuff that's going into this single image. But then on top of that, you've got the rings, you've got the moons. The aurora are so bright that they're diffracting in the image, which is crazy, just nuts. So real showcase of the kind of power of what you can get out from this kind of stuff.
This campaign will give the answer to what all of this stuff on the edge is, right?
Yeah.
That's the hope, right? And it's an observation in a way that we wanted to do for a decade at least. I always talked with my supervisor about trying to do this observation from Earth using a ground-based telescope, and it's just not practical. It's just so hard to do it, and the signal is so weak that it's basically almost impossible. But the idea has been there for a very long time to try and constrain and understand variations along the limb. So it's really good that we're getting an opportunity to try and break that down and get some real detail for the first time.
And we can rely on the weather being good at James Webb as well, which is pretty nice.
That's an absolute joy that we don't have to worry about that kind of thing. Definitely the case. So there is one other telescope, I believe, observing around about now, but I haven't got the specific details. But I believe Hubble is also looking at Jupiter today, and will be doing observations of the stratosphere. Whether that's timed exactly with these observations, I'm not sure, but it's certainly also supporting some of those Juno observations. So we may have 2 space telescopes and
I wouldn't trust anything in this box.
Juno.
Sorry.
No, it's okay.
Useless.
We are multi-zooming, all of us. So, do we have any questions? I'm trying to find the questions tab on here, but I can't see it anywhere right now.
So looking, there's nothing in the Q&A, and I'm checking out on YouTube. We have a few viewers watching now, but no questions there. I thought it might be a good time to show the program, because we only have basically less than an hour left in today's observation. Again, it always goes by so quickly.
Crazy, isn't it?
So hi, I'm Lucinda Offer, RAS Education Outreach Officer, and we are currently doing day 1 of eyeing the ionosphere, Juno, JWST, and Jupiter. And you can register to join us on Monday for day 2, where we're going to look at some images from today's scanning via JWST. It's a 22-hour scan. I think, how many hours are we into the scan now, Henrik? What, an hour, 2 hours? He's focused. No worries. You can answer it when you're ready, no worries. I'm just showing the program now. We've gone through all of these wonderful talks from the speakers who have joined us, from Dr. Johnson, who's still with us, I believe. Is Rosie still with us? Yes, hopefully. Professor Nichols visit us. Thank you, Professor Nichols visited us from Leicester, talking about far UV auroras, and Dr. Mellon gave us a JWST talk. So something when you watch this again and again, because the previous remote observations, I think I've watched them 10 or 15 times, and they're 6 to 8 hours long, and we just have usually so much fun, and they go by so quickly, and you're learning. There's so much content in them, in addition to all the data that they're retrieving, but just the stories that are told and the information that you're getting, looking into an academic astronomer, a professional astronomer, what they do, and the work that it takes to do to get the data that they need. We also looked at some illustrations from several previous astronomers with Dr. Prosser, our RAS librarian. And we've heard, we have with us Katie Knowles, the principal investigator, and Dr. James O'Donoghue visiting us from Japan. So visiting us, that doesn't even sound right. Calling in from Japan via Zoom. We are now in our last observation update from Dr. Mellon and Professor Stallard. So this is the time. If you have any questions about Jupiter, the aurora, whatever's, what it takes, JWST, Keck, IRTF, astronomy in general, now is the time to put your questions in the Zoom Q&A or on YouTube, and get those answered directly from the people who are here with us today. In about 20 minutes or so, we're going to be joined by Dr. Dunn at UCL, who is the manager of Orbits, original research by young Twinkle students, and we'll have a couple of classrooms or students joining us as well. We might have a classroom from Austria. So this is by far the furthest Zoom observation we've had, well, other than JWST out in space. But classes of students, we usually have them visiting us via Zoom in London, never from Austria. I think we have a couple of, you might have one in Northumbria, I'm not sure, which is where Professor Stallard is. And probably have a classroom from London joining us as well. So as well as Dr. Becky Parker, who does the IRIS, which is also a student-based research course that they offer, where they give students data, astronomical data, to look through and make perhaps new discoveries via this. And it's a great thing for secondary students to get involved with. So we look forward to that at 3:30 when we'll hear more about both of those programs. For now, I'm going to hand it back over to Tom and Henrik to fill us in on where we are now. And how many more hours of JWST scanning will we have?
We'll continue until 2 o'clock tomorrow afternoon, basically. So we're in our 4th observation out of 36. So there'll be a break between about 6 o'clock this evening till about midnight, when the telescope does something else. And then we'll go back to Jupiter and finish our scan along the limb. So the data is appearing on the server. So it's almost coming down, half an hour later after being taken. It's extraordinary. So it's all systems go, I would say. And the ground-based, we're getting data from both telescopes at the same time.
Looks like
Kyle's broken. All systems almost go.
Literally seconds after you said that, it just crashed.
Are you joking? No, you're not joking. Oh no.
You're good to go.
Oh, thank you.
Thanks, Craig. Just start the guide.
No.
Tom, I think you're muted, so.
Apologies. So I missed the fun bit, but only just. So you can see that on the left-hand side, we've got the spectrometer, and on the right-hand side, Kyle is now happy and busy. It's yellow and it's taking data. When it's not doing anything, it's green because it's ready to go. And every so often, if you're very unlucky, it goes red. And it just went red, which meant that it failed. So that does happen, and is one of the most common errors, and fortunately one of the easiest to fix errors. All that needs to happen is you communicate to the telescope operator that it's gone wrong, and they reset the server, basically. So it takes maybe 20 seconds, 30 seconds, which is why I wasn't even able to get the screen sharing up before it had been fixed. And so basically everything was positioned the same as it was. So they just had to hit go on the guider again, and it started acquisitioning data and taking data again. So it was a problem and is now being fixed, which is great. So these are the kind of things that just sort of throw up issues through a night. Sometimes it's something where the way you're taking data is problematic, and sometimes just the telescope breaks, and that's the reality of using the best telescopes in the world. You know, there's 1,000 different things going on all at once in these telescopes, and sometimes it's difficult to make sure everything works. We see these errors all the time, and it's why what we do is hard. A lot of the stuff that you're seeing right now in terms of observations, because we've done it enough, it's very easy for us. We just sort of set things up. We know what we're doing. We set the macros that we've pre-written and running, and then we're able to sort of just chug along and not do anything. But when you see a red light like that, suddenly the mood changes and you have to try and combat it. In that case, we knew what that error meant, and it was very easy to get it fixed. But, you know, you never know what's going to happen on a night like this. Sometimes the error will be very sharp, sudden and easy. If you remember back to the last time we did this live stream, at the start of the observation, we couldn't get the instrument working for an hour because the primary mirror, that was an unusual one. I've never had that issue before. And I was genuinely worried that we wouldn't get any observations at all that night, because there's just no way of knowing whether they'll fix it or not. And they did fix it. So
yeah, those are the kind of things that are really interesting. And to know how quickly someone on the ground, those support people on the ground or on the telescope, are responding and fixing things for you, because your time is precious, your observation time.
Yeah. And this is where, you know, we're so well supported by amazing staff at the mountain that really know these telescopes in and out. And so they're able to fix things really much quicker than anyone else would be able to. But we've all lost time to all sorts of things. There's an ever-growing list of reasons why we haven't been able to observe, that includes some crazy stuff. You know, we lost time on our last observing run last year because the volcano exploded and there was live lava streaming down the mountain that we could see from the summit. And actually, that didn't stop us observing. Shockingly, we were able to observe, but because they were very worried about volcanic volatiles in the air, they made the limits on things like humidity much lower than they would normally be. So normally the limits on how humid you allowed the air to be is about 80%, because after that it starts accumulating. But on those nights, it was actually about 40 or 50%, just to make sure that no sulfuric acid trapped in the clouds would accumulate, because you can imagine it would be very bad to have a sulfuric acid condensing on your mirror. So if we were observing at that time now, we wouldn't have been allowed to observe. So we lost some of our time due to an active volcano. We've also lost time due to earthquakes before now, and all sorts of other fun things. So these observations are in an interesting place at the top of a mountain in the middle of nowhere. But that is an active volcano, or often, you know, if it's not in an island, it's on a mountain chain somewhere, and mountains also very tectonically active. And then, you know, instrument failure, telescope failure.
What happens when that occurs? Do you get your time rescheduled somewhere else, or like you said, you've lost it?
Often you will just lose the time and you'll have to ask for the time again. We've had issues where significant amounts of time have been lost because of there was a shutter failure on RTF where literally the big metal shutter that rolls around failed, and because they were losing so much time, they were able to reschedule some of that. But of course, you know, you couldn't necessarily see the same targets. Generally speaking, if you lose time to weather or bad situations, then you just have to propose for that time again, which is great, except when you have an occultation with Juno and James Webb, and you want the timing to be absolutely perfect. And so sometimes you just have to bite the fact that you've lost that time. And often the observations we're sharing with you guys are those kinds of observations. We did a shadow observation, which had we lost that time, it would have been impossible, I think, to get that time back, basically, because, you know, it's a once in a blue moon observation where you don't necessarily have an opportunity to observe again later. So I think we finished that run, and so hopefully they'll be running another macro just to take us to the end of the night.
Got one question from our Zoom audience. AC wants to know if observations from the ground are you utilizing adaptive optic capabilities?
So I mean, we can do that. So adaptive optics is basically a way, if you remember back to Henrik's talk where he showed the moon wobbling, and basically the twinkling of the stars is that same effect. Everything wobbles as a result of the fact that the turbulence of the Earth's atmosphere just distorts the image. And that's the limit on what we can see effectively. You can correct that if you have a computer that looks at an object that it knows should be a certain shape and looks at how it's distorted over a very short time scale and basically bends your mirror back into shape so that that becomes into focus. So adaptive optics is a really effective way of correcting data. And there's two ways you can do it. You can do it on a star or an object in the field of view, so when you're taking data, or you can use a laser guide star. So often you'll see pictures of Keck or VLT with lasers coming out of them, and that's shining us a light into the atmosphere that scintillates, and then they're able to monitor that. It's a really effective way of correcting data, and it's really, really hard to do it for planets like Jupiter. Jupiter's so big that actually it's larger than the radius of that correction often. And so if you're correcting one side of Jupiter, the other side is far enough away in the sky that those distortions are less effective. But mostly it's that Jupiter's just super bright. So whenever I've talked to people about whether you can do laser guide star corrections, they're just very skeptical of it from the teams at the telescope, because they just feel like the object's so bright that they wouldn't even be able to see that laser guide star close enough to Jupiter to use it. And then Jupiter's really big itself, so and also Jupiter moves across the night sky quite quickly, so you'd have to find a star that's really close by and take measurements of that star in a way that allows you to what's called closing the loop. You close the loop on the correction, and it allows you to effectively correct for that atmospheric distortion. The one thing that we have been able to do in the past is use some of the moons of Jupiter. So although they're not really point sources, they are small enough that you can correct with them fairly effectively. And so we have done that with Io and Ganymede before now, not on Keck, which has an adaptive optics system, but the adaptive optics system on Keck is built into a very different version of this spectrometer. So you can do spectral measurements, but not the way that we want to do them. But on VLT, you can do that. So we have a very scant number of adaptive optic corrected spectra from VLT, but literally the bane of my life, effectively trying to get that to work. We managed to get it to work a couple of times, but you're looking at a moon that is orbiting and shooting across above or below the planet and trying to close a loop on it while also offset measuring the auroral region. It's really hard. So it's something I want to return to, but unfortunately VLT now has an instrument that's changed slightly, and so is much less effective for Jupiter, certainly. I think in the future we're going to use it more for Uranus and Neptune, because there it's much easier, but it's very hard. It's one of the most difficult objects that you can use adaptive optics on, and so it's a long journey to try and get these things to work in a way that's effective. It's a tool that we wish we could use a lot more, but it's just really hard, basically.
AC says, great explanation. Thank you, Professor Stallard, for that. And we just have about 6 more minutes for any other updates ongoing until we switch over to Dr. Dunn.
No, I think we're just coming towards the end of the full scan for what you're seeing now, which is IRTF. Once that's done, we'll close that down. IRTF will go off and do other observations and other targets. And in the meantime, Keck is still taking data, so we can switch back to look at what Keck is doing. I'm not sure what Luke has decided to do next, but we can have a look at that in a little bit, maybe. In fact, let's have a look now and see what, have a nose at what's going on.
There's some clouds coming over, so you can probably tell in the, there you go. You see on the top right, our images are getting a bit fuzzy on this side with the IRTF.
Just based on the spectra from Keck, I think they've gone back to the North Aurora and they're going to do a scan of the Northern Aurora now. That's how sad I am as I know spectra too well to know the things that well, just based on what you can see on this screen right now. And in fact, I'm right. Look, the images come back in and they're back on the northern pole of Jupiter. So they've decided that they've done enough of the scan down to support the specific occultation of Juno. Now the focus is on supporting the ongoing observations by James Webb, because as we said, we're moving clockwise around, and at the same time, the aurora is rotating into view. So if we take data with NIRSpec on Keck, we can scan through that region and maybe get measurements not only of the auroral brightness, but some of the things that Rosie was talking about in her talk, where we'll be able to measure the velocities of the winds and stuff like that. So that, I think, is what they're planning to do next, which is fun. But as you can see in the image on the far top right, there are a lot of clouds right now above Mauna Kea. So most observing would be stopped. Most telescopes wouldn't be observing at all at this point because it's just too thick. But because the aurora of Jupiter is so bright, you can actually do a lot of these observations in conditions that no one else is able to take any data at all, because it's just this incredibly bright torch light in the night sky. And I think that is a good place to summarize where we're at for now.
All right, wonderful. Thank you so much. I see clouds are covering Keck again. I'm going to bring on Dr. Will Dunn, who's here from Orbits. I think he had a question for the group. Go ahead, Will.
Yeah, so Tom, I just want to, I'm really sorry I couldn't join earlier. How do the observations look? What do you think we might see with JWST based on what you guys are seeing with Keck?
It's hard to know for sure. What I think we will see is things that we don't expect. I think that's the biggest message. We've got some really nice data, but of course, the one thing we're seeing that we won't see with James Webb is clouds. So we've had quite a lot of clouds tonight. We've had gaps in those clouds and been able to take some really nice data in the interim. But what we're really pleased to see is that some of the data is already on the servers on Earth. We have the data in having been taken, which is very exciting. And we were earlier able to see schematics of what the radio telescopes are doing, the radio communication systems are doing, and we're able to see the Juno occultation happening at the same time as James Webb was transmitting information back to Earth. So it's kind of a visual representation of this whole project in one static image, which is pretty crazy.
Amazing. Any insights into the aurora? Like, how are they looking tonight?
Well, we're just about to start scanning the aurora with Keck. When the first occultation happened, the aurora was slightly over the horizon. So as that comes into view, James Webb is going to move up into it. So schematically, we've seen that, the data being taken now is, right now, James Webb is looking at the aurora, the northern aurora of Jupiter. And we will have some scanned data from Keck shortly where we're able to see that. I see if I can see any, depending on them being able to see through those clouds, basically, and how thick those clouds are.
Okay, I see that we've got Dr. Parker with us, and we've got Declan Fleming here with us. We've got a few of your guests. Will, I wonder if you want to start off with maybe quickly telling us a little bit about orbits, and thank you for being here and bringing your students to share some of this with us. We really appreciate it.
Oh, no problem at all. I mean, thanks so much for letting us have some
Hey, that's Will.
Oh,
Right,
Becky, I think
hi.
you're, yeah.
Haven't got any
You're currently
sound.
live
Hold
on
on.
YouTube. So, yeah. Yeah, it's just, again, I think I said this when Henrik and Emma and Tom, you guys were doing the Uranus observations on the last live stream, but I just think this is super cool to share this process with the world. And yeah, and it's a really nice model. And I hope you keep winning all of these observations and keep getting to share them. Yeah, and it's amazing that Raz is providing this really great platform for it. It's cool.
I just want to say that, you know, something I've learned from you, Will, in the last year is it's super important not to just appear as some superstar that appears in the sky. I think this is a good way of doing that, because you can see us getting it wrong some of the time and just not knowing what to say some of the time. And you know, that's the hope, that we're able to emulate what you've been doing and say, oh, something's happening, I don't know what.
I think that's a really important part of it, right? It's an important part of breaking this paradigm that scientists have all of the knowledge and that we're all Einsteins, that we all have, a level of expertise or a level of intellect that just it's impossible for any human being to have. Well, I mean, probably someone on this call does have that, but I certainly don't. But I guess I'm very fortunate to be an astrophysicist anyway. So I'll talk, I guess I'll give like a brief introduction to orbits as a program. I was going to do slides, but I think actually maybe it's nicer to not do slides. But and then depending on so Becky and Simon Langton Girls' School students, I'm conscious that this has all been like a really last minute turnaround because you guys only got back to school 2 days ago. But if any of the group want to talk about their experiences on the project or share some of the work that you've been doing, then you're totally welcome to. But equally, this is obviously a very like last minute thing that we're putting on you, so no pressure at all, whatever you fancy. I think Sam from one of our other schools is going to talk about some of his observations of Jupiter's X-ray and UV aurora and how they compare. And I guess even for the scientists on the call, this will be the first time they've seen these comparisons of Jupiter's X-ray and UV and the amazing stuff that Sam and the students in his group have been doing on it. So I'm excited for that to be shared, but also obviously it's still in the process of being studied, so insights and stuff are really welcome. So orbits. Okay, so orbits is a program that's really about just making sure that everyone, regardless of your background, regardless of your race, your gender, your every aspect of you, that everyone can feel like they can be involved in science if they'd like to be involved in science. And so the way that we do this is we pair up scientists with schools. And the scientists work in the schools on a research project with the school students, and actually the school students do most of the research for most of the chunk of the year. And so these research projects vary from, we've done lots of projects involving exoplanets and school students discovering things about new exoplanets. The students on this call will talk to you about some of the things that they've been doing with Jupiter studies. But particularly, we're trying to work with school students who don't normally get these opportunities, or school students from groups that typically are underrepresented in science. And science really at the moment, and particularly physics, has just some chronic and terrible inclusivity problems. For instance, from age 16 onwards, we find that only 20% of the cohort are girls. And so there's some problem with our system in science at the moment that means that we're not supporting girls to feel like they can become physicists if they'd like to become physicists. And so as much as possible, we hope that Orbits is trying to address these issues. Particularly as well, there are issues with income demographics, for instance, that we find that you're 6 times less likely to get an A at A-level physics if you're from the lowest income background than if you're from the highest income background. And in fact, you're 3 times less likely to even take physics if you're from the lowest income background. Similarly, we have inclusivity problems from an ethnicity perspective in the UK. In the last IOP Institute of Physics study of the UK PhD cohort, we have about 2,000 people in the UK doing PhDs in something related or directly in physics at the moment. And only 10 of those students were Black in the last study. So we have these deep-seated diversity issues, and they probably spin all the way back to school and maybe even preschool and our society as a whole. So we're trying to break that with Orbits by really providing scientists to the school students, and not for a one-off visit. I really want to stress that it's really important that school students get to actually know the scientists. They get to realize that we are fallible, that we're human beings, that we're not, that we're not these Einstein figures that generally the population think we are. And that's really important, because when you look at the reasons that school students don't go on to do physics, and you specifically look at groups who are underrepresented in physics, a lot of the time, they can have all of the attributes of like hard work and curiosity and creativity that you need to be a physicist, but they're not choosing to do physics because they think they're not smart enough for it. And it's a ridiculous paradigm that we've created. And so some component of this, of Orbits, is hopefully that they get to know a scientist and they realize, oh, we're fallible, and like maybe we're not that far removed from them. And also they get to do real science. They get to do real research that typically isn't available in a school classroom setting. Typically, school science at the moment is essentially you learn some things and then you write it on an exam. And that's the model that we built for our school education system for physics. And it's really not representative of what we go on to do, and what you've probably seen if you've watched any of the live stream today. Actually, the skill sets that are involved in learning things and then writing them on an exam are quite different from solving problems that have never been solved before, or creating new things that have never been created before. And really, that's what you want your scientists to be doing, right? Creating new things and solving things and discovering things about the universe that we didn't know. And so the hope is that by giving school students access to research and by giving them the chance to contribute, and we do find that they contribute, in fact, more than 250 school students who've done Orbit so far have authored publications in scientific journals that discover new things about the universe. So they are directly contributing, and it's a lie to think that school students can't directly contribute to the science knowledge and can't feed into science and create this body of knowledge that exists, rather than just being given it. And I think that actually gets to the root of the problem, that really the school system is giving students knowledge when actually we should be letting them create that knowledge and create that new science for society. So I think that pretty much sums up the program. Did that sound okay?
Yeah, I think that's great. I'm just going to pin and say hello to the students who have been here. Hi, I'm Lucinda Offra, the RAS Education Outreach and Events Officer for the Royal Astronomical Society in London. I'm so happy to have you here. Hi, then Dr. Becky Parker, thank you so much for sharing your classroom with us. I'm going to bring on some scientists now, and you get to ask them questions. Hello, you get to ask them questions. So
Lucinda, just before we do that, I'd like to give the students a chance to share some of the cool research they've been doing.
Oh, absolutely.
Because they've got, to show that it genuinely is like cutting edge new science research.
You just say when you want to do Q&A, so I'll let you continue on then, and
then maybe
who you want me to pin? I'll pin Dr. Becky Parker's classroom, perhaps.
Yeah, so actually maybe Declan and Sam. So Becky, okay, just before we do this, Becky, I don't know if any of the girls in the group want to talk about the project or want to share any of their experiences from it, maybe after Sam's presented, but equally zero pressure, no worries if not, we can just do a Q&A. But maybe, so Sam, if you talk through some of the cool X-ray and UV stuff that you've been doing, and then afterwards, I guess if any of the students at Simon Langston Girls' School want to talk about their experiences, then we can do that.
Okay, so Sam is on now, and I'm going to remove your pin, Will, and I think is it Sam with Declan?
Yeah,
that's correct. Is it possible to add Sam as a panelist so that he can share his screen? Because he ran over to join us from another meeting, so I wanted to make sure the audio was ready for him.
So you're a panelist, Declan, is that correct?
Mm-hmm.
So
is it up in you?
So you have permission to share.
He's raising his hand to share his screen if possible.
Is he? Oh, he's an attendee. There we go. Let me promote them to a panelist. I thought Sam was the person sitting next to you.
That is, that's he came in straight from another meeting, so I wanted to have the audio ready and not
Okay,
like,
I think I
let's
brought
update Zoom.
I think I brought his computer over. Is all good now, Sam? Let me know.
Yes, all perfect. Thank you. So I just play from.
Yeah. Is that right?
So basically, in the Jupiter project with Will, and as you can see, the team that helped produce this set of slides, which is Leona Berner, Rosie Duran, and Ainsley Walker, we were looking at studying Jupiter's aurora and the relationship between the X-ray and UV emission. And so to kind of like preempt that, I want to start with what is the aurora. And for many people know that the aurora on Earth, at least, is what we experience as the northern lights. But you might not know that these are caused by the magnetic reconnection of field lines on the planet that accelerate charged particles down into the atmosphere. And in the collision of these charged particles, it releases wavelengths of light. Whereas on Jupiter, we see an aurora similarly, but in a different wavelength of light. So on Jupiter, rather than seeing the aurora in the visible spectrum of light, we see it in the UV and X-ray emission, and as well as observing it, I think, in some other at the moment in radio, for instance, but it's not visible. And so we specifically looked at it in the ultraviolet and X-ray wavelengths of light, which are much more high energy than the visible light, to try determine if there's a relationship between these two wavelengths of light in Jupiter's aurora. And so you can see as well a further difference between Jupiter and Earth's aurora in the structure of it. Here you can see Earth's auroral circle, and the areas of high activity shown in the red and the green versus lower activity in the blue, contrasted against the Jupiter's aurora, which is obviously much bigger and relative to the size of the planet, but also slightly differently shaped, and where is high energy and where is low energy and where is more active. And so I guess the question that kind of starts for many people is why bother studying this? And so we say that the reason is that it helps understand the Big Bang, the materials making up Jupiter around it, and how solar systems evolve, and possible life elsewhere. And these are all important things, but I think more importantly, it's just interesting. You're studying it because it's a cool thing to know. And I guess more context that we want to add to this is, before we go into actually looking at what we've studied and the periodicity and what that led us on to discovering, is it's more focused on now Jupiter's aurora. Having introduced you to the differences of Earth's aurora and Jupiter's aurora and how they differ from each other, it's good to take a more focused look at Jupiter's aurora itself. And you can see here Jupiter's auroral oval in this animation on the left, as well as in the photo on the right. The Jupiter's aurora, we'll talk about it a lot in terms of dawn, dusk, noon, and polar region. So these are defined by what side of the planet they're on. If they're on the dawn side, the dusk side, and the polar region accompanies all of that. And you can also see distinct like traces and footprints and stuff in aurora that just make it quite distinct. So, for example, on the far right, you can see a little trail, which is Io's, the volcanic moon's trace on Jupiter's aurora. But now I can actually start and get into our actual experiment. So what we were looking at was, as I said, was the relationship between UV and X-ray and how they were correlated. And to do so, we looked at use two different telescopes. We used Chandra for the X-rays and Hubble Space Telescope for the UVs. Obviously, this had with it several uncertainties due to how they have different periods of viewing time and you see that a lot in the X-rays, where we're not able to really spatially say where an X-ray emission is coming from, which later on leads us into a couple of unanswered questions about what we've discovered. But in general, we get the X-ray emissions from Chandra and the UV emissions from the Hubble Space Telescope. So from that data, we produce light curves. And what light curves are is plotting UV power and X-ray counts against time. So in these graphs, you can see from the polar region, you can see all of the UV power in green, red, and purple, and yellow, which shows the polar HST mean, standard deviation, and a 95th percentile of that data, and shows the power for those specific requirements. And you can also see X-ray counts, and these are plotted against each other. And this was initially where we tried to visually see how they were related, because you can see here that peaks in the X-ray and the UV seem to line up a little bit. So it follows from that you would assume that they might be correlated on later on. But this is one of the first methods of graphing our data that we used. And then we also use other data methods, such as these videos, which produce time videos of what's happening on Jupiter's aurora minute by minute, and where X-ray emissions appear relative to where's high UV emissions. So the X-ray emissions are shown in the dots, and the UV emissions are the darker regions, like the orange regions that show up like this are the UV emissions, stronger UV emissions. So after looking at that, and that was about a year ago, we came to the conclusion that they seemed to pulsate with some similar frequency. And if not at the same time, it just seemed like there was some sort of relationship, but we were not sure why or whether this was actually true. So this year, we went in more into depth to try to see if they were correlated. And so we used the Pearson's correlation coefficient for our investigation. So here, for example, we plotted the mean UV power versus the X-ray counts and drew a line of best fit across it. And the Pearson's correlation coefficient for those who don't know is between -1 and 1, with 1 being a perfect positive correlation and -1 being a perfect negative correlation, and everything in between being varying levels of correlation. So in this one, you can see a particularly strong correlation. Off the top of my head, I believe it's a 0.6, which for our data is quite a strong indicator that there is a relationship between the two variables. You can see again, you can see it. So from there, we went more into depth to find out in other examples how two variables were correlated. So here you can see in the bottom on the Excel sheet screenshot a bunch of our initial data and what it yielded. So we first experimented with binnings, which is the amount of data we kind of took for a period of time, and try and find which binning would give us the best number of points for our graph for which we could plot a correlation plot for. And then we kept on producing correlation points, keeping in mind the UV family and what type of aurora that we were seeing that correlation for. So across these 3 different data sources at the top, we started to develop an understanding of how there's a relationship between UV and X-ray emissions in Jupiter's aurora. And so from that, we kind of begin to see that they were correlated, that there did seem to be a correlation. And by looking at the videos, it seemed that they were also somewhat spatially correlated, like they seem to happen at the same areas. So if you see in this video where there's an injection of X-ray events, there also seems to be an injection of UV events around the same time in the same place. Now, obviously, this is quite a hard claim to make because there's such large uncertainties in the X-ray data of where they actually are. So we took beyond that, and what we continue working on is we find more regions on Jupiter's aurora that we could take more data from and compare across those different regions. So now we're able to define an area, say, of Jupiter's aurora that we think is particularly high activity in X-rays and compare it to another area which is particularly high area in UV. And that's kind of into two things that accounts for maybe partly the uncertainties and saying that, well, yeah, these all are happening over there, so maybe we're systematically wrong in where we think the data is coming from. But also it's letting us see that maybe the region we're taking is too large and not specific enough, or maybe there's certain areas that are correlated to other areas. So by having defined more areas, we can start comparing correlations across areas and stuff like that, which is a new place that we can take this kind of idea of correlation between UV and X-ray emissions from Jupiter's aurora. So that's all what's really exciting and what's next and what we'd plan to do. And that's coming in the future, but I'd like to say thank you for this so far, what we've done so far, to Will Dunn, obviously, for supervising the project and helping us with the data and all of that. But also this work builds on work that was started 3 years ago by Daisy May, Kirill Feigelman, Ben Sipos, Ainsley Walker, Rosie Duran, and Leona Berner, who have all been working with me to produce, and before me to produce, some of this data and stuff that led to us reaching this point where we wanted to focus in on this. So thank you very much for listening.
Awesome stuff, Sam. Yeah, that was really great. Do any of the Jupiter folks, so you missed one of the really important wavelengths when you were talking about Jupiter, which is infrared, which is what Tom and the team are doing right now, with with the James Webb Space Telescope and with Keck at the moment. So I don't know if anyone has questions based on that. Tom, I saw you staring intently at the screen, and that left me deeply concerned, but also you always have these incredible.
Oh, it's so good. It's really interesting. I have a lot of theories about this that I won't go into, but really interesting stuff. And seeing those movies of the spikes of X-ray coming in at the directly plotted on top of the images, so I don't know if this is a question maybe just for Will, because he might understand the details a bit more, but those X-rays are so sporadic. How do you have a sense of each of those dots being meaningful?
I think that's the crux of the X-ray, the X-ray question, right? So I think, to be honest, we took some inspiration from your 2017 paper, which by basically just summing up longer periods of time until you can start to see structure. Because when you see some of the videos Sam showed, you're just seeing single dots at a time, and it's really difficult to notice if there's any relationship. But I think Sam, you showed a video that was on your slide with the Excel spreadsheet at the bottom, but the third video on the top, where it maybe had a longer time window, and you can actually see them. You can see that they're starting to form the same structures as the UV over the longer timescales. The problem here, and I guess this is me pitching, the problem here is that we're so limited by observing from Earth orbit and trying to look at Jupiter, right? It's such a long distance away, particularly for the X-rays where they're kind of a bit rarer. If we had an instrument actually at the planet observing it, then you see 10 to the 7 times more counts. So it's a complete paradigm shift. You would actually start to see those beautiful high photon regions that you see in the UV with all these arcs and the different structuring that you see in the pole that Sam just showed all the videos of. An X-ray instrument that was orbiting it would see something similar, but the equivalent for the X-rays. And so you would start to see these arcs because you have 100,000 counts per second rather than one. What was it, Sam? 1 count per minute, or 2 counts per minute. And similarly, the students from Langton Girls School have had the same challenge where they're using a slightly different instrument, so you get a few more counts, but you're still kind of maxing out at 20 counts per minute, and it's really difficult to connect those things up. yeah, I don't know. Sam, did you have any thoughts on that?
Oh yeah, just to add, like I think the one positive thing from the X-ray data is that it actually extends the HST UV data, because we only had a 90-minute slot, I think, for HST data, whereas the X-ray emission data like surpasses that. So at one point we did actually extend the light curves beyond the HST UV data. And so we actually had, like, I guess, a more abundance of X-ray data to look at. It was just from a different time period, but it's one advantage from it.
I think it would maybe sort of pitch in there, but before Sam came onto this, like a lot of these things, of course, those earlier slides, some of those were like adapted from like Daisy, Kirill, Ben, and of course it was Daisy or Kirill, I think he pressed you back in maybe like 2020, 2021 to start adding on the sort of error bars. So we do have sort of some kind of a sense, don't we, about like what are good places to trust and what are less good places to trust.
I think that's actually, and for any scientist watching this, I think the idea that when you do a project like this, that it's some sort of like charity work and you're giving directly and not getting anything back is nonsense. The amount of new scientific ideas or new directions that the project's taken because of Daisy's ideas, because of Sam's ideas, because of Kirill's ideas, there's lots of new science directions that this has taken because of their ideas, and it's not been in any way charitable. Like I as a scientist and selfishly have got so much better understanding, and we found so many things. Well, we published a paper last year with some of the students from the school about the first generation of ideas, and I think this set of UV X-ray correlations is working its way into a paper right now. So yeah, so I definitely think it's really symbiotic. It's not. Yeah,
I mean, the stuff that we've seen is really amazing, and it's worth pointing out that, you know, students are struggling with this concept not because they are students. We're all struggling with this region. No one understands this region, except me, obviously. But it's a profoundly weird bit of the aurora that we're really struggling with. And Johnny was on earlier talking about his new observations, which will be Hubble and James Webb at the same time. And if we can do X-ray with that, we'll have the best shot yet of trying to break it. Because as you know, one of the reasons your students didn't talk about the infrared is because it's so different from the X-ray. You can't necessarily compare them very well. But if we're able to compare all three, I think it would be profoundly interesting, because one of the things I really love about X-ray is that it is so different from the infrared that if you have both, you're getting two different buckets of the atmosphere and two different pieces of information. So it's really nice to be able to sort of see this comparison and contrast in what you're seeing. And I'm hoping we will not see any of this. That's my prediction. In the infrared, I think we won't see anything. I changed my mind about what we're seeing, and I think that a lot of these weird swirls and stuff that you definitely see in the UV, but not necessarily in the X-ray. I'm not sure that you do. I think that the swirls are a UV only event, and I think the X-ray stuff you guys have been seeing are pulses from the magnetosphere, which are completely separate from the superimposed swirliness that you see in the UV. And if that's the case, then we definitely should be able to pull those apart with James Webb as well.
Well, we should. I mean, we're creating science on this, I guess. So we should definitely do that proposal to Chandra and XMM and see if they're willing to give us the time to coincide with HST and JWST. That sounds like an amazing campaign. So we'll propose it and we'll see if they're willing to give us the time. And then maybe some of the students on this call can have a go at looking at that data.
So Lucinda said that there is a question for Sam.
Oh yeah, so Sam, did the X-ray dots in the auroras represent single photons or some sort of average?
Yeah, they represented single photons.
Yeah, that's our starved X-ray signal. Any other questions for Sam? And then I guess we'll switch over to Becky and Simon Langton Girls. And then I guess we've got a Q&A. Sorry, are we massively overrunning here?
Yeah, that's not a problem. It's fine with me if it's okay with Henrik and Tom and James and Katie. It would be great to, I mean, we could definitely do a Q&A. I would love the students to at least know why we are gathered today. So if you don't mind, I'm just going to quickly share my screen and just let the students know, and then we can go to Becky and just hello everyone. Today we are completing a 6-hour observation of Jupiter using the infrared telescope facility at NASA's facility on Mauna Kea, Hawaii. We're using Keck and JWST, but Dr. Mellon and Professor Stallard and company can tell you more about that. And this is what you are part of this program that we are completing now. And I'll definitely give this link to Will so you can watch all of it in its entirety at your leisure. But I'm going to hand it back over to either Will, who wants Becky to go on, or Tom to talk about the science that was done today. So Will, Becky, did you want Becky to go? Do you want Tom to go? It's up to you.
Should we do, so if Becky and any of the students at the Girls' School want to talk, and then I guess we could do the Q&A at the end where Tom reintroduces it and then the students can ask.
That sounds great. Thank you.
So, Lucinda, can I just check? Can we go back and watch all the images then at a different time?
Yes, so I'll send you the YouTube link. I'll email it to you now.
Oh, fantastic. Yeah. So we could have a quick look through to see all the amazing images which clearly were earlier.
Oh, well, Tom, did you want to talk about what images we did see? Maybe if you want to share your screen really quickly, I think that's something we can do. Becky, if that's what you're interested in.
That'd be amazing. I've got a room full of students as well as orbit students who are all so excited.
Yeah, I would love to pin Tom and Henrik and James in Japan and let them tell about themselves and what they've done today. We'll do that right now. Thank you.
Fantastic. Thanks.
So there's a lot to talk about for today, right? We've talked about a lot of different things because today is the most manic day of my entire career. We're doing lots of different things all at the same time, which is why it's super interesting. The two things that are really unique and unusual about today is, one, there's a spacecraft orbiting Jupiter called Juno, and Juno, about, I guess, 2 hours ago, was communicating back with radio telescopes on Earth and watched the signal fade away as Jupiter moved in the way. And that allows you to use that data to measure what the ionosphere of Jupiter, how it changes with density with altitude. So they can get sort of an altitudinal profile of how dense the ionosphere at the top of the Jovian atmosphere is. And at the same time as that, ongoing and still going now, are a whole sequence of James Webb Space Telescope observations where we're using the James Webb, the biggest and best space telescope ever put up into space, to look at Jupiter and to look at that region, the top of the atmosphere of Jupiter. And so we're doing a sort of clockwise scan all the way around the planet that's going to take about 22 hours. So we're at the start of that. And while we've been doing that, we've also been looking at Jupiter from two telescopes on Earth, the Keck telescope and the IRTF. I was going to show you what's happening right now, yes, but please. Right now there is clouds, lots of clouds. So what we're observing right now is the Earth's atmosphere. But earlier in the night, we were able to see Jupiter very cleanly and clearly. So we had both telescopes looking at different parts of Jupiter to try and pull out more information about the top of the atmosphere. So everything that we're doing is all focused around this sort of thin edge of space above Jupiter. And that's a really interesting place because it gets affected by the underlying atmosphere as well as the surrounding space environment. So what you can see on the screen right now, what you could see right now was a view of the weather at the mountain summit. You can see the summit. It's all lit up because the moon is above it, and you can see lots of cloud and not much space. And that cloud is now so thick that even we can't see through it. So a real shame, but that is what's happening the other side of the world at nighttime in Hawaii. And as I look at it, we can't really see anything in the imager, let alone the spectra. But in the past, we had nice clear skies, as you can see here. So this is about an hour ago. And during that time, we were able to take some really good data of Jupiter and get some really nice, clean and clear pictures. So if you roll back time on the live stream later, you'll be able to see that and see us looking at Jupiter as an image and also taking spectra of Jupiter. So really, really cool ability to see what's going on from Earth. But of course, Juno can see right through that. That's not a problem because it's using radio to look at Earth. So that measurement was not affected by the weather here on Earth. And of course, James Webb is out in space taking data of Jupiter as well. So it's a very unusual day. You don't usually observe with more than one telescope. We have two telescopes on Earth looking at the same time, as well as James Webb, as well as Juno, and potentially as well as Hubble, I think, as well. So we've gotten a profound amount of data that we're going to have to try and think about and understand as we move forwards. And people that you can see on the screen are in the UK, in Japan. We have colleagues out in Boston, and the observations are happening in Hawaii. So it's a worldwide network trying to get these observations out. So that sounds all very impressive, but we're just muddling along and hoping for the best, to be honest.
I did want Tom to share his screen to show, but I don't mind, Henrik, and if you want to introduce yourself and then who you are and what you do, and Paula, your student, and also then James and Katie would be great to say hello.
Sure. Sure, absolutely. So my name is Henrik Mellin. I work at the University of Leicester. That's where we're sitting right now. And I'm nominally working on the technical side of the James Webb observations. So right now, we're taking data at 85 degrees north. And I think we're getting some beautiful views of Jupiter's northern aurora as we speak. I think that this is a good longitude. This is observation 6 out of 36. And so we're barely getting started with the James Webb stuff, but we did observe, yeah, this is the geometry of the observations. So we're scanning the small green box around the limb of Jupiter. And we do that trying to capture the vertical extent of this upper atmosphere, how that extends into space, and how we lose parts of the atmosphere into space by atmospheric loss, essentially. So we started around, was it 1 o'clock? The observation is going to finish tomorrow at 2 p.m. So this is going to be James Webb's work for the next 24 hours. Just going to complete this scan for us, and hopefully, I'm pretty convinced there's going to be some amazing data. It's the best telescope in the world, and here we are using it. So,
and we're going to see some of that on Monday, hopefully. Fingers crossed.
I need Tom to give us access to the data. That's on his to-do list.
Yeah, on my to-do list is to find out from Henrik how to do that.
I'll send you a link. Yeah.
And then we have James and Katie in Japan.
Oh, Paula, did you want to say something?
Sorry about that, Paula.
No, that's all right. Yeah, I'm Henrik's student, and I work on very similar observations, but with Juno. That's a spacecraft around Jupiter, so constantly looking at Jupiter. And yeah, so hopefully we managed to combine different data sets, some from space and some from ground. So yeah.
Great.
I think James and Katie can talk now.
Yeah, we're actually in Japan over here, so it's just gone midnight, and Katie is leading the observations with the NASA Infrared Telescope facility, which we're using remotely from Japan. The telescope is in Hawaii, but we're in Japan. I know it makes no sense, but it's what we do. No, we're over here to do some work, some different kind of research. And but yeah, this is Katie's main project. So I'll let you talk about it.
Yeah, thanks, James. Yeah, I'm Tom's PhD student, and my PhD project is all about Jupiter's upper atmosphere away from the aurora, so more like in the equatorial region, and the extent to which that equatorial upper atmosphere is driven by Jupiter's strong magnetic fields. Yeah, and this observational campaign I'm the lead for has been scanning Jupiter from the North Pole to the South Pole, or in some cases the South Pole to the North Pole, every 2 nights for a whole month. Thank you. Yeah, so scanning from like the top of that image of Jupiter, you can see all the way down through the equator and then down to the south, so that we can see Jupiter globally across an entire month.
Yeah, so our observations concluded about was that half an hour ago? Very successful. For about 2 hours, we were looking at the whole planet, and it started to get cloudy at the end, but then the clouds cleared just in time to get some more data. So we looked at the top of the planet, the northern aurora, so like the northern lights on Earth, but those data that we got with our telescope, the NASA infrared telescope, were recorded roughly at the same time as the other telescope, the Keck telescope. Both telescopes are based in Hawaii, and so yeah, we've never looked so much at Jupiter at once, I don't think, in the history of our field, I think.
Excellent. Thank you so much, everyone. Would Becky, Dr. Parker, would your students like to ask the questions to the panel? Or
looks amazing, honestly. So all those observations went on today, and when will they compile? Like, so it's Monday when the JWST images will be processed, what, from the infrared into something visible, into a, equivalent image. Is that right?
So that's Henrik's job over the weekend.
Yeah. So we can't see it now, anything, can't see anything.
I'm afraid not. No, it takes time to download everything, and they haven't finished taking the observations yet. So, it's going to finish tomorrow about 2 p.m. You have to download everything. Everything has to be processed as well. You get the raw data, but you want to process it in some way. And then hopefully there'll be some pretty pictures to show on Monday. Fingers crossed.
So our students have been doing that with Juno data and XMM, is that right, students? So we've been doing X-ray data analysis and looking at the aurora with Will, obviously, and they've done amazing things. But is this really unusual to do every telescope looking at Jupiter for a day or a day and a bit? Amazing.
Incredibly unusual. Yeah. It does happen every so often, but not usually. If it does happen, it's something like the Schumacher-Levy 9 impact, or some big globally announced news event. For us to just be the only ones doing it and having so many telescopes looking at once is pretty crazy, and very privileged to be able to do it.
Yeah, I can't wait to actually sit down and look at this data. Yeah, I mean, it's so much of it, right? You have to triage a little bit, but yeah. What's the most important thing to see?
Henrik, can I ask you to share that screen that shows the students all the schedule of observations? And it's just really interesting to see how it's organized and which ones have already been collected and archived, and how many more do we have to go?
So this is the Space Telescope Science Institute has a website for each program, and this is the website for our program. You can see what's happening with the observations live live-ish anyway. And so the time now is, in universal time, is 3:15. So we should be looking at this observation. It says collecting on this one. I wonder if that's a little bit delayed. But these ones above, it says archived. So we have 36 observations in total. It says 37 because for some reason I started on 2. But we have 36 observations. We've archived 4 of them. And that means the data has been sent back to Earth, and we can actually download it at least very soon. Collecting means the telescope is taking the data right this minute, and then these next one's going to happen in the next 24 hours or something like that. So it's all coming down. It all seemed to have worked. We have to look at the data to confirm that properly, but this is a big day, I think. I can also show you this. This is the collection of dishes that makes up the Deep Space Network. And that's a network of radio dishes that talks to all the space missions out there around us. So at the top, you have the station in Madrid, and you can see JNO is the Juno spacecraft. So this dish here called Lucy is now talking to Juno as we speak. And we also have James Webb down here, although they're not talking right now, which probably means we're not getting the data right now. Oh, it says at the top, doesn't it? Oh yeah, so it's the Canberra one. I misunderstood. So the dish in Australia is talking to James Webb, transferring probably our data right now. And this Goldstone dish is talking to the Juno spacecraft. So it's all happening as we speak, which is pretty neat. I'll stop sharing that.
And James, I didn't know if you minded if I show the students your YouTube page. He's like, thumbs up. So if you didn't know, Dr. James O'Donoghue, who's connected to us with from JAXA in Japan, I'm just going to share his YouTube page. What is it's at Interplanetary now. That's different from before, but he spends he volunteers his downtime, as far as I know, to do all this wonderful work to visualize the science. And so if you haven't seen any of his animations, I highly recommend checking him out. It's at Interplanetary is his ID on YouTube. Lots of really great visuals to see what's going on with lots of different places in the solar system. So you might have seen this. This one's really seen a lot. Well, look at this, 1.3 million on the scale of the solar system. So check it out. Just wanted to give you a shout out, James, for all the work you've done.
Thanks for the plug. Yeah, cheers.
We are so excited to see you. We didn't realize that was you, James. Those images all
right. You got a celebrity amongst other celebrities.
Brilliant.
Oh, thank you very much. Appreciate it. Yeah.
No, they're brilliant. Got a quick question from a student.
Hi, I was wondering why are the photos all taken together at the exact same time? What advantage is there for them all to be taken together rather than like a few days apart or months apart? Is this something that can only be done at a specific point in time, or is it like to compare data or something like that?
So, I mean, there's a really good question, and there's a really good reason for it, which is that Jupiter, as you know, you guys know that how variable Jupiter can be, right? The aurora is changing all the time and throwing energy out. And one of the things we're really interested in is how that energy moves from the region you're looking at and washes down equatorward. And so the closer in time we can get, the more likely it is we'll be able to see those waves of energy as they pulse away from the aurora. So if we did one a day over a period of a month, we'd get some of the science that we want, like looking at the altitudinal variations on a more broad scale. But what we're hoping we will see is some of that auroral activity forcing waves to move down through the planet, and we should be able to move around the limb and be able to pull out that kind of wave activity as it pulses through the atmosphere. So there's a real advantage in being able to do it as close in time as possible, because then we're sort of taking a snapshot and at the moment we're moving up, but later we'll be moving down through the planet, and hopefully we'll be able to sort of see any of those waves, if they do move, moving into other frames as we look.
I was going to add just one thing. If you have like a picture of a heat wave on day 1, and then you look at it again on day 2, and it's in a different place, you have a distance, and you also have a time, so then you can work out the velocity, so you can figure out how fast it was moving exactly, which is good, because normally it's difficult to understand the weather, like the wind speeds and stuff like that in the upper atmosphere. So it's a way of actually visualizing the winds. There isn't any clouds in the layer we look at, so there's not really much to go on. Yeah, that's a really fun part of this. And if we have all these overlaps, we can get a really good, accurate measurement of those velocities. Yeah.
Yeah, so all data sets bring something different to the table, right? They all do something slightly different. And it's in combining those, you're getting added value in your science, right? And there'll be some hard work to put all that together, but yeah, it should be fun.
Fantastic, absolutely brilliant, thanks.
Any other questions from Dr. Parker's class? Maybe not. So we can wait to check in with us. Oh, she's good. Okay, Will.
That's brilliant. Thanks so much.
Thank you for joining us.
Thank you.
Thank you.
Yeah, thank you.
Great questions.
So it looks like Tom, you're muted, but it looks like Tom might be sharing his screen with us.
Oh, wait. Never mind.
Sorry, yes. I'm sharing it because you can just about see Jupiter right now. You can see it.
Oh, look, this is a live stream. Oh, sorry.
So the clouds are pretty awful, and it's moving in and out of the clouds, but every so often we're getting a break in the clouds and you can see Jupiter through them. And it's pretty nice when it clears up. But right now the clouds are really thick. So we've been really lucky. We've had some really good weather over the last month where we've gotten some amazing stuff, but today has been a bit more variable, I would say. But we have James Webb, so we don't need ground-based, right? That's okay.
Yeah, we did get some really good, I think, at least possible ground-based data in Katie's program on the infrared telescope facility and Keck as well. By the way, I just downloaded one of the cubes from Webb, and it seems to have worked. We'll see the see H3 plus, which is what we're interested in. So yeah, all worked.
Good. Yeah. There was a moment where it said only I had access that I felt incredibly powerful. Then I remembered that Henrik's the only person who can actually do anything with it.
Thank you.
As of this moment, nobody's seen it, right? So you're seeing it for the first time as well.
Yeah, that's right. Paola's seen it now too.
Is there anything you could show us, Henrik?
It's on the wrong screen, but how shall I do this?
This would be fresh JWST data.
Mm.
Can't get any better than that.
Let's try it.
This will be the fastest press release in James Webb history, right?
It's not going to look pretty at this stage. That's the only thing I'd say. It needs some processing.
I think that in itself is interesting, though, right? The rawness of it.
Exactly.
Why don't I take you through the process? I'll have to log in first.
You could show us anything and we'll believe you
Yeah.
as well.
Share my screen. This is the interface to the Space Telescope Science Institute portal. It's not the most swish-looking thing in the world.
Maybe it's slower because you're sharing.
So all the ones that are yellow have been downloaded to the server. Let's pick one up that's been processed. This one. So this is at 45 North on the Dawn side. They have this visualization tool. See a little preview. So we're all going to be the first to see this together. It's taken only a few hours ago. Oh.
Better on his.
I don't know if everybody froze. Is everyone- There you go.
Just my internet connection is unstable. So this is what the spectrum looked like when you divide it into basically infrared colors. Oh. This is a bit underwhelming. I appreciate that.
Yeah, Henrik's going to turn this into gold.
I don't know why it's not.
You're giving these students, you know, an experience of a lifetime right here by just, or, you know, even the audience who will watch this later, they're going to get the full gamut of experience of observations and to be able to get this data so quickly. It's just quite phenomenal, to be honest.
I mean, the one thing I can see in this data, you can see that the spectra goes from 3 micron to 5 micron, and it's really bright about 4.6 onwards, right? You can see how it's very flat. I think it's being a bit ruined by one spike that we got. But out at 4.6 onwards, it's much brighter, and that's because Jupiter's hot, right? So the internal heat of Jupiter is leaking out and brightening that wavelength range. And so that region is glowing from the internal heat of Jupiter as a result of its gravitational collapse over the last 5 billion years. And that's why that bit is brighter. We're looking at a range shorter than that and right on the edge of the planet. So it's a little difficult to see what's going on. But there's something going on in those images for sure.
Yeah. Ooh. So this is what it looks like raw. And I think we're saturating a little bit here.
Yeah.
Incredibly bright. But this will all be tidied up by Monday, I promise.
So a lot of the students will have experienced something similar to this, I imagine, because I know that the X-ray data is incredibly sparse and difficult to understand. And then, you know, the UV stuff looks really pretty, but needs a lot of work, even in its calibrated form, to get out something useful. But here, we're struggling to get the details out, and that's because there's a lot going on in this data set, and you can see that a lot of it is probably noise from the instrument.
Yeah, I suspect there'll be very little noise in this data eventually. But anyway, another spectrum, so that looks promising. So all this bright stuff, it's expected. I suspect this is the limb, right?
Yeah. You can definitely see Jupiter, which is good.
Yes.
I mean, at the very least, right, that means we're in the right place.
Yeah.
Because
we got the right planet this time.
Yeah. Didn't miss, which is great.
Yeah.
It's just
Anyway, I'm just clicking now. So sorry. Right, there we are. We have data. It will work.
Oh,
This is why we wanted to wait until Monday before we show the first views. Even those are not going to be amazing to look at necessarily, but it gives us the opportunity to try and at least do the first calibration of the data and try and pull in something useful rather than just this mess that you can see right now. And that's why they pay Henrik the big bucks.
I wish. Yeah.
well, fantastic. If we went 30 minutes long, so I'm very happy to do that. But I wanted to give you guys an opportunity, and just it's already been fantastic and amazing, but an opportunity for any last things you want to say before we wrap up and say goodbye from our 6.5 hour observation today.
Yeah, thank you so much, Lucinda, for facilitating all this. I think it's been absolutely brilliant, and as always, a lot of fun.
Yeah, thank you. It's not easy to round us all up from around the world and all different time zones. Yeah, thank you for arranging.
3, 4, what is this, our 5th observation? Oh my God, I enjoy every single one of them, believe me. And I'll watch this one 10 times as well. But how are you guys feeling? Are you going to go for another more observations after we say goodbye? I mean, what do you guys do after this? Do you go straight to sleep?
Well,
probably. Oh, if we're at the mountain, we will definitely do that, and you guys are going to do that. It depends, I think. One of the advantages of observing from the UK is that you end the night and it's late afternoon, so it's quite go for a walk. Stuff that you can't do when you're actually at the telescope. But yeah, I think in the short term we'll just rest, right? But it will certainly be interesting to start to see what's coming out from James Webb when we start seeing the first of those results. The other data is more normal to us, and so we're not quite so excited about it, and it will be a really useful resource on the medium to longer term. So we're going to spend more time working through that and analyzing it. And we have to figure out who's going to do that. So some of the younger faces in the room might get strong-armed into doing some of that work. But ultimately, the aim is to start addressing those science questions. And that is a long-term thing. As the people involved in orbits have experienced, it's a slow process to go from what looks like really pretty things to meaningful things and getting some really interesting results. So that's the long-term aim, which, I would say, I'm not sure we've quite gotten there with some of the data that we took last time we spoke and looked at Uranus, for instance, that some of that is now coming out as papers. So it's a year or 2 years sometimes to get that to that stage. But we're going to continue to look at Jupiter for now until it's finished, although it's swamped by clouds still, and then take a rest. I think we will be observing again on Saturday, 2 days time. So we'll have another 2 hour observation with IRTF, and then the last one will be the last of the entire month, which will be with you again on Monday.
Yes, that will be with Dr. Robert Massey. He's going to host that. It's a 3-hour observation, IRTF, and also looking at some of these images that data that Henrik's going to spend the weekend processing. Sorry, Henrik.
Oh, my pleasure.
You get some sleep this weekend.
We're all going to be relaxing while Henrik is doing all the work. Yes.
What time is it in Japan right now? Is it almost after midnight, I think? Is that right?
Yeah. Midnight and 30 minutes. Yeah.
Well, it's been just it's always a pleasure You know, I'm always up for a 6-hour plus observation with you guys. The team is fantastic. And I just want to say a big thank you from me and the Royal Astronomical Society for sharing all of this with us. This is, you know, to be able to see JWST data like that all in a day's work. It's just, you know, dream come true, phenomenal thing. I never thought I'd be able to see it that quickly. So thank you so much. And Will's like shaking his head. Yeah. Will, did you want to say anything before we wrap up as well? Anything about orbits or say to students?
Thanks so much for having us, I think. Yeah, it does amaze me that you get the data within, so our X-ray data you wait, best case you wait like 3 days, but the X-ray spacecraft have like a 2-day orbit around the Earth basically, so you have to wait till they get back to those satellite dishes that you were showing to get the downlink of the data. But yeah, super cool to see it so quickly. That was really amazing. And the resolution on those spectra is insane. Like so many, and then you zoom in and there's even more little bumps. So yeah, really, really cool. Yeah, so thanks for letting us be part of it, I think. Yeah.
Thank you to Declan and Sam for joining us, and Dr. Barker's classroom. I don't know if any of the students are still there, but thank you so much for hanging around. And I think I'm going to sign off now. If anyone else is having anything itching else to say, going once. Going twice.
Yeah, I just wanted to say thank you, Lucinda. It's been great again. It's always amazing how easy this is. I send you an email saying, "Can we do one?" And then that's all I do, and you do all of the hard work.
Focus. I am very much an action-oriented person, so you just give me a task and I make it happen. So that's my magical skill.
Thank you so much.
But thank you all. You guys make it happen too. So I couldn't have done it, you know, couldn't do it without you, obviously. But also how easy it is to work with you. So it's been a pleasure. And so again, just want to say thank you to everyone. Thank you for being with us this whole time. We are it's just been a fantastic day. Again, this goes by so quickly. Thank you to the H3 Plus team, Professor Tom Stallard, Dr. Henrik Mellon, who we look forward to seeing again, both of them on Monday for our Eyeing the Ionosphere 2 with Dr. Robert Massey, who's going to host that, and all our speakers and our guests today who shared all their skills and information on observing Jupiter and its ionosphere. Dr. Rosie Johnson, Professor Jonathan Nichols from Leicester University, Dr. Sean Prosser, who showed us some amazing illustrations of observations of Jupiter from 300 plus years ago. So it's just been phenomenal. So I just thank you everyone for being a part of this. And thank you to my colleague, Dr. Sheila Kanani, for being here today. Maybe she's still with us, but just want to say thank you for everyone. And until next time, see you Monday. Bye, everyone.
See you.
Bye. Thank you.
Thank you.
Oh my gosh. Look at there's the students still hanging out. Bye.